And we're live. We will just give folks a couple of minutes to come over and find the new stream. And in the meantime, while we wait, let's see if we can get a little rider cam. Oh, hi. You want to say hi to the weather and climate live stream, bud? All right. Seems like people are making it over here. We'll just give folks one more brief minute to find the new stream. All right, let me introduce our new host, Dave Gutzler. Welcome, Dave.
Glad to be here.
All right, we can hear you, and I will let you take it from here.
Okay. Yes, my name is Dave Gutzler. I'm actually a recently retired climate scientist. I retired in the midst of working on the IPCC assessment that came out in 2022. So I am not here to defend my own salary and position, but I am here because I'm tremendously grateful for boatloads of state and federal support over the course of my career. So we're moving on, rocking and rolling into hour 83 of this live stream. And for those of you who've been on for a while, you have a pretty good idea what I'm about to say. And that is to remind you why so many people are putting so much effort into this whole live stream. The standard script, which is worth hearing again, is just how important all this work is. Weather and climate forecasting, the script says, is a modern miracle. I was taught years ago not to use that kind of language with respect to scientific activity. I think of it as a hard-won triumph of investment by the public and hard work by an awful lot of devoted scientists. And as I said, it was my great privilege to be one of them for many years while I was a good old wage slave, if you can call being a professor something like that. But the triumph of weather and climate forecasting was made possible by decades of investment. And we are here to defend that investment by the American people. And we're doing it by illustrating just what the payoff is and by discussing what the future payoffs could be by continued investments in what all of us have been doing and sincerely wish to continue doing in the future. So with that pep talk, the link you've seen before is scrolling across the bottom of the screen, and we are imploring folks to call and make your voices heard by our elected officials as they discuss the future of the U.S. government's budget. So let's do it. And meanwhile, we have a lineup of really great speakers that I will be privileged to host. The first one is Mitch Bushuk, who is a polar climate scientist at a government lab, and is here to tell us about progress in Arctic sea ice prediction. And I'm looking forward to that very much. I played a teeny tiny role a decade ago in the IPCC chapter on attribution of climate change that included some talk about sea ice. And an awful lot of good work has been done since then. So welcome, Mitch. Thank you so much for your participation here, and you're on.
Great. Thanks so much, Dave, for the introduction. And yeah, so great seeing all the people dropping some comments in the chat. I saw one from Ariel Dreyfus. Shout out to Ariel for staying up late and watching this. And yeah, huge thanks to everyone for just taking the time to log in. I know it's late for a lot of us on the East Coast, especially. So yeah, the chat's been incredible. So also, if you feel inspired, drop a few hundreds or hearts into there just to keep the energy up. It's been great so far. Yeah, great. So in today's talk, I'm going to talk about the current state of our knowledge regarding the question of, can we predict Arctic sea ice? And my name is Mitch Bushuk. I'm a polar climate scientist at a government lab. And I just want to say a big thanks to the Sea Ice Outlook community, which is a big international community of researchers. I'll tell you a bit about what that community is in the talk today. Okay, so first off, what is sea ice? So sea ice is the thin layer of frozen ocean water that exists in the Earth's polar ocean. So we find it in the Arctic and the Antarctic. And one of the great things about studying sea ice is we have a beautiful record of satellite measurements of sea ice concentration. So every day we get a beautiful map of sea ice concentration data, and we're playing those data in this movie here. And so you can see a lot of fascinating features going on. The most striking thing you see is the big seasonal cycle in sea ice. So every year the sea ice melts back and reaches a minimum in the Arctic in September. In the winter, it cools off, the ice grows southwards, and it reaches a maximum in the month of March. And then the sun starts coming up in the Arctic, the ice starts melting, and then the ice proceeds back towards the North Pole and eventually reaches a minimum the following September. So we have this big seasonal cycle you can see. And then, of course, in the Antarctic, we have a seasonal cycle, which is flipped, of course, due to the fact that it's in the southern hemisphere. So sea ice is a really fascinating, complex, multi-scale material, and it's fascinating for a number of reasons, two of which are the fact that it's coupled strongly to both the atmosphere and the ocean. And this coupling happens both dynamically and thermodynamically. So when I say dynamically, I mean how ice moves around. And when I talk about thermodynamics, I'm talking about how ice melts and freezes. So on the atmosphere side, we have winds blowing above the ice, and these winds push the ice around, so they add momentum to the ice. We have the sun shining down, and that solar radiation melts the ice from the top, and we get the formation of these melt ponds on the surface in certain conditions. And when we get those melt ponds, it changes the reflectivity or the albedo of the ice, which changes the energy balance substantially over the Arctic. We also have precipitation falling on the ice, primarily as snow, which changes the albedo of the ice substantially, as well as the conductivity. On the ocean side, we have ocean currents flowing beneath the ice, and those ocean currents pull the ice around. They also transport heat laterally, which can melt the ice as well. And then we also have vertical ocean mixing happening, which can mix up warm, salty waters at depth up to this ice-water interface and cause melting as well. There's a whole host of fascinating processes within the sea ice as well. For example, ice is a porous media made up of these fascinating little brine channels where the seawater that the ice formed from collects and then eventually drains out over time. And the ice is also a solid material, which means that it can support some amount of internal stress within the ice. And once a critical stress is reached, the ice will actually break and fracture. And that's a really fascinating physics to study. And it's very crucial for understanding the dynamics of the Arctic as well. So when we try to model sea ice, we try to put all these processes into our climate models, and then we try to faithfully simulate the coupled sea ice, atmosphere, ocean, and land system in order to make predictions and projections of the future Arctic. So when I first started this field, I had this kind of naive picture that sea ice was just sort of like lake ice, where it was just a stagnant sheet of ice covering the Arctic, and it couldn't be further from the truth. So because of the strong coupling with the atmosphere and the ocean, the ice is incredibly dynamic. And to illustrate that, I'm showing one of my favorite observational data sets. So here we're looking at a video of sea ice age. So this is basically, for each pixel you see here, it's the number of years that piece of ice has lived for. So these bright whites you're seeing are the old, what we call multi-year ice. So these are pieces of ice that are typically 3, 4, 5 years old and beyond. And then these light grays are what we call the first year ice. And so this is ice that grows every winter, melts every summer, and it only lives for 1 year of time. And age is important because it's a proxy for the ice thickness. So this older ice tends to be thicker because it's had many winters through which it's grown thicker and thicker over time. And by watching this sort of bright white multi-year ice move, you can really get a sense of just how dynamic the Arctic sea ice pack is. It's moving around in a way that kind of resembles a viscous fluid. Over the Beaufort Sea north of Alaska here, we have a permanent high pressure system, and that anticyclonic circulation is driving the sea ice in a corresponding anticyclonic circulation. You can see the so-called transpolar drift stream, which is transporting ice from this Siberian coastline towards the North Pole and then sort of spitting the ice through this gap here, which is called Fram Strait. And then I think you've probably seen this clock ticking as the movie's played. And as we've watched this movie play, we've seen that huge amount of bright white, old, thick, multi-year ice transition into a new ice pack, which is thinner and much younger. So now we have a lot more of these gray shades, which are this younger, thinner ice. And so what we're seeing here is a climate change signal right before our eyes. Okay, so we can get a bit more quantitative with this now. And what I'm showing here are two time series. So on the left, I'm showing the time series of September Arctic sea ice extent. This is the month of the summer minimum in the Arctic again. The units here are millions of square kilometers. And so at the start of the satellite record, we had about 8 million square kilometers of sea ice in the Arctic. And in present day, we're down to about 4 or 5 million square kilometers every summer. To put that aerial loss in context, that corresponds to 5 times the area of Texas, 8 Californias, or 21 Floridas. So really, we're talking about just a massive area of ice being lost in the Arctic. The Antarctic sea ice, as probably many of you know, is a very interesting story, and it's been a bit of a mystery within the climate science community, in the sense that up until 2015, there was actually a slight positive trend in Antarctic sea ice, despite the fact that nearly every climate model was predicting a negative trend in Antarctic sea ice over the same period. Now, it's notable that over the last 7 or 8 years, we've witnessed a whole series of record-setting minima in Antarctic sea ice. And this has led climate scientists to suggest that we may be seeing a regime shift in Antarctic sea ice, where we're starting to finally see some negative trends emerging. And you can see here that the trend is now negative, but it's only modestly negative. It's fairly flat compared to what we see in the Arctic with this big decline. Okay, so in addition to this long-term negative trend, we also have a huge amount of interannual variability in the Arctic sea ice cover. And one year that was really famous because it caught the community off guard completely was 2007. So up until this point, there had been a negative trend. We had been losing sea ice in the Arctic. But 2007, the ice just kind of fell off a cliff. And this really caught scientists off guard. And this raised a question of whether we could have anticipated this big loss of sea ice in 2007. And sort of around this scientific question, this big community effort known as the Sea Ice Outlook was formalized. And so the Sea Ice Outlook is basically a community forecasting exercise, which collects predictions of September Arctic sea ice each year. And these are seasonal predictions. So they're initialized a few months before the September minimum, namely on June 1st, July 1st, August 1st, and September 1st. And the Sea Ice Outlook has been collecting these predictions of September Arctic sea ice continuously from 2008 to 2024. So we have about a 17-year record now of these predictions. We typically get about 30 predictions each month from groups all over the world. And crucially, I want to mention that this work has been funded continuously over this period by a whole host of agencies within the US as well as the UK, namely the National Science Foundation, the National Oceanic and Atmospheric Administration, the Department of Energy, the Office of Naval Research, and in the UK, the National Environmental Research Council, NERC. Actually, I think NERC is actually the Natural Environmental Research Council. So this plot here shows a typical submission to the Sea Ice Outlook. So these were submissions in June 2024 that came in. We had 27 contributors in that month, for that initialization month. And the submissions come from two main forecasting methodologies. So the green bars are dynamical models. So these models are kind of similar to weather forecast models, where we do a process called data assimilation to generate initial conditions. And then we run a a coupled atmosphere ocean land sea ice model forward in time. This is a model that's a computer model that's based on physics equations. And then we make an ensemble prediction using that model. The red lines here show various empirical and statistical models made for predicting Arctic sea ice. And the idea here is basically you look at past observational data and you learn a relationship between certain input variables and September sea ice extent. Then you can apply that relationship to make a prediction of the future. And then there's also a few blue bars, which are these so-called heuristic methods. These are basically educated guesses. So they aren't as serious a methodology, I would say. Okay, and then the nice thing about this is we get feedback instantly on how we did. So here's the 2024 observed sea ice extent. You can see that there's a number of models that look pretty good. There's a number of models that underestimated the sea ice, and there's also a number that overestimated the sea ice. So there's a big spread across the various models, and a natural question here is whether we expect that Arctic sea ice should be predictable on these seasonal timescales or not. Regarding that question, there's been a whole ton of research done over the last 15 years or so, investigating the predictability sources for Arctic sea ice. And we believe that we have good reasons to think that Arctic sea ice should be predictable. So I'll quickly walk through a few of the key sources. The first is radiative forcing. So if we take a present day climate model and force it with observed concentrations of greenhouse gases, aerosols, and other forcing agents, we recover something that looks like the gray line here, which you can see captures the observed sea ice decline quite well. And so in order to get the decline, we need to put the radiative forcing in. That's very critical. But in order to capture these interannual fluctuations in sea ice, we need to put in other sources of predictability. So there's a number of predictability sources that originate in the sea ice itself. Namely, there's a lot of persistence in both sea ice extent and sea ice thickness anomalies. So these sea ice extent anomalies typically have an e-folding timescale of about 2 or 3 months, whereas the sea ice thickness anomalies tend to have longer autocorrelation timescales. A typical timescale would be up to a year or so. And they also tend to have larger autocorrelation spatial scales as well. So they're kind of larger scale features in space, which gives them an important impact on predictability for summer sea ice. The ice albedo feedback is a very well-known positive feedback that exists in the Arctic. And this is also a source of predictability in the sense that if you know what your anomaly is at the start of the melt season, this ice albedo feedback is self-reinforcing, and it will tend to amplify and self-reinforce the pre-existing anomaly, which will give you some predictability. Sea ice dynamical preconditioning is another important one. And the idea here is if you blow winds over the Arctic sea ice in the winter, and you can track that, that will imprint a pattern in the sea ice thickness field. And that will tell you about what the subsequent summer sea ice spatial pattern is going to look like the following September. There's also a lot of predictability coming from both the ocean and the atmosphere. So in particular, if you know the upper ocean heat content, that really helps you to predict, especially the sea ice extent in the fall and the winter months, and to a lesser extent, the spring months. And then the large scale circulation of the ocean is also very critical. And that's because the ocean transports heat northwards into the Arctic. So if you can predict the anomalies in ocean circulation, you can predict the anomalies in heat transport, and that tells you what the anomaly in melt is going to be, and that translates into a sea ice extent anomaly. And then also via its dynamic and thermodynamic coupling with the sea ice, if you can predict atmospheric modes of variability, such as, for example, the North Atlantic Oscillation, that gives you some associated sea ice predictability. So long story short, we think we have a lot of good reasons to think that this should be possible, but are we actually doing it? Are we actually achieving skillful predictions in our current real-time prediction systems? And regarding this question, there's a tension that exists in the sea ice prediction literature. So on one side, we have a series of studies that have looked at past predictions submitted to the September sea ice outlook. And a typical plot is shown here from one of those studies. So the dots here show the observations, the squares show the July median sea ice outlook prediction. And you can just see by eye that these predictions do not look very good. There's not much skill. And so most of these studies has a statement along the lines of, evaluation of these forecasts has revealed that regardless of method, forecasts struggle when the observed sea ice extent minima depart strongly from the linear trend. On the other hand, there's a whole host of studies that have looked at retrospective seasonal sea ice predictions in individual forecast systems. And these studies have found that their systems do have skill. So most of these papers has a sentence in it along the lines of, for most predicted months and lead times, trend-independent forecast skill exceeds that of an anomaly persistence forecast. In other words, there is skill in the system. So back in January 2021, the Sea Ice Outlook contributors got together for a forum, and we discussed a lot of issues in our community, but kind of the biggest burning issue was basically trying to understand where we were at as a community in terms of our current prediction skill. And so that motivated us to make a multi-model intercomparison of Arctic sea ice prediction skill. And what we did is we made a big retrospective data request to the community. And so we requested retrospective seasonal predictions of September monthly mean, Pan-Arctic sea ice extent, regional sea ice extent, local sea ice concentration, as well as initial conditions and ensemble data when applicable. We requested these data on the Sea Ice Outlook initialization dates of June 1, July 1, August 1, and September 1. And we requested this data over a minimum reforecast period of 2001 to 2020. And here's what we got back. So we received a really incredible response from all over the world. We got data back from 17 dynamical models, 17 statistical models, and 1 heuristic prediction. And these contributions spanned 11 countries across Europe, Asia, and North America. And in total, this represented nearly 3,000 independent predictions of September Pan-Arctic sea ice extent. Subsequently, all this data has been formatted into a common format, and all the data and code has been made publicly available in an online repository, which is listed here. And this represents the most comprehensive data set of multi-model sea ice predictions that's ever been assembled. Okay, so how do these predictions look? So we saw this plot on the left earlier. Here's the analogous plot for the retrospective predictions. And so the red line shows the multi-model median prediction. The black line shows the observations. And you can see that the predictions look pretty good. So in terms of skill metrics, the anomaly correlation coefficient is 0.94. The detrended anomaly correlation coefficient is 0.82. And so that metric is obtained by first linearly detrending both the observed and predicted time series before computing the correlation. And so we definitely have some skill here in these multi-model median predictions. So we can get a little bit more quantitative, and I'll just show this plot here. So first I'll talk about these. So the dashed line here shows the skill of a reference forecast, which is a simple linear trend climatology prediction. The ACC of that prediction is around 0.7. So what that's saying is that the linear trend can explain roughly half the variance we see in Pan-Arctic sea ice extent. The solid gray line shows the skill of a damped anomaly persistence forecast. This basically takes that linear trend prediction, then adds the observed anomaly at the time of initialization. And we can see that by adding that anomaly in, we get a strong boost in skill, especially from September 1st and August 1st. And then it converges back to this trend climatology skill at longer lead times. Okay, and now I'm going to add the black line, which is the multi-model median prediction. And what we see is that there's a high degree of skill in this multi-model median prediction, and it's beating damp persistence by a fairly large amount. And even for detrended ACC, which is a hard thing to predict because you're not including the trend at all in this prediction. We have skill of ACC values around 0.8 or above at all sea ice outlook lead times. So pretty encouraging results. Okay, so now I'm going to add the 17 dynamical models to this plot. First of all, you see that there's a lot of spread across the various models. But taken as a whole, the models are doing pretty well in the sense that they're beating damp persistence, especially from June 1st and July 1st. There's a lot of models that have skill above 0.6 for detrended ACC at all sea ice outlook lead times. So that's a fairly high level of skill, something you might consider a useful forecast, I would say. And then there's one model that kind of stands out, which is this yellow line, which is the ECMWF SEAS5 seasonal prediction system. And they're doing quite well, like nearly as well as the multi-model median prediction. Okay, now here's the 17 empirical statistical models that submitted predictions. Again, quite a bit of spread across the various systems. There are some models that have lower skill, but there is a large group of models that has quite a high degree of skill for predicting sea ice on the seasonal timescale. And again, there's a couple models that are sort of positive outliers on the high skill side. Great. Okay, so now my final slide here, I just wanted to quickly return to that tension I mentioned in the literature of this question of why are the retrospective predictions more skillful than the real-time sea ice outlook predictions? We think there's a lot of reasons going into this, but we think the most important reasons is a model selection bias. And so I'll explain what I mean by that here. So the blue line here shows the real-time predictions, the multi-model median submitted to the sea ice outlook in real time. The red line here shows the multi-model median for the retrospective seasonal predictions that we analyzed in our study. And what you see is that there's a large divergence between those two, between 2008 and 2015 or so, but then they fall more into line with each other in the more recent period. And if you look back at the submissions that were submitted to the Sea Ice Outlook, we had a lot of these so-called heuristic submissions over those first 7 years or so. We also did not have too many submissions from dynamical models. And that's because the dynamical models were just starting for the first time ever to forecast sea ice. They were figuring out how to do this, how to do data assimilation, how to initialize the models. Their predictions weren't very good. They weren't very sophisticated yet. And then, so over time, these models have gotten better. We've got a lot more submissions from these more skillful dynamical models over time. And meanwhile, we've had fewer of these heuristic predictions. So we think that's the main reason for this, this gap that exists in the literature, but there's also another number of other factors that might be contributing. Great. So to conclude now, we've created this new multi-model reforecast data set consisting of 35 different models. It's publicly available, so would love to have you take a look at it and download it. And we found that most of the models that were submitted to the intercomparison did have skill at the sea ice outlook lead times. So there are bright prospects for making useful forecasts of sea ice on these timescales. And if you want more details, I encourage you to scan this QR code and check out our article in BAMS. And I'd just like to say a huge thanks to all my co-authors. We worked with a massive team. Basically, the entire Sea Ice Outlook community contributed to this, and we really see this as a consensus study that we all kind of signed off on and all agree upon. And now to the more kind of serious point, funding. So the Sea Ice Outlook is currently seeking funding for the 2025 season and beyond. We thought we had some funding secured for the next few years, but unfortunately that funding looks like it's not going to come through after all. Tomorrow is June 1st. So we're going to start making our sea ice forecast for this September tomorrow. We don't currently have funding for the Sea Ice Outlook, but we are going to figure out a way to triage the situation and make it happen, even if we don't have funding. But we can't do that forever. So obtaining funding is really crucial to maintaining this really critical record of real-time predictions and avoiding a data gap, and also to sustaining this incredible community of international researchers that have all kind of coalesced around this scientific problem of predicting Arctic sea ice. So I will leave it there, and I'm happy to take any questions you have in the chat. So thanks a lot for your attention.
Thank you, Mitch. That was really encouraging. I'm just awed at the amount of progress that's taken place over the last few years. So bravo. We'll have time for a couple of questions. Let me see if this works. Margaret, how do I bring this question up? I'll just read it. It was one that came early on about the image, those glorious images you showed of sea ice. And the question was, are there ways to measure sea ice by satellite when it's cloudy, or are you taking clouds into consideration? How does that work?
Yeah, so the great thing about this, the data set that I showed at the start, the very first video, is one of our main ways to measure sea ice is via passive microwave observations. And the great thing about that is they're insensitive to clouds. So we can see microwave radiation signals through clouds, and that means we get an image of sea ice no matter what, whether we have cloudy conditions or not. And that's been really fundamental for our understanding. There are also a number of other sensors that are in the visible light spectrum. Those are sensitive to clouds. They're often also higher resolution, so they have a lot of value as well, but you just don't have a picture every single day. But yeah, the answer is yes. A lot of the sensors do see through clouds, which is extremely useful.
Great, and we'll have time for one more question at least. And this is about how will fish populations be affected by melting sea ice?
Yeah, this is a great question. I'm not a biologist, but I do know that the fish populations in some regions, for example, in the Bering Sea, there's certain fish species that follow the sea ice edge. So they like the water conditions that are basically, as the sea ice melts, it leaves behind a lens of cold, fresh water. the temperature range that certain species of fish like. So they tend to basically follow that sea ice edge around. And so for fisher people planning their missions for the coming weeks or whatever, they want to know where that sea ice edge is going to be, and they can figure out where the best spots to kind of launch their ships are from. And also the state of the sea ice cover is very important as well. Is the ice strong and consolidated such that if a storm comes through, is it going to stay in place? Or is the ice kind of all broken up into a bunch of little flows such that if a storm blows through, will the ice actually drift many, many kilometers really quickly and trap a ship potentially? So these are really important questions.
Okay, there are many more, but we ought to move on. And thanks again so much, Mitch. This was really enlightening, and very much appreciate your work.
Great, thanks a lot, Dave, and thanks for the questions today. Yeah,
you bet. All right, there's been a fair amount of chatter in the chat about calling your reps. And that is great, because in addition to just hearing some really great research talks, the purpose of this whole live stream is to generate some excitement for actually doing what for a lot of people is kind of not easy, which is to call your reps. But they have no choice. They want to hear from you, even if they don't necessarily want to hear your, exactly what or agree with your opinions. But they very, very much appreciate input, and so we have a real opportunity here to try to influence critical legislation by calling your representatives. And so. Not for the last time, I would like to cheerily exhort you to do that. Okay, our next speaker is Evan Oswald, contract research meteorologist at a government lab. Greetings, Evan. Thank you so much for spending part of your evening here and presenting your research to us. We're switching gears a little bit, and he will be discussing forecasting weather disasters.
Yeah. So my name is Dr. Evan Oswald, and I am a contractor at a federal contract agency called ERT. ERT stations scientists all throughout the federal government and NOAA, but I'm stationed at the Climate Prediction Center. And I was actually going to change gears a little bit today. I know that a lot of the talks are really just research talks. And I have a whole half the year where I do a lot of R&D. But for about half the year, it's more operations, because the Climate Prediction Center is actually an operational operational center within NOAA. And we put out products every day. And I was going to kind of talk a little bit more on that side. So move a little bit closer to my mic. Yeah, I could maybe do that. But I basically I'm going to kind of go through like a typical Friday during the summertime at the Climate Prediction Center, what I would kind of do. So my slides are going to be a little bit less graphy, but a little bit more, and we'll talk about some kind of good stuff like that. But anyway, we'll kind of dig into it. And let me tell you a little bit more about myself real quick, just to kind of start off. Again, Dr. Evan Oswald. I'm from the state of Michigan. That's where I live, Ann Arbor area, outside of Detroit. I have a PhD in atmospheric sciences. I graduated from the University of Michigan in 2013. My dissertation happens to line up perfectly with what I do today, and that was on extreme heat. My thesis was on heat islands, heat waves themselves, and the data sets that have the ability to represent extreme heat. One of the operational products in the Weather Service that you might use to kind of look at that is called threads. And those are the kind of examples of data sets. They have to be specifically curated a certain way to be able to represent the tails. prior to my work at the Climate Prediction Center, I worked at the Vermont State Climate Office and worked with, for example, the Vermont Health Office, where we would look at like the relationships between heat health, or actually specifically hospital visits with regards to the heat and the temperature in Vermont. So in other words, what are those thresholds in Vermont temperatures where we could start seeing that spike in hospitalizations with regards to heat? And then I went into some private forecasting at the sub-seasonal time scale for weather-dependent climates, our clients. As you can imagine, there's lots of businesses and people and agencies all across the private sector that care a lot about what the weather is going to look like in a week or two. And I was kind of trying to help them out. And then one day I noticed the Climate Prediction Center wanted someone to help forecast heat waves at that time scale. And I thought, oh my gosh, this is exactly what I want to do. And they hired me, the ERT did, and then staffed me there. And that was in 2017 when I started working there. And then personally, outside of work, I'm a father, I have 4 kids. I like to do fishing when I'm relaxing. And I'm also a community organizer. And I'm a DJ, I spin a little bit of music. And that's just kind of how I relax when I do stuff outside of this weather stuff. But let me get more into what I want to do on a typical Friday during the summer. You know, I might get into work about 9 in the morning. And, you know, I really check the National Weather Service's front page, that colorful, weird-looking front page that we call the Wawa map. Weather advisories, weather warnings, basically what kind of bad weather, what kind of socially disturbing weather is hitting the United States right now. And what I'm looking for is the orange colors and those magenta colors, and even the dark burnt orange colors, which I'll talk about a little bit. But the orange is your weather forecast offices issuing heat advisories. So when they're telling the public, hey, watch out, we got to change our behavior because it's going to be really hot. And they'll talk a little bit about it. The more purpley colors or magenta colors are the more extreme version of that. It's called excessive heat warnings. And those are just a little bit more stronger of a weather, an intensification of that weather, of that vibe. And when I go to it, because again, what we're trying to do at the Climate Prediction Center is we're trying to forecast the Wawa map, but we're trying to forecast it like 10 days in advance, 7 days, 14 days in advance, even outwards to like 28 days in advance. But that's what we're trying to, I said, at least at my particular job there is really support and developing tools so we can give a heads up that's just before the weather forecast offices will do this. Because as a weather forecaster, it would be nice to get a heads up of what's probably going to come up in the next day or so. So they can kind of get looking at it closer and start thinking about their thresholds, etc. Anyway, when I take a look at the Wawa map, you can click on those orange areas or those magenta areas, and you can get a weather forecast office's messaging about the weather that's coming up. They'll talk about some of that like IDSS stuff where it's like, hey, you know, stay inside or drink lots of water. Football programs should probably take a break today. But it will also give you some thresholds. It'll say those like, hey, it's going to be between 95 and 102 here in Idaho, which is really important to us. And that to me triggers, that's what we're looking for this time of year at that weather forecast office, that part of the country. And that helps us at the Climate Prediction Center understand, you know, what we're doing or what we're looking for, what we're trying to forecast, the kind of the triggers, you know. But I'll be honest with you, and this is an important point. The weather forecast offices around the country, they have guidelines of what they are looking for. They don't have to follow them. They do not follow them. They have a lot of leeway in their interpretation of what is dangerous for their community. For example, that first heat of the year, that first hot weather of the year, it's more sensitive. The community is way more sensitive to it than, you know, at the end of the heat season. And so it helps us as forecasters to be able to think about, you know, what the thinking process is of the weather forecast offices. And the weather forecast guest offices often will outline it with these nice graphics. So that's where I'll start my day off, you know. But then I start transitioning into more of the what is the nowcast. What is happening today? What's today going to look like? And I think one of the best ways to look at that is the National Weather Service's National Digital Forecast Database. That's what I have here on the screen here. And you can see what today's daily high is expected to be across the nation. You can zoom on in and get real nice forecasts there. It's a really great tool, and I would encourage anyone to use it when you're trying to look at spatial forecasts. Now, it doesn't just look at today. It also will scroll you out for the next 5-6 days, and often that's what I'll do. So I'll scroll out to 3 or 4 days from now. For example, this is where it's going to be hot in my area in a few days. But also, as we have made forecasts, in the future, first we're concerned, how's our forecast looking? And you'll start seeing, the weather a few days out. Now, I mentioned earlier, not just the orange and the maroon, but there's also like a burnt orange color. It's kind of this darker red, kind of looks like this, the infographic there where it says protect yourself from heat and weather, that color. But that color is kind of like a few days in the future, not just today, but a few days in the future. And those kind of colors can line up with a few days in the future. And that again helps us to see, okay, our forecasts lining up. And I'll show you some of our forecasts in a minute, but this is one of the Weather Service products that I look at. The next one that I'll kind of start transitioning into is at the Weather Prediction Center. The Weather Prediction Center is kind of like our sister forecast center. We're the Climate Prediction Center. We start taking over things after about 7 days. These cats focus in on day 3 through 7. So we're always trying to be kind of on the same page with them, but similarly, they, we're also curious to see how our forecasts are developing. And I'll be honest, it really is important to see how your forecasts are developing. For example, something I've noticed over the past couple of years is that a forecast about 7-10 days, a signal in the weather forecast that far out, tends to almost speed up a little bit as it comes closer to you. We actually call it forecast slippage is the terminology in the weather forecast community. And those are the kind of things that we really care about. So we hedge our bets, a little bit closer in time or further in time or this or that. So we go to the Weather Prediction Center. The Weather Prediction Center has the daily maximum temperatures and the daily minimum temperatures forecasted out for the next 3 to 7 days. And that really helps us out. One of the things that I'll transition into there is looking directly at the anomalies, the deviations from normal. And we see here on these figures that they provide, I think this is a day 7 for us, which is the day right before the beginning of our forecast period, which is of course important because you want to think about, hey, are we entering into our forecast period already with a heat advisory? When we're thinking about what will be on the maps, on the Wawa maps, between 8 and 14 days in the future, because that's a product that we have, and I'll talk a little bit more about that product. But on these maps, you can see there's anomalies, and there's a nice yellow shading. Now, it's true that in different parts of the country, we're looking for different numbers there on those maps. For example, we know as climatologists that certain parts of the countries have more variability, subseasonal variability in their temperatures. So, for example, a double-digit, 10-degree or more positive deviation from the norm is pretty important. That's kind of the, I would say, standard base across the country that we're looking for. But it's less important in places where there's more variability. For example, the continental United States. So, for example, the Great Basin. There's a little bit more variability there than there is in, let's say, San Francisco, which there's less variability because they have that marine influence. Or Florida. Florida, as you know, is covered by water, surrounded by water. So, the ability for them to change a lot of temperature is much less. So, for example, we might look at maybe a 5 degrees over there. 5 degrees could be very impactful over there. And so, not just maximum temperatures, but also minimum temperatures. Now, one of the things about extreme heat is that it's not just about how hot you got today, but it's about how can you cool down tonight. It's not just true for humans. It is definitely true for humans, but it's also true for things like substations for electrical distribution. You know, if a power outage happens in the area, that's a big deal for the ability for a community to withstand a heat event, or businesses to stay open, jails to cool their inmates down. It's also important for trains. When trains go through a town, if it's really hot, the metal heats up the tracks. And the tracks might get wavy. And if the tracks get wavy, the ability for those trains to kind of blow through there in their normal temperatures is definitely, they have to reduce their speeds to be able to go. So that's just another way that heat impacts society. And that's the kind of things that we think about a little bit as a heat forecaster. Now, the next thing I do there is I head on over to another tool over at the Weather Prediction Center, housed at the Weather Prediction Center, but I will say, I believe it was developed in the Western region. That's one of the rocks. This is the National Weather Service Heat Risk Index. Now, this heat risk product is actually a pretty complicated product, but it looks at absolute values. It looks at the relationship in health statistics from the CDC. It also looks at minimum temperatures and daytime high temperatures before and upcoming, and it figures out a color. Now, these colors range from like a green, which is like, it's going to be fine, down to a purpley color, which is like, it is not going to be fine. Now, personally, we're looking for reds. Reds will usually correspond with those weather forecast offices calling heat advisories, maybe even excessive heat warnings. And those purple colors for sure, definitely, big time. So anyway, the WPC houses this tool, and it will give you today out through day 7, which are, again, those 7 days prior to what we're forecasting at the Climate Prediction Center. And so it's really important to look at these because we can kind of see how these compare to those other anomalies I just showed you. And that helps us get a good feeling. Hey, should we call, put a shape on our map for our products so we can get those products real good? All right, so the next thing we'll do, or I'll personally do, is I'll head on over to what's called the U.S. Hazards Outlook, the days 3 through 7 that's housed and created at the Weather Prediction Center. And they have this product, there's a bunch of shapes on the map, and they have things, they forecast not just extreme heat, and that we don't just extreme heat. I just happen to be the support person over at the Climate Prediction Center for extreme heat. And so they have different colors and different shapes on there, as you can see on this map, which was made on Friday. But actually, this is the map from Thursday, because when we come in and start looking at these maps, they're always from the day before. And throughout the day, it'll update to today's preliminary map, but this was the day before. Anyway, you'll see an orange color on there on the bottom there in Texas, where they talk about the hazardous heat. That's a hazardous heat forecast for them. And then I'll click on that and I'll look at, it's these particular days that the WPC thinks is going to be, forecasting those wawas, those heat shapes on the wawas. So that's good knowledge for us. We're always thinking, yeah, our forecast for that did well, or maybe it didn't do well. Then I'll start shifting into our tools. Now, I happen to develop most of the tools and maintain most of the tools at our office, but I'm not the only one. There's a couple other important tools too. They're not in this talk, but because generally I don't have to maintain those tools. Now, it's one of my jobs at work to make sure that these tools work, and so I have to go and check them. And some of the problems that might arise with our tools is that there might be a data flow issue, upwind from us, the raw model output from the ECMWF, the GEFS, or even the CFS, or whatever these models that model output that we take in at our office. Now, I don't take them in personally, but there's more technically savvy people at my office that are tasked with making sure that these data come in. But anyway, they might not come in. A variable might not come in today. IT support at my office might have a problem, and some of these things might not run. One of our computers is down. So anyway, it's my job to make sure that this product appears here, and if it doesn't, I have to go into the code and find out what's wrong with it. If something's wrong, I'll talk to the other people in my office. But anyway, this tool that I developed right here in 2017, along with a guy named Augustin Vinciolis, who I don't think works at the CPC anymore, but he's still probably out there doing this kind of stuff. Anyway, they this product looks at whether in the future, what is the probability of having 2 days that are hot in the future in our forecast period, specifically 2 days over the 90th historical percentile. When I say historical percentile, we have this 30-year period at the CPC that we consider historical. 1991 through 2020, I believe, is that period. And so in percentile space, that's relative space, are we going to catch 2 consecutive days of 90th percentile, that top 10%? And then on these 3 columns here, on the left-hand side, we have the guess. That's the American model, UCMWF right in the middle there. And then we have a skill-weighted blend on the right-hand side. And you'll see that I have some radio buttons there clicked. You can do a raw one or a calibrated, because, when these models say something, they don't necessarily mean, you don't necessarily take it at face value. You have to think about in context historically. When it says 90% chance, what does that really mean historically? Well, it turns out it only means 50% historically. That's fine. Our forecasters really want to know that, because when they put on their map, when they make a forecast, they want to get, what that really means, that put it into real terms. So anyway, that product here is good, but I will I have some other products too. Let's see here on this tool. One of them is the start date. This helps the forecasters understand where in our forecast period is that extreme heat going to start. I have another product on that page that is more in the absolute space. So for example, during the forecast window, is it going to hit 100 degrees? Is it going to hit triple digits? Because as you all know, triple digits is kind of like it's kind of arbitrary, but it does happen to resonate a lot with the forecast offices. And this has part of the country, these darker reds on these maps are more certain that we're going to hit those triple digits. And we have different thresholds in the radio buttons, This is another one that is more in like standardized anomaly space. So do we have a 2-day, 1.5 standardized anomaly? As most people know, 1.5 standard deviations above the norm usually indicates kind of that wing, that maybe that top 10%, something like that. We have lots of different tools. Another tool that I developed that I check every day is I call it the change analysis. Basically, it looks at yesterday's this page compared to this day. Because of course, every day we make these forecasts for the Weather Service, and this product goes out, and it's just kind of like, hey, how has it changed since yesterday? Because we like to think about, that really helps the forecasters out. Like, okay, has it got a little bit hotter over here, a little bit cooler over there? And on this map, on these tools, we have today's on the top row, yesterday's on the bottom row, and that middle row shows reds and blues where it's gotten kind of warmer, the signal's gotten stronger, or the signal's gotten colder since yesterday. And we don't just look at just since yesterday, we look at since 3 days ago, maybe since last week. We got a bunch of these, and the forecasters this is an internal tool. Forecasters can hand it over here. This really helps the forecasters out to kind of get a good forecast. Now, about this time of the day on a Friday, I got to stop, and I'll head on over to the week 3-4 discussion. This is a different product at the Climate Prediction Center. We forecast not just next week, but we forecast week 3 and week 4 as a block. Now, not necessarily in the extreme heat sense, but more in the above normal, below normal in temperatures or precipitation. And what we do, we got about 7 or 8 of us that kind of gather on up. And one of the forecasters, the federal forecasters, not the contractors like me, I'm more support. They go through all the different climate signals that would matter in week 3-4. So for example, this is an MJO analysis. If y'all don't know, MJO, the Madden-Julian oscillation, is a circumglobal pattern or a circulation of a convective activity that goes around the globe. And when you have something like that goes around the globe, the tropics, it makes ripples up into the mid-latitudes. And those ripples have, 5, 6, 5, 10, 15 days later will impact our forecast periods. Now, admittedly, it's not a huge thing in the summer, but it's a big thing, in the winter. But we go through all kinds of different signals: El Niño, SST, soil moisture. We start getting into the dynamical models. that are provided to the government. So the CFS, ECMWF, the JMA, which is the Japanese model. We got the Canadian model. We got the GEFS, which is another American model. A lot of different things. We don't just look at, this is 500 millibar height anomalies, which is important, right? So, that's the thickness between, the surface and 500 millibar height. That's a big deal. But also the surface level stuff. Is it precipitating more than average? What's the probability of it? More than average. What's the anomalies? What's the calibrated? We can break it down by week 3, week 4. As you can imagine, week 3 has more skill. So our forecast team sometimes will weight a little, more heavily weight that week 3 than the week 4. Other times not, and they do all this consensus. Here's another tool that I really like. It's called the subsampling tool. Just to think about this. Now, as you can imagine, forward in time, earlier time leads, we have more certainty in our forecasts. And in those later times, we have less. So sometimes with all the ensemble members of a week 3-4 forecast, we only use the ones that are more what we think is going to happen in week 2. So we kind of crop down the grouping of ensemble members, and we just look at those. That's a subsampling tool. That's kind of a trick to kind of help us get better skill in week 3-4. We take all those things together, and then the forecast team draws a map. These kind of products go out to the public once a week on Fridays. Now, head on over. I'll go back into my tools, look at some other problems, some other streams tool. This is another tool at the CPC. Because look, this is an internal tool. There's a public-facing aspect of this tool. And there's different. This is a smart tool, so it's not just probabilities, but it's also absolutes. And then something interesting here. We were wondering on this past Friday, is it going to be hot in California in a couple weeks? Is it going to be hot enough? Because you can see here on these maps, this is day 9. So remember I said we do day 8 through 14, and we have some red colors there in California. So what we ended up doing was looking back in time in 2017. There was a heat wave. There was some weather forecast, of heat advisories back in 17. So we look at the actual temperatures during those times. Look, they didn't really cloud until about 105. But if we scroll back here, it looks like we're cracking 99, 100. So maybe we don't put it on the map. So that's how that's that logic. It's tough, but we use all those resources inside the Weather Service. It's important note there. The Weather Service is a giant thing with lots of products. We need all the products. Here at the CPC, we use products from other places, the rocks, all those other places. It's important. We lose any of those tools, our forecasts can go down, because we rely on all that stuff. And anyway,
Evan, we'll need to have time for a question or two very soon. So
okay,
I hate to interrupt, but
yeah, absolutely. But we'll look at more tools, and then here are some. We'll have another discussion for all of our daily products. We'll go through all the tools there as a group, and then we'll come up with our daily forecasts for the 6 to 10 day period, 8 to 14 day period, week 3-4 period. As I mentioned earlier, we have this product with those extremes, and then I'm working on an experimental week 3 forecast where I have a bunch of tools I look at, but I'm going to let you guys crack some questions at me. But anyway, thank you guys very much for listening to me. And I will say that in the next month or two, the funding that provides, pays my paycheck, we don't think it's getting renewed. We have no idea. So honestly, what's happening at the Weather Service may make me, go get out of here, So we're not really sure. A lot of uncertainty, but I appreciate you guys. And let me hear a question or two if you have time.
We'll go for that. Thanks so much. I learned an awful lot about products at the CPC that I haven't seen before. I appreciate that very much. Let me push one quick question on you, because I think you've addressed some of the questions that came up. And that has to do with how much you take humidity explicitly into account in creating extreme heat forecasts, or is it just implicit in the fact that humidity will affect the temperature?
No, that's a very good point. So in all different parts of the country, you have like a typical amount of dew point, typical amount of moisture for this time of year. And so that can drop. That can make in California, let's say Arizona, it can make things feel better, right? We call it dry heat. And over in Mississippi or Michigan, it can make it feel a lot warmer, a lot more oppressive. So, but the thought is it more moist than normal? Is it less moist than normal? And also, it even gets more crazy because, like, if it's really hot, you have that like more ability for the air to hold the moisture. But maybe is that deviation from the dew point temperature between the air temperature, is that amount more or less than usual for this, for this particular situation? So it goes on, it gets really hairy, and we end up having to think about it a whole bunch. That's kind of why they almost have to have some support people just thinking about that to kind of help those forecasters make the best forecasts. That way we can really get, good products in the weather forecast office's hands so that they can make good forecasts to protect society.
Great. That's great. And I'll start. Thank you very much for a really enlightening presentation. I really liked it. And as I say, I learned an awful lot. And your pitch about funding is, alas, quite important. And so I'll thank you one more time. And then we will move on and build on Evan's pitch about funding, just to remind everybody about, the underlying purpose of this whole live stream. So thanks very much, Evan. We're moving on to hour 84, and we are here both to learn about some very cool science, as we've done for the past hour. I'll be the host for one more hour. My name is Dave Gutzler, and I am here right now to give you all a pitch to contact your reps about funding for weather and climate science. Here is the link that you can follow. There are scripts there. I mean, things are set up to make this as easy as possible for a lot of people that often aren't real comfortable making these sorts of calls, but it's really important right now. So we are trying to maintain support for a weather and climate science and forecasting enterprise that is the envy of the world, and that has been built using really hard work by a whole lot of people for many years. And we want to maintain it and keep the service to the American public going by maintaining funding for our weather and climate enterprise at all levels. And so we just heard a really wonderful presentation about products associated with forecasting that are really intended to save lives, in terms of forecasting extremes. And it is critical for us to keep that going. So there is the link. Please follow it and do what you can to help us keep this enterprise going. All right, we're going to move on and switch gears a bit. Our next speaker is Peyton Cavnar, an early career climate scientist who is going to tell us about paleoclimates and the use of cosmogenic nuclides, as you can see on the title slide there, to study past climates and how they inform what's going on right now. So welcome. Thank you for being here, Peyton. Take it away.
Hi, everyone. I just want to make sure everyone can hear me okay. Do I sound good? All right, perfect. So thank you so much for joining us this evening. Thank you, Dave. Like you said, I'm an early career climate scientist. So I recently finished my master's studies at the University of Vermont. And for 2 years, I was a member of the UVM NSF Community Cosmogenic Laboratory. So today I'm going to be talking to you about this tool that we can use to study past climates and why that's actually still relevant to current climates and us making more informed modern climate decisions. So jumping right in, just in general, the field of paleoclimatology, what is it and how can it help us when we look forward to the future? So hopefully you guys have heard some more about meteorology and climatology. The last talk was great. So with paleoclimatology, we are studying the climate of the past, but by past, I don't mean yesterday or last week or even 10 years ago. I mean ancient climates that predate the human ability to study and document climate systems with instrumentation. So we are here right now. And our Earth is always changing, right? It sometimes goes through cyclical changes, but sometimes these changes are so slow that we aren't able to observe them and perceive them based on the scale of a human lifespan or even a generational lifespan. So paleoclimatologists, we like to sort time into different units. So right now we are in the Holocene. Maybe if you ask some other climatologists, they'd say that we're in the Anthropocene or the Anthropocene. That would technically be correct too. But humans, we are just one blip in the Earth in regards to the geologic timescale of the Earth's lifespan. Most of my work concerns the Pleistocene epoch, our most recent epoch before the Holocene. And the Pleistocene is well known for its glaciations. So basically, the Earth has gone through a lot of climate fluctuations before we even arrived. And a lot of these cold periods were favorable for the cryosphere to grow itself. So when I talk about the cryosphere, I just mean all of the places on Earth that are covered by ice and snow, but not just polar regions, anywhere that could be a lake that's covered by ice, things like that. And so when you think about the last ice age, that's how we colloquially refer to it, you're most of the time probably thinking about the last glacial maximum that happened from 20 to 25,000 years ago. Now, when the last glacial maximum was happening, most of North America was covered by miles of ice. So here in this figure right here, this is my love and academic focus, the Laurentide ice sheet. Now, it was actually fused to the Greenland ice sheet, which we still have today. It's one of our 2 remaining ice sheets, and the smaller Cordilleran ice sheet, which covered most of the Pacific Northwest and some of Alaska. So this was at its greatest extent in the last glacial maximum. And so here, like I said, the Earth has gone through cyclical changes in the past. H stands for Holocene. This is where we are now. We are currently in a warm period or an interglacial. And then all of these dips in the graph represent past glacial periods that the Earth has gone through. And so what are cosmogenic nuclides and how do they even pertain to the fields of climatology and paleoclimatology? Why are they important? And so cosmogenic nuclides are basically just really rare forms of isotopes that are created when radiation from space, it's super cool, comes down and interacts with atoms that we already have in our atmosphere. And through these reactions, we call them spallation reactions, we get different types of cosmogenic nuclides, but what I study, they're specifically in situ or created in place in the surface of the Earth, specifically aluminum-26 and beryllium-10. So these are only 2 of many. So this is what you see going on at the bottom of the screen right here. And these nuclides are actually stored in minerals like quartz. So in this image, you have almost clean or pure quartz. And this is where these spallation reactions are happening. Most of the time, paleoclimatologists, we like to study cosmogenic nuclides in pairs. So we always want to study nuclides that have different half-lives. together. And this is because this gives us an informative ratio of what's going on, and it kind of adds another dimension to our data. So for instance, beryllium-10, it has a half-life of about 1.36 million years. So if I have a set amount of beryllium-10, it's going to take 1.36 million years for that to naturally decay to half of its original quantity. But aluminum-26, on the other hand, it has a shorter half-life, so it's only going to take 730,000 years for it to decay to half of its natural quantity. So that's how we get this ratio created between the two. So now, if we're thinking back to ice sheets and glaciers, and ice sheets are just glaciers that are huge, that can span continents, that can be miles thick. Ice sheets and glaciers are always moving, even if it's very slowly, and they're constantly eroding the landscape that they are occupying. Sometimes the ice can move fast if you have sort of an ice stream situation going on. But regardless, it's always going to be spitting out this till, which is just a conglomeration of dirt, sand, sediment, cobbles, boulders, and depositing it at the terminus of the ice sheet. So that's what we have going on right here. Here's the terminus or the end of the ice sheet, and you have this deposition of sediment and a land feature that we call a moraine. And so if you have an ice sheet that used to be this big, which is this line right here, it's spitting out sediment and it's creating this terminal moraine. But over time, maybe the Earth starts to warm, maybe we start to move into an interglacial, that ice sheet's going to recede. And so it's going to leave a series of smaller moraines that indicate where the ice sheet edge used to be. But there's a problem here because ice sheets don't only just move in one direction. Now, I know a lot of the time in the media, we're talking about warming, we're talking about melting that's going on in various portions of the world. And that is certainly true. But as a paleoclimatologist, when I think about long-term timescales and all of the different glacial periods that the Earth went through in the Pleistocene, there's a lot of growth and retraction going on. And so the Laurentide ice sheet, when it grew to its greatest extent during the last glacial maximum, it actually mowed down all of the old deglacial features that it created during past glaciations. This is difficult for us because it basically just erased all of the past evidence it created on the landscape that we could have used to study its behavior before the last glacial maximum. But we have tools. We have tools to help us understand this. And so basically, if you go out and you measure aluminum-26 and beryllium-10 in different types of sediments or in different types of rocks, it doesn't matter. The substance just needs to be rich in quartz because that's what hosts the nuclides itself. The ratios will tell you about what was going on in that landscape in the past. And so on the left here, we have a deglacial feature. This is called an esker. And so if you have an ice sheet and you have a river or an inglacial stream within the ice sheet, it's going to be rapidly transporting sediment out to the ice sheet terminus. But what happens when that ice sheet starts to rapidly melt? It's just going to drop all of that sediment in the position where the river used to be and create this kind of like snake-like depositional feature on the landscape. This is good for us when we work in the field because it's typically easy to identify with the naked eye. So here's this picture taken by yours truly in the northeastern part of Canada, close to where the Quebec-Labrador ice dome used to be. So this is a deglacial feature. We know that this sediment was at some point buried underneath the Laurentide ice sheet for tens of thousands of years. So when we sample it, we expect it to have a depressed ratio. So basically, when you have this block of ice that's miles thick, that covers a section of land for tens of thousands of years, it's going to actively inhibit the production of cosmogenic nuclides because the landscape needs that exposure to radiation from space in order for those concentrations of aluminum-26 and beryllium-10 to build up. So when you have this block of ice that just sits there, all of the nuclides that have accumulated in this till or in these rocks, they're going to naturally start to decay And that's why the ratio between the two is going to be depressed or get lower. So depending on where we sample, the ratio between those two nuclides can tell us how long a portion of the land was covered by ice, and therefore how long that portion of the land stayed glaciated during a warm period. So because of this, Cosmo can help us look into the past. Obviously, the Laurentide ice sheet is no longer covering most of Canada. But when it did exist, there were three main powerhouses or ice distribution centers that were doing most of the work. So we had the Keewatin Dome, which is over here, the Fox-Baffin Dome really far to the north, and then of course the Quebec-Labrador Ice Dome, which is where most of my work focused. So there's a lot of questions in the Arctic paleoclimate community right now concerning how long these ice domes were able to sustain themselves as we moved into interglacials and then the final warming period into the Holocene. And so when we learn about the past, it can help us make and check assumptions on how paleo ice behaved. And this is cool because if you look at these two images, these are from a paper that tried to model how this portion of the ice sheet behaved before it deglaciated for the final time, so before it completely melted away. Now, as you can see on this part A, this part near the ice dome has a very, very low, almost zero sliding distance. So this ice was not moving a lot. It was not very erosive. It was very stable. Likewise, it had a very low sliding velocity. But what's cool is that if you look at modern ice sheet and glacier models, we're using the same parameters to understand what's going on in real time. So these models are actually from two glaciers taken from the Greenland ice sheet, one of our two remaining ice sheets, and then they're observing the same variables. You have observed velocity and simulated velocity. So because these ice sheets are still around, we can go and do our best to observe them in real time and see how they're melting. But we can also use models that are spun up using paleo data to check how accurate our observations are. And so in general, what problems are we trying to solve? Cosmo is a very niche field. Paleoclimate itself is a very niche field, but there is a lot of untapped potential using paleoclimatology to help us make more informed, smart climate decisions as the cryosphere is starting to change right now. So the major thing is that we're trying to figure out more accurately how climate sensitive ice sheets and glaciers are. There's a lot of variables that come into play with this that we think we've underestimated the importance of. So there are a lot of feedback loops involving the cryosphere and a lot of coupled modeling that needs to be done. So how does the atmosphere interact with the ice sheet? How does albedo or the reflectivity of the ice sheet or any pollution or surfaces that have landed on the ice sheet, how does that affect how it melts or how it accumulates mass? Feedback loops within the ice sheet. Okay, guys, ice sheets are hard to study. It's hard to send a camera down there in very, very cold conditions. It's hard to send a person down there in the field to observe in real time. So what's going on underneath the hood per se, there's still a lot of mystery there. How sediment, how ice is transported. And then specifically, I was trying to look at how resilient that portion of the Laurentide ice sheet was to Holocene warming, what regions deglaciated last and when, because this is going to tell us about the GRIS, the Greenland ice sheet, and the Antarctic ice sheet, and maybe give us more insight onto what portions of those ice sheets are more vulnerable to modern climate perturbations. And this is all possible because of this lovely principle that we have in paleoclimatology called uniformitarianism. So this long fancy word, it basically just means that all of the laws of science, physics, thermodynamics that govern how ice sheets and glaciers move now, those are the same laws that applied in the past to paleo ice sheets. So the way that ice sheets move, the physics involved in that, and therefore the variables and parameters that we have to use when we make our models, those are going to be the same regardless if our branch of time is past, present, or future. And this is very, very important because modern ice sheets are in trouble. So the Antarctic ice sheet loses about 150 billion tons of mass per year, and the Greenland ice sheet loses about 270 billion tons of mass per year. Now, you may be thinking, okay, I don't live in an Arctic climate. What does this have to do with me? So I live in Texas, obviously not an Arctic climate zone at all. But the cryosphere is very important because it kind of gives us a window into what's going on with the overall health and well-being of the climate system. So maybe you've heard the term Arctic amplification. Basically, that's just saying that polar regions are more sensitive to climate change than other regions. So if we have some sort of climate anomaly or a perturbation and we can't observe the effect of it in other ecosystems, chances are if we look to the Arctic, we'll be able to see some effect and study that effect there. But also, just like in the past, when the Laurentide ice sheet covered the span of an entire continent, that is a major, major impact on other climate systems. So these ice sheets, they affect how the atmosphere circulates, and they, of course, affect sea level. But that's going to affect globally how our ocean circulates, how our ocean transports nutrients. That in turn impacts ocean ecosystems. So if you think about fish and resources that coastal communities rely on for food, then that's going to impact us terrestrially. So this is something that we need to understand. And I like to compare it to legal cases. When you're faced with a legal case and you don't necessarily know the answer, a lot of the time people refer to the past precedent, the case that was most similar to it in the past, to make an informed decision. So this is why we need paleoclimatology, even though it is long-term timescales before humans were on the earth, because we need to understand how our world works without us being a climate forcer in order to understand fully the systems that are happening now and that could possibly negatively impact us in the future. And so I just want to close by saying that this would not be possible without modeling powerhouses like NOAA, like NASA, like other university labs, and also by NSF, the research that it funds, and different Arctic data centers. So the Arctic Data Center itself is funded by NSF. And so if we don't have these repositories where researchers like me can make our data public, if we don't have funding for people like me to go out into the field and dig and other climatologists, then this work won't be done. And it's just one small piece of the picture, but regardless, it's important because we can't address a problem unless we understand it. So with that, those are some references, but I ended a little early. I'm happy to answer any questions. Thank you, everyone.
Thank you very much. Awesome graphics and awesome settings, really interesting. We do have some questions that we'd be happy to put to you. Why don't we start with sort of a science question, and that would be, why is the ice not covering all of Alaska? And were the sheets that thick, as the thickness you mentioned, everywhere, or just in the central U.S. and interior of Canada?
Okay, I love that question. I can go back to where we looked at Alaska. Okay, here we go. So the Alaskan landscape, or just the western portion of the continent, it's very different topographically than the eastern portion of the continent. And so when it comes to why wasn't an area glaciated, it's not just about how far north it is and how cold it is. It also depends on the terrain. If it's very mountainous, if there's a lot of changes in topography, what kind of vegetation occurs there. And also you'll notice that the portions of Alaska that were glaciated, they are close to the ocean, they're marine terminating. So we definitely have some cold ocean circulation that's helping sustain that ice. But I do want to stress that this is just a snapshot of one of the glaciations that occurred during the Pleistocene. And so this is just looking at one moment in time, and it's not a good representation of an average over tens of thousands of years. And then in terms of, is the ice thick uniformly across the continent? No, it is not, but that's a great question. So the ice would have been thickest around the ice domes. So the Keewatin Dome, the Fox-Baffin Dome, and the Labrador Dome, that's where we're going to have miles upon miles of ice, because those places are favorable for ice accumulation based on elevation, based on atmospheric circulation patterns, where it's going to get a lot of precipitation. Because that's how ice sheets accumulate mass. They just get snow on them, they get ice, it freezes, it has to stay frozen for a certain amount of time or else melts away, then you have net zero. And then slowly, if you think about an ice sheet like a pancake, that's how it's going to distribute mass to other portions of the ice sheet. So one of my colleagues like to say that if you think about pouring pancake batter onto a pan, it's going to kind of glob up in the middle first, but then slowly radially spread outward until it's mostly even. So the physics of an ice sheet are kind of similar.
Okay, I love your enthusiasm. It's really great. And so we'll ask one more question, which is not really a science question, but will speak to a lot of us that are, science nerds. But and that is, when did you get to visit your first glacier or ice sheet in person? Did you have a moment of awe when you first saw it?
Oh, my first glacier in person was actually the Exit Glacier in Alaska, which was pictured in one of the slides. And I only got to visit my first glacier in my first year of grad school. So it's kind of funny because I'm studying paleo ice sheets, and I'm studying something that I've never seen before, but I know that it's existed in the past. But when I got to see it for the first time, I definitely did have a sense of awe, but also it was a sense of urgency and a little bit of sadness too, because the Exit Glacier, it's known for being a great indicator of climate change because it recedes so visibly. You're able to track it with your eye. If I went back this year, I would be able to tell the difference between when I saw it years ago. And so I think it just really lit a fire in me to make sure that my work stays relevant to modern climate applications. I think maybe the worst thing about paleoclimate, even though it's so cool and so interesting, is that sometimes you can get too lost in the equations and forget to apply it to what's actually happening around you now.
Oh, I think the equations are very cool as well. But I hope you have a chance to visit a lot of these places, many more times in the future. I know my wife is a geologist who has worked in the Alps for decades until she retired. And, just having tagged along with her, has been astounding for me over my professional lifetime, just seeing how much the glaciers there have retreated. And I saw those glaciers, and then the next time I'd go back a few years later, you could see how much smaller they were. It's daunting to see that. And so, well, best of luck for you as you move forward. This was really great. Thanks very much.
Yeah, thank you, everyone. I hope you have a good night, and thank you for putting on this event. Bye, everyone.
Bye. Okay, we're moving right along. We're halfway through hour 84 of this live stream, kind of getting into the home stretch and moving into the wee hours of the night, certainly back east. And I will, before we move on, it is my task and privilege to bug you again, to call your representatives and make sure that they hear that there is widespread and vocal support for the kind of research that we've been talking about on this live stream. We really need to act now to maintain the research community and the operational forecasting community. We've heard talks about both those topics. We really want to keep this up, and we will need government support to do it. The payoff is huge, and so let me urge you again to, there's the link, and let's make lots of phone calls and see if we can keep things moving. We're hosting duties to Karen Schell, who I think is here. And I would like to thank the live stream organizers and our audience. It has been a great pleasure for me to do this for a couple hours. So Karen, welcome, and carry on.
All right, thank you, Dave. So hi, everyone, I'm Karen Schell, and I'm going to be your host for the next 2 hours. So we are up on hour 85 now, with 15 more hours to go. We have, as usual, a great hour of weather and climate coming up. It sounds like it's going to be sort of weird in this next hour. But before we get started, I want to remind you of why we're all here. So you're here because you know how important weather and climate forecasts are to protect your lives and livelihoods. Luckily, the United States has long been a world leader in weather and climate prediction. We developed the first computerized weather forecasts, and we made the first computer models of the climate impacts of carbon pollution. To make these forecasts, we've had to have all of this amazing observational data from satellites and ships and balloons and floats and planes. And the fact that all of these come together to make our weather forecasts and climate projections is really amazing. I'm not going to call it a miracle this time because your previous host, Dave, as he pointed out, maybe not exactly a miracle. There are thousands of scientists and like the ones you've been hearing the past few days, as well as engineers and technicians who all have come together to create this amazing weather and climate forecasting system. So I'm going to call this a true scientific wonder instead. And so we are so glad that we could share this wonder with you. This wonder was made possible by decades of investment by you, the American public. But in recent weeks, funding cuts have put this miracle at risk. And in fact, we know that future funding cuts are looking like they will be continuing in that direction. Weather stations are so short-staffed that we are losing our observational coverage, which is already hurting our forecasts, as you've seen in some of the previous talks. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for a basic understanding of the weather and climate is disappearing. And we're losing a generation of scientists. You've seen a whole bunch of students and postdocs and early career scientists who have been supported by fellowships and scholarships and grants and summer programs to get the training and education they need in order to become scientists. And by not having these funds available, there's going to be a whole generation of scientists who lose out on these opportunities. It doesn't have to be this way. If you like what you see here, then we ask you to please use the link on your screen right now to contact your representatives and tell them to save our forecast, to keep the lights on for weather and climate science so we can keep this miracle alive. And please spread the word to join this live stream. Either way, we hope you learned something new about weather and climate, and please ask questions in the chat because we love to talk about our science. So our first speaker will be Nick Lutsko, who is a professor at Scripps, UCSD. And before he gets started, just a reminder that the views of the speakers are all their own and not the institutions where they work. So take it away. Tell us about the weird weather.
Cool. Thanks, Karen. Hi, everyone. Is my slide showing up okay?
Yes.
And can you see my cursor or not?
I do not see it.
Okay, no problem. Okay, I can advance. Yeah, cool. So I guess, like a lot of the speakers, I want to start just by introducing myself a little bit. So I'm an assistant professor at Scripps / UCSD, working on climate dynamics. But I'm originally from Belgium. which, despite my accent, is known for, when you're from Belgium, there's like a small number of things which people know you for. So people know about Belgian chocolates, and they know about Belgian beer, and they might know about illegal diamonds, which we're also a big center for. And also, it's the center of the European Parliament. So this is the EU parliamentary building, and that's what brought my family to Belgium, was working for the EU. But when I was growing up, one other thing that I associated with Belgium was bad weather. We only get like it felt like we only got a few days a year of sunshine, and the rest of the week, the rest of the year, we would just get kind of gray, drizzly weather all the time. And kind of ironically, now I'm in Southern California, where it doesn't feel like we have seasons either. But the weather is a lot nicer. But I moved to the US for grad school, and I immediately noticed a big change in the weather just day to day, where I was on the East Coast, but it still felt like the seasonal cycle was a lot larger, and it would get much warmer in the summer and much colder in the winter. As you start to like explore the US a little bit, I realized that North American weather is much more variable, especially in the center of the continent. So what I'm showing here on the left is some data from a weather station maintained by NOAA at the Denver International Airport. And this is from 2022 when I grabbed the figure. But if you look in the top left at the kind of solid blue line there, you can see that in January and February, the temperatures were jumping by, like maybe 40 or 50 degrees Fahrenheit in just the span of a few days. And then on the right is a news article from a newspaper in Colorado, which mentioned that in winter of that year, Denver actually saw a record for the largest temperature drop in an hour that had ever been recorded. Again, this isn't Fahrenheit, unfortunately, but so in 1 hour, temperature dropped 57 degrees in Denver, so it would be about 20 degrees Celsius. And I think in a day and a half, in total, there was about a 40 degrees Celsius temperature swing in Denver. So this has always struck me as someone, or it struck me especially when I was on the East Coast, and going to conferences and visiting places in the Central North America, was just how variable the temperature was. And so that got me interested in trying to explain what was going on. And this project really started in 2019 when I was living in Boston. And I don't know, it depends how good your US geography is, but so Boston is on the upper East Coast here. And so on January 21st, it was super cold. So these are temperature anomalies relative to the average weather in January. And so it was about 20 degrees below average on January 21st. And I remember it was a snow day and no one went into work that day. And then 3 days later, you can see now temperatures were something like 15 or 20 degrees above average. And I biked to work in a t-shirt. And when I was growing up in Belgium, we would get a snow day if there was like an inch of snow on the ground. And here we were going from having like a foot of snow on the ground one day to a t-shirt weather a few days later. So I thought that was wild. And so I went and, before I talk further about that, I want to make a point here, which is that I think there's an interesting connection between these extreme temperature swings and the perception that we have of climate change, where every year in winter, you see kind of a host of articles about winter storms and the polar vortex and these extreme winter weather that we always experience. And yet somehow that's sort of interacting in a kind of complicated way, in a way that's not obvious, with a long-term warming trend. And there's a quote by James Hansen, one of the legends in climate science, where he said, how can a person discern long-term climate change given the notorious variability of local weather and climate from day to day and year to year? And so I think kind of clarifying and better understanding the relationship between extreme weather, particularly extreme cold weather, and long-term warming trends is kind of important for communicating. I see Karen's dog just came into the picture. Or is that a cat? It's a cat. For communicating and helping prepare for long-term climate change. So back to the story is I grabbed some observations and I just made some maps of temperature variance in winter, Northern Hemisphere winter. And so that's what I'm showing here. And panel A is the variance of December, January, February daily temperatures. This is at peak near the surface from 1979 to 2012, which is just the data that I had at hand. And you can see that there's this bullseye over North America, over central North America, east of the Rockies. In panel B, I'm showing the same thing, but I'm showing what's called synoptic temperatures, which means I've just filtered to timescales of about 3 to 15 days, which we kind of think of as setting the typical timescales of weather events. And this was just to try to understand, whether the timescales of these phenomena. And you can see that again, there's this huge bullseye over North America. And finally, in panel C here, I'm just taking a cross section across 50 degrees north and showing the temperature variance. And you can see that it's maybe twice as high over North America at 50 degrees as it is over Eurasia. So I was pretty surprised when I made these maps. When you think of like extreme winter weather, at least for me, I tend to think of like Eastern Siberia or Central Eurasia or something. And while it might be very cold there, the temperatures don't really vary that much during a typical winter. Whereas, one of the things that makes winters so hard in North America is these massive temperature swings, which people have to learn to live with. And so I want to try to explain why North American weather temperature variability is so high in winter. And so this kind of confirmed that this intuition I had that the weather is really weird over North America in winter. And so what I want to try to think through together with you guys is a kind of hypothesis for why this would be the case. And it has 3 pieces to it. The first is that temperature variability is high where temperature gradients are high. The second piece of the hypothesis is that large-scale orography affects temperature gradients and hence temperature variability. And then finally, that the relative locations of the Rockies and the Asian mountains create regional differences in temperature variability. So I want to walk through these steps a little more carefully now. So the intuition for the connection between temperature variability and temperature gradients, I've tried to kind of sketch here, where the colors denote temperatures and the arrows are kind of like winds. So imagine a case where we have like relative kind of mildly warm weather to the south and mildly cool weather to the north, and we have winds kind of going between these, mixing up these two air masses. We might expect lower temperature variability than a case where we have really cold temperatures next to really warm temperatures. And then, just a subtle change in the winds can bring really warm temperatures far north or really cold temperatures far south. And so this also kind of gives us a way into the problem where, like, if we're trying to explain why temperature variance is so high over North America, what we really have to do is explain why temperature gradients are so high. The second piece of the argument is on this role of orography. So this is a very crude sketch, but it's trying to show kind of the stream flow looking down kind of in a bird's eye view on a mountain. And if you imagine that the flow is going around the mountain, then what we'd expect is like reduced temperature variance and reduced temperature gradients upstream of the mountains, where the air is kind of being pulled apart, and then enhanced variance downstream of the mountain when the air is reconnecting and pushing back together. The caveat to this is that the flow has to go around the topography or the orography, not up and over it. So if you have a little bump, the air can easily flow up and over it. But if the mountains are too steep, then the winds will have to go around the topography. And it turns out that this is what happens for the major northern hemisphere mountain ranges. So the Asian mountains, the Tibetan Plateau and the Himalayas, and also the Mongolian mountains, and then the Rockies. Okay, and so the last piece of this is the relative locations of the Rockies and the Asian mountains. And to talk about this, I'm going to go back to this plot. The top row is showing the same thing as what I showed before. And then the bottom row, I'm now showing the north-south temperature gradient squared in panel C, and the east-west temperature gradient squared in panel D. It turns out that temperature variability is related to the square temperature gradients when you do out the math. But what you can see is downstream of, if you focus maybe on panel C where it's most clear, downstream of the major mountain ranges in the northern hemisphere, you see enhanced temperature variance. So you see these darker shading of red downstream of the Asian topography and here over most of North America. So at these latitudes, the winds are blowing from west to east here. Okay, so this would be downstream. So my sort of hypothesis is that this high temperature variability over North America is due to these large temperature gradients, which are being set up by this orography. You might wonder what's going on over the Pacific here. So we have large temperature gradients here out over Japan and in the Northwest Pacific. But because the ocean has a high heat capacity, larger heat capacity than land, we would expect a lower variability over the oceans than over land surfaces. This is also one reason why the weather is so stable over Southern California here. So what I want to do now is try to understand the link between these mountain ranges and the temperature gradients. Like it looks plausible, but there could be other things setting up these temperature gradients. And so the way that we like to approach these problems in climate science is to use kind of a set of climate models in which we can play games flattening mountains and raising them to test this hypothesis. And so the first set of tests I did was using idealized climate models. So on the left here, they're from a simulation with a dry climate model, and on the right with a moist climate model. So the dry climate model was kind of the simplest model I could find that would maybe show this effect. And then I used one which has water vapor included in it in case somehow that would affect the results. And it turned out to work really beautifully. So the shading here, the kind of gray shading is where the mountains are that I put in. So these are simulations with kind of a perfectly spherical Earth in which I add kind of a bump at the latitude of the maximum winds. And you can see that downstream of these mountain ranges, we indeed have enhanced temperature variance. So that you can see that with this darker shading in red downstream of the mountain ranges. And the top row, I'm also showing the winds. And this effect is even larger when we add atmospheric water vapor, because water vapor contributes to temperature variance and kind of reinforces this pattern. And then on the bottom row, I'm showing the squared temperature gradients again, which again are enhanced downstream of the mountain ranges, exactly like we expected. So in these idealized climate models, everything seemed to work exactly as we hoped. So then we wanted to test it in a more realistic setting. And so we used a comprehensive climate model. This is a model developed at a NOAA lab, the Geophysical Fluid Dynamics Laboratory, which is also where I did my PhD. And what was really nice about this model is it was kind of specifically set up to model extreme weather events. So it's really like the perfect model for us to use in this study. And we ran 3 simulations. We ran a control simulation in which we tried to reproduce the temperature variability that we see today. Then we did a case where we flattened Tibet, and we did another case where we flattened the Rockies. For some reason, it was easiest to flatten them down to 300 meters rather than 0. People sometimes ask me whether we ran a case in which we flattened both Tibet and the Rockies. And we did, but the climate of this system of this case got really weird because we kind of got these superstorms, which took over the climate of the northern hemisphere And it really wasn't any comparable at all to what we see today on Earth. Okay, so now here I'm showing again the temperature variance. The top left panel is the observations, so we've seen this before. And then the top right panel is the control simulation that we did. And I think it does a really beautiful job of capturing the pattern of winter temperature variance. Both like the kind of broad brush features that we see, this bullseye over North America, but also kind of like quite a high degree of granularity. So for example, there's this bit of enhanced temperature variability on the south coast of Australia. If you look carefully, there's some structure over the North Pacific that the model is also capturing. So we were really happy with this. And again, this gave us confidence that we could use this model to check this question, to investigate this question. So in the lower panel, I'm showing the results of the flattening the mountain ranges. So on the left is what happens when we flatten Tibet. And just like we expected, we saw enhanced temperature variance over Eurasia. So if you compare, say, north of India here in the No Tibet simulation versus the control simulation, we saw an increase of about 50% in the temperature variance. Surprisingly, though, we also saw temperature variance increase over North America. And that was because the Tibetan mountains interfere with storms that end up propagating to North America. So they actually weaken the storms that we experience. In the lower right here is the simulation where we flatten the Rockies. And in this simulation, we see reduced temperature variance over North America, which is exactly, again, what we expected. So if we flatten the mountain ranges, we have weaker temperature gradients, and we have less temperature variance. And so again, we saw a reduction, depending on how exactly you want to calculate it, of somewhere between 30 and 50% of the temperature variance. This is another cross-section across 50 degrees north. So let's see, the blue curve is the control simulation. The red curve is the No Tibet simulation, and the gray curve is the No Rocky simulation. So if you look at the No Tibet simulation, we see this increase in temperature variance upstream of the Tibetan mountain ranges, but we also see an increase in temperature variance over North America. In the No Rocky simulation, we see a decrease in temperature variance over North America, and we also see an increase in temperature variance here over the northeast Pacific, which again is what we would expect, right? So that we expect mountain ranges to reduce temperature gradients upstream and also reduce temperature variance there. So when we flatten the Rockies, we see enhanced temperature variance over the Northeast Pacific. And so this is going to be my final slide. I just want to give two takeaways from this talk, which are that first, North America has the highest temperature variance on Earth in wintertime. And second of all, that temperature variance or temperature variability is enhanced downstream of large mountain ranges. And depending on how exactly you want to draw your boxes, like what you mean by North America and what you mean by Eurasia, this explains something like 30 to 50% of the difference in temperature variability between the two continents. We've since followed up on this work, and we found that most of the rest of the difference comes actually from stationary waves, which the two continents excite, and they interfere with each other in kind of complicated ways that further strengthen temperature gradients over North America. But this is all the time I think I have, all the material I think I have time for today. So thanks again for listening and tuning in. And yeah, hopefully there's some time for some questions.
Yeah, great. Thanks. That you did say it was weird weather, but not really weird weather. So I guess you couldn't use the model with both mountain ranges flattened. So we have a few questions here. So start with how do these results vary between 850 millibar and the surface? You're showing.
Yeah, that's a great question. So most of what I showed is at 850 megabar, which is a level in the lower atmospheres, but not quite at the surface. Mm-hmm. And the reason for that is because they're very well correlated with each other, but the surface is a little bit more complicated because of the role of different land surface types. So if you just think about being like, or if you think about like the urban heat island effect, if you have a city versus kind of like an open plain, that will affect the temperature variability. That kind of like smaller scale detail wasn't really the focus of what we were interested in doing here. So it gave cleaner results to focus kind of just, a kilometer or two up in the atmosphere.
Mm-hmm. Okay, thanks. A question from earlier in your talk. Someone was asking, actually, I guess the Weather and Climate live stream was asking, what about austral winter weather over South America and Australia? And you briefly talked about that a little bit, but do you have anything?
Yeah, sorry, I should have made a backup slide on that. So we expect the strongest temperature variability to occur in winter. And in the southern hemisphere, the main mountain range is the Andes. And you do see a slight enhancement of temperature variability downstream of the Andes, so over like northern Argentina. But South America is actually so narrow compared to the other continents that the effect is relatively muted. So you see kind of a slight increase, but it's not. It doesn't show up as much as over North America.
Okay, I think maybe one more question. So I guess we've seen a bunch of talks over the past few days about aquaplanets. So I guess this is sort of a land aquaplanet. But what if you flattened every mountain range on land? So do you have a guess as to what might be happening? What might happen in that case?
Yeah, that gets to these superstorms that we were seeing. So what happens is a lot of storms grow by recycling energy from old storms. And what the mountain ranges do is they kind of interfere with this process. So if a storm is growing and it's kind of feeding off of getting energy from old storms, and then it'll run into the Rockies and then weaken because it gets kind of blocked by the mountain range. And so if you flatten all the mountain ranges, you get these really strong storms because they're just feeding off each other and there's nothing blocking that process. And so, you just get, if you think about it in terms of temperature variance here, just imagine like a really thick band of dark red here, much higher temperature variance than what we see today. And so that's why we felt that wasn't really comparable to what we see in today's climate. So in a way, it's super interesting. But it wasn't really relevant for trying to understand what we're seeing.
Okay, great. Thank you.
And thanks so much. Thanks for hosting, Karen.
Okay, so we are moving on, and we are going to sort of continue this weird topic here. But first, sort of check in where we are. So we are in the middle of our 85 of the live stream. And so we've got 15-ish hours to go. Before we get started, I want to remind you again of why we're here. You're here because you know that weather and climate forecasts help protect your lives and livelihoods. And luckily, the U.S. has been a world leader in weather and climate prediction. We developed the first computerized weather forecast, and we made the first computer models of climate impacts of carbon pollution. To make these forecasts work, we've created this unparalleled network of observations using weather stations and satellites and balloons and planes and boats and floats. And this resulting forecasting and observation system is a true scientific wonder. And we're so excited to share this wonder here with you. This wonder was made possible by decades of investment by you, the American public. But in recent weeks, funding cuts have put this miracle at risk. Weather stations are so short-staffed that we are losing our observational coverage, which is already hurting our forecast. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. And we're also losing a generation of climate and weather scientists as undergraduates and graduates and postdocs are not able to have the funding to continue their research and education and training. It doesn't have to be this way. If you like what you see, then we ask you to please use the link on your screen right now to contact your representatives and tell them to save our forecasts, to keep the lights on for weather and climate science so we can keep this wonder alive. And please spread the word to join this live stream. Either way, we hope you'll learn something about weather and climate, and please feel free to ask us any questions about the science in the chat. I do want to back up a second and tell people that my co-host I had here for a while, that was Leo, and he's a brown tabby cat, but he had something else he had to do, cat business or something. The next order of business is Garrett Finucane. Hopefully I got that right. A grad student in oceanography who is going to be talking about the density of seawater and how weird it is. And before we get started, a reminder that the views expressed by all of the speakers here, as well as the hosts, are their own and not the institutions for which they work. So great. Take it away, Garrett.
Hey, how's it going, everybody? My name's Garrett. So I'm a fourth-year graduate student at UCLA in Los Angeles, and I'm a physical oceanographer. And that means I study how the ocean moves and how it brings heat and things like carbon and other stuff with it. And so right now, my work is mainly focused on the physics of how water melts ice in Antarctica and how that's going to affect sea level rise and Antarctic ice sheets in the future. But I'm not going to talk about that today. And that's because when I was thinking about this talk, I was thinking about how I got involved with oceanographic research, and that was as an undergraduate. And I was lucky enough to have a fantastic teacher, Professor Susan Hodala at UW in Seattle. And she had an NSF grant, which had enough money to pay an undergraduate researcher part-time. And so I worked part-time on this project about deep ocean circulation. And I learned a lot about density, and I learned something about myself, which is that I love density. I love seawater density. It is a passion of mine. And so I thought, okay, what I want this talk to be is really like a love letter to density and all research that is kind of in the weeds, maybe a little pedantic, maybe a little bit boring, maybe a little bit niche, but that still matters a lot. And yeah, so let's talk about density. And so we're going to start by looking at a cross-section of the ocean. And we're going to do that using something called a conductivity, temperature, and depth sensor. And if you want to sound like a cool oceanographer, you can call it a CTD. And a CTD measures salinity. Really, it measures conductivity, obviously, from the name, but that is a proxy for salinity. It measures temperature, and it measures depth. And so that's the CTD on the right there. And the actual parts of the sensor that we're going to talk about, the salinity, temperature, and depth part, are pretty hard to see in that picture. What you mostly see is these bottles around the top that are called Niskin bottles. And those, as they are lowered, this whole sensor gets lowered through the water column. As it gets lowered, these bottles like fire off, and water is collected, and oceanographers on the boat can look at the oxygen or the organisms in the water at varying depths. And so the CTD is really like a fundamental way that we do ocean science. It's one of the few tools that really can give us a picture of the ocean from the very surface to the very bottom. And it's something that we've been doing for decades. So going back to, I kind of like hesitate to put a date on it, but at least the 1970s, almost certainly earlier. And so the way a CTD works is you have some seagoing vessel. I don't think you can see, oh, you can see my cursor. On the back here, there's this lift. And so you take the CTD, you put it down through the water column. At every depth, you take the temperature and salinity, and then you get a profile of temperature with depth that looks like this. So there's depth on the y-axis, temperature on the x-axis. So it starts off hot at the surface, and it gets cold at depth. And then you move your boat a little bit in another direction, you lower the CTD, you get another profile, and you do the same thing again and again and again. And eventually that tells you a lot about the state of the ocean. And this is such a fundamental part of ocean science that we've been doing this for decades, and we've been doing it all over the world. So here I've picked one international program through which we have taken a lot of these hydrographic CTD surveys, and that's the World Ocean Circulation Experiment. And here I'm showing just the section lines from the Atlantic. And a section line is basically a path, a trip that a boat's going to make over and over again over the years, so we can see how the ocean is changing and how the temperature and salinity and depth are changing over the course of decades. And we're really going to zero in on line A16 here. And the reason I chose A16 is because it goes a long way, and it goes from all the way from Svalbard up near Greenland down to this small island near the Southern Ocean. And like I was saying, you know, a boat went all the way down this line many times over the years, and it's dropped to CTD and measured temperature and depth, temperature and salinity. And we get a profile like this. So on the x-axis is distance. Svalbard's on your left, the Southern Ocean's on your right, and you have depth on the y-axis. And this is a picture of temperature down that whole section. And first things first, at the top, it's a lot hotter, especially in the equator. The sun's beating down on the water. The water is 20 degrees, maybe hotter, and it gets down to 0 degrees at the bottom. And one thing that may or may not surprise you, but that I do think is kind of unintuitive, is that when you look at this, the ocean is layered. It's not well mixed top to bottom. All the water is not one temperature. It's not homogeneous. There are these layers of waters of different colors going through the world's ocean that see the surface at one point and then travel down into the interior of the ocean and remain there. And I think this is really unintuitive. And I think it's really unintuitive because a lot of, as just people who go to the beach, for myself, like before I knew this from oceanography, when you're at the beach is this crazy place. The waves are crashing. It's really loud. There's a lot of foam. It's an incredibly well-mixed environment. But in the interior of the ocean, away from the surface, away from the beach, the ocean is way less like a bathtub where everything is well mixed. It's one body of water, and way more like a combination of oil and water, where you have differences in density that make water not want to mix together. And so because there are these changes in density, the water doesn't want to mix. That makes the ocean layered. It makes it stratified. And that means if you kind of if you take one step further, if the water doesn't want to move up and down, you can start to see that this water must move approximately along surfaces of equal density. So what jumps out is that density is this incredibly powerful tool. Like if you can start to understand where these layers lie and the layers of equal density in the ocean, then you can begin to trace these pathways of how water moves throughout the whole entire ocean. So density is really important and a really important diagnostic for oceanographers. And to really drive home this point that the ocean mixes less than you might think, this is a simulation of the Strait of Gibraltar, where the Mediterranean Sea goes into the Atlantic Ocean. And this is a simulation from a physical oceanographic group at the University of Malaga. And what you'll see is that there's Mediterranean water in yellow here. It's saltier, so it's denser, it flows to the bottom, and Atlantic water on top. And this is sped up. This is hours of simulation. But you can see there's 2 layers of water. And even as the tides slosh these waters back and forth over this strait that's like an underwater mountain, the layers don't fully mix. So it's a little bit hyperbole, but the ocean really is more like oil and water than it is like one well-mixed fluid. And this is like such a fundamental part of the way that oceanographers think about the ocean, and such a powerful assumption that a lot of the ocean models we make are layered ocean models, layers of equal density or equal density. And yeah, it's so powerful that we base, this assumption is so strong that we base some of our models off of it. Okay, so far we've said the ocean doesn't mix up much and down much, and that's because of density. And that means that water approximately travels along surfaces of equal density. I'm going to put that in quotes for reasons you'll understand later. And that makes density a really powerful tool. Okay, so I've talked up density. Now we want to calculate it. How do you do it? So here I'm using the symbol rho. That's what oceanographers use to talk about density. And the first way that we think about density is just as mass over unit volume. Oceanographers call this, maybe we're overcomplicated, we call it in situ density. The density, if you went and saw some water in its natural habitat at 2,000 meters or whatever, what its mass divided by its unit volume would be. And we know that there are three factors that determine the density of seawater. And that's the heat of the water, the salt of the water, and how much pressure it's under. So the hotter your water is, the less dense it is. We know that hot air rises, hot water is much the same. Like the hotter your water is, the less dense it is. Saltier water is more dense. It's got more stuff in it, more salt crystals weighing it down. And the more pressurized water is, the more dense it is. So as you take a piece of water and you really squeeze it, it gets more and more dense because you're forcing it into a smaller volume. And in practice, this happens in the ocean as you increase in depth. So the farther down in the water column you are, the more water is above you, and the more you're getting crushed by that water above you. And so water gets denser as you go down in the water column. And so you can go into a lab and you can figure out to a ridiculous, little amount of error, figure out the exact density, mass over volume of seawater by taking a piece of water of different temperature or salinity or pressure and then using these different instruments to measure it. And you can get an equation for how density varies with temperature, salinity, and pressure. Here are some pictures of old schematics from the 1960s and 70s of how density was measured from this wonderful article by Frank Malero. And so the result of all that hard work in the laboratory is you get this really long equation, a really long polynomial. It has 100 terms probably. I think 91 might be the real number, but that's from memory and I'm kind of making it up. But you get this really big equation. And what this equation does is that a hard-working oceanographer like myself, you take your temperature, you take your salinity, you take your pressure, you plug it into this equation, and what you get out is density. And so you might think, okay, we're done. We said density mattered. We came, we saw, we conquered, we figured it out. We know how to calculate density from salinity, temperature, and pressure, but it's a little more complicated than that, because say we go to the ocean and we take our boat and we lower our CTD and we get a first cast. And so here I've colored this cast with made up values of in situ density. So red is less dense, blue is more dense, lighter water is sitting over heavier water. And then you move your boat a little bit to the right, you drop your CTD and you get another profile. And so what we said before was, okay, we want to know density because if we know density, we can find these pathways of water in the ocean where it's not like oil and water, it's like water and water, or oil and oil, where water wants to mix with water of its kind. And so you have these two waters of equal in situ density, equal density at where they are. But this, and you say, okay, well, they're going to mix, so let's bring them together, right? They'll have to eventually meet at some midpoint if they physically want to get together and mix. But this problem arises where we said that density was dependent on pressure. And so as you raise the parcel on the left and the parcel on the right lowers, the parcel on the left, because it's raising, is getting crushed by less water. It's under less pressure. And so it gets less dense. And the parcel on the right, because it's now being crushed by more and more water, it gets more dense. And so by the time they meet, they are not the same density. Oh no, this is a problem. We went through all this, we spent years in the lab, and now we don't even have the thing that we came for. And so what oceanographers started to do was to play this complicated game. So you go to your profile on the left, you have this piece of water, it's some certain density. And now instead of naively choosing the water with the same density on the right-hand side of the profile, what you're going to do is you're going to ask this question, which is where, if I pick a water parcel, it'll be a different density, But where, if I pick a water parcel, if I bring them to the same depth, will they be the same density? So you have to play this complicated game where you search each profile for like each parcel needs its buddy, its pair. Yeah. Okay, so we can kind of now extend that from just 2 profiles to create this thing that we call neutral density. And so basically what Jack and McDougall, they're Australian oceanographers, they said, okay, so we start with one, but we're gonna take a reference climatology, which just means a bunch of profiles that we're gonna use as our reference. And we're gonna start with one profile. We're gonna pick a parcel and we're just gonna label it some random density. It doesn't even, we can call it anything. You could call it a symbol, a number, it doesn't matter. We're gonna call it, they call it 10, they pick a number that looks like real density. So they call it 1024. And then they say, they take the next parcel, they take the next profile in their climatology and they say, we're gonna play this game. We're gonna find the depth where these 2 parcels, when they match up, will be the same density. And then they do that from the second profile now to the third profile. And from the third profile to the fourth profile. And then they're not going to do it just for 1 point on that first profile. They're going to do it for a bunch of points on that first profile until you have this set of layers that traverses the whole entire world in your reference. And then if you're an oceanographer who's out at sea and you get a piece of water, you can look at the closest reference profile and you can play the little game of finding the closest piece of water, and that will tell you your neutral density. Awesome. So that seems pretty good. We kind of got around a hard problem there. And you end up with a new density variable is what we call it, or a neutral variable. So here's neutral density. It's wiggly. It increases with depth. That's what we want. Denser water is underneath lighter water. And this is actually A16. This is the section I was showing before. But there is one big caveat, and that's that if you play this game where you go from profile to profile and find these matching pairs of water, if instead of going in just a simple line or spreading out, if you go in a circle, you don't end up back at the same place. And this is a real weird idea. Like we were saying that we want to find water that's like that will mix easily with the water next to it. But if you play this game and you go around in a circle, you don't get back to where you came from. And so suddenly, instead of having a layer, you have this like weird corkscrewing 3-dimensional surface that is wrapping around islands and, it's doing crazy stuff. And what's even weirder is that this isn't a consequence of observational error. It's not like, we put the CTD down too fast or our salinity temp sensor was a little bit off. It's a consequence of really complicated mathematics of the shape of our density function as it relies on temperature and salinity and pressure. And so what that means is that there's no fixing it. Like this error will always exist. Like as much as we look in the ocean and we see these nice layers, mathematically, they're not well defined. And that's kind of crazy. And so that spawns this whole literature of people trying to make the most equal density. That's not what they call it, but I figured that's what I call it. The density that is, no matter which way you go, there's the water is the most similar, trying to avoid this problem. And so what you get is all of these different ways of better creating surfaces of equal density, better ways of calculating how well these surfaces are doing, ways to calculate it using really weird math like topology. And I actually worked with Jeff and I did a summer project with him when I was an undergrad, also paid by an NSF grant, working on an extension of this work. But all of this really is in service to creating a density variable that's useful to oceanographers who go on to do this incredibly impactful work. So on the left, I have a image of a study that was looking at how CO2, anthropogenic CO2, is taken up by the ocean. And it's looking at that on surfaces of neutral density. And on the right, I have a picture of a study that looked at how the ocean is taking up heat, again, on surfaces of neutral density. And so all of this weird, corkscrews in the ocean and time in the lab of temperature and salinity, it transfers into increasing the precision and the interpretability and predictability of our understanding of our work in oceanography. And I think that's really exciting. So my takeaway conclusions are that the ocean mixes surprisingly little away from the top and bottom. So like in the interior of the ocean, it's really pretty relaxed. The water's hanging out. There's not much mixing. The ocean is stratified by density, and that's what makes that suppresses mixing. And really, the science is kind of this team sport. So even though there is research that is really in the weeds and seems hard to understand why it would ever be useful, like these theoretical questions about density, that they all kind of help push the field forward. And I find that really exciting, and also an exciting part about listening to all these talks on this live stream. Thanks. Oh, and this is my dog, Kiwi. Yeah.
Thanks. That was weird. I have to admit that was definitely weird. So I'd like to start off with a question. So how might density change with global warming? Will it get more weird or less weird?
I planted this question.
I
thought it
was interesting.
Thank you. One thing that is really crazy, and this is a figure from IPCC's AR6, which is the annual review, chapter 9, which is about the ocean. These are plots of sea level rise under two different predictions of climate change, SSP 2.6 being a more mild climate, and SSP 8.5 being a more extreme emission scenario. And in both cases, this black line, thermal expansion, these are components of sea level rise. Thermal expansion is the water getting hotter and expanding. And so as we're heating up the atmosphere, as we're heating up the ocean is becoming less dense. It is expanding, taking up more space, and driving. It's actually the leading term in sea level rise. From now until 2100, at least. I do Antarctic science, and if things go really badly, that might not be the case anymore. But yeah.
So there's actually a question that popped up that is related to this, in that, so does this weirdness mean that the CMIP class models aren't actually, are they able to fully model this density?
Yeah, that's a fantastic question. And so I think the answer is that I think it's more something that people take into account when they analyze CPIP class models in the ocean. You want to make sure that you are still using the right type of density for your analysis if you're doing work about long-term changes in the ocean. So often these models, even if they're layered, they don't look for these they operate on a more local basis. They don't look for these global ideas of non-mixing surfaces. And so they kind of don't have to consider that problem. But when you go to analyze it, if you want to make statements about long-term changes in the deep ocean in CMIP class models, for example, you would have to be aware of this sort of error in density or error in choosing the wrong density. Yeah.
So the next question is about observationally, if you're trying to measure density in the ocean, isn't it always changing due to ocean currents or changing conditions? So is it really a moving target?
Yeah, that is a fantastic question. And it's really the thing that it's really exciting, that gets me very excited about physical oceanography is that if you want to, next level, all right, density is also what drives a lot of the large scale circulations in the ocean. So places where density is changing the most are often places with the strongest currents. But I am not an observational oceanographer. I've never been on a boat, but I do know that I think these CTDs are really heavy. And so they don't get pushed around too much when you drop them in the water. And you don't have to worry too much about errors in them bobbing up and down, for example, because the ocean currents usually aren't strong enough to significantly push them around. But they certainly, this field of density you're observing is changing as different like eddies and small features of ocean currents bring less and more dense water by your sensor. And so you kind of have to average through that. And that's why we often take repeated transects over the course of years to average out that small scale signal. Yeah.
Okay, I think maybe one more question quickly, unless we need to go. But a question about, are there other nations who are doing this research and collecting these transects if the US is no longer doing them?
Yeah, so actually, the World Ocean Circulation is the World Ocean Circulation Experiment. I believe the US has played a really significant role over the years, but it is under I believe it's called the World Climate Research Project, although I could be butchering the acronym. And so it really is it really is like an international effort to maintain these transects over the course of decades. And I don't think it's an exaggeration to say, though, that the US plays an integral role, and it would be it would be bad if they stopped doing it. Yeah. Yeah. Thank you.
Okay, great. Thank you very much. Really interesting work, Garrett. And thanks for joining us. All right, so we are now officially in hour 86. Wow. So 14 more hours to go. And we've got some other neat talks coming up here. Next, we'll be hearing from Burney, who will be talking about agriculture. But before we get going on that, we want to do our standard spiel here about, weather and climate, the importance of weather and climate research in terms of your lives and livelihoods. Luckily, the U.S. has long been a world leader in weather and climate prediction. We developed the first computer weather forecasts, as well as made the first computer models of the climate impacts of carbon pollution. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observing system is a true scientific wonder, and we're excited to share some of that wonder with you. This wonder was made possible by decades of investment by you, the American public. But in recent weeks, funding cuts have put this wonder at risk. Sorry, it's late. Weather stations are so short-staffed that we are losing our observational coverage, which is already hurting our forecasts. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for our basic understanding of the weather and climate is disappearing. And we're losing a generation of young scientists, as students, postdocs, and other early career scientists are not able to get the training and education they need in order to grow as scientists. It doesn't have to be this way. If you like what you see here, then we ask you to please use the link on your screen right now and contact your representatives to tell them to save our forecasts, to keep the lights on for weather and climate science so we can keep this wonder alive. And please spread the word to join this live stream in these last remaining hours. We hope you learned something about weather and climate, and feel free to ask us any questions about the science. And so the next speaker we have coming up is Burney, who's a professor, and she's going to talk about climate and air pollution and impacts on agriculture. And I just love that we've gone from talking about weird weather to weird ocean, and now we're going to talk about air pollution and agriculture. So this is great. Quick reminder that her views are her own, as are the views of all of the hosts. And go ahead and take it away when you're ready, Jen.
All right, thank you so much. And thanks to this incredible team of organizers for, not only pulling us all together to help share this with the public, but really making it just an event full of delight and wonder. And I love that it's explicitly framed as wonder, because that's why all of us are here, is trying to understand our wonderful planet. I thought what I would do is talk a little bit about some of my research group's work on climate and air pollution impacts on agriculture. And that's something that sounds very applied and like it would be very practical to sort of always have this around. But what I want to tell you is that this really has been surprising at every step. And I'm going to take you through a little bit of a timeline of what we've learned over the years by leveraging our incredible data and observational capacity that was never intended for this. This is sort of an accidental set of discoveries. And I thought it would be very fun, especially late at night, to tell a good kind of unexpected science story. All right, so my research group does focus on food security and climate and the relationships between them. As one piece of that, we work on understanding, climate and environmental impacts on our ability to produce enough food and really on people's livelihoods. Why do we care about this? Ultimately, it's about food security, right? We want a world, it's a value shared by everyone. I think we want a world where everyone has access to the food that they need for a healthy and productive life. And when I started really as a PhD student, sort of over on the left of this plot, we were making really good progress in year on year reducing the number of hungry people in the world. And as that PhD progressed, that curve started to level out here. It looked like we were on target for sort of World Food Summit targets, which were to have the number of hungry people in the world by 2015. And then we saw this kind of flattening out. And sadly, in recent years, we've actually turned in the wrong direction. And year on year, more people are going to bed hungry every day than the year prior. So we're now a long way off from where we thought we would be. And one of the puzzles in here is that, of course, many things contribute to food insecurity. We can think about disruptions like war or conflict, but also we know that countries are not keeping up, and globally we are not keeping up production-wise. We have sort of amazing gains, but they're not enough. And my group's been trying to figure out some piece of that. All right. And when we look at this leveling out that I just mentioned kind of over the course of my career, it was very interesting to try to look at this and look at sort of progress in food production in different areas in the world and try to puzzle out like how much warming was contributing. So just overall, for example, like temperature changes, precipitation changes, but also rising carbon dioxide levels, right? How much all these things were contributing to sort of crop production around the world. But there was this other piece. And this piece was that looking around the world, it's hard not to notice that many of the world's most productive regions are actually incredibly polluted. In addition to feeling a lot of, the same trends that are being felt everywhere, warming and sort of weirding, we also have this dirtying in many areas that produce a lot of food. So I'm calling in from California here. So we're the fruit and vegetable market for the country and the world. And you can see this is an image from Bakersfield where a ton of, different produce crops are produced, and it's incredibly polluted during, most of the year. We go around the world. This is now a NASA, NASA visual imagery of a sort of annual pollution covering the Indo-Gangetic Plains, one of the major wheat and rice producing regions of the world. And you have this in many regions, this coincidence of deep pollution conditions and heavy production areas. And so we set out to figure out why does this matter and how much, and sort of what sense can we make of this system. In addition, there was smaller scale evidence that some of this should matter. So the lesson I would say to take from today is that pollution is a little tricky to study because there's many pollutants and many pathways for impact. If we just think about the United States Environmental Protection Agency, we define 6 criteria pollutants that we monitor and have standards for. Those are ozone, particulate matter, so suspended particles in the air, sulfur oxides, nitrogen oxides, carbon monoxide, and lead. And so each of these, we have some monitoring for, and we know they are dangerous to human health. That's why we monitor them, but we set out to understand the relationships with crop health and crop production. And we had some small scale evidence reason to believe this. So one is that it's long been known that ozone is damaging to plants. So over here on the right here, this is a leaf with direct ozone damage. And it's an irritant, just like anyone who is asthmatic knows that breathing ozone is terrible for the lungs. It's an irritant, same thing for crops. From chamber studies and things like that ozone was likely going to show up as important. But there's also some smaller scale evidence, teeny studies here and there that had sort of suggested that maybe these oxides of sulfur and nitrogen were also potentially damaging to crops. And then we had reason to believe that particulate matter, these particles suspended in the air, would matter for crop growth. And that comes directly from us being climate science people, right? Which is, we know that aerosols in the atmosphere are sort of the gift that keeps on giving. They have lots of different effects, all of which really matter for crops. So here's a little diagram over on the right of all the things that aerosols do. They have many different sources. When we talk about particulate matter, there's many different flavors, right? We've got ammonium compounds, we've got sulfur compounds, we've got nitrogen compounds, carbonaceous aerosols coming from different places. We really generally measure it in bulk with a little bit of speciation information at coarser spatial and temporal scales. But really, we tend to think of this as a homogeneous thing, even though it's not. But what I want to point out is that these aerosols in the atmosphere do a bunch of things that would matter for crops, right? So first, they actually change the nature of sunlight reaching the surface where crops would use it to photosynthesize. They do that by both absorbing radiation if they're dark, or if they're shiny, they scatter radiation, and both of those things matter. They change the surface temperature underneath them, so you actually get a little bit of aerosol cooling, right? Aerosols also interact with clouds and change precipitation dynamics, which of course matters for crops as well. And then even there's some evidence, of course, that if there's really, really dirty air and aerosols are directly depositing on leaves, like in these images here on the lower left, that would directly impede sort of photosynthetic capacity. So a range of ways in which we think particulate matter would matter. So again, a whole range of pollutants, and we set out to try to start to figure this out. Now, what you'd love to do, right, is like your elementary school science experiment. You'd love to have like a whole bunch of different pots, and you'd love to expose each one to like different conditions and have lots of replicates to be able to do this, and change all sorts of other things methodically. This becomes a very, very big experiment, and of course, you can't actually do that. It's very hard to set up and control things like your sulfur dioxide concentrations over a pot and change that carefully. So this is not the kind of thing you can do at large scale in all of the different dimensions you would like. At the same time, it's also really important that we understand real world conditions. We want to understand like how this is affecting farmers around the world and our food system. So we do actually want to understand this in the real world. What we can do, though, is leverage the fact that agriculture is the single biggest perturbation to Earth's surface. And so there is a lot of data out there. There are a lot of hectares of land producing a lot of food, and we can use the variation and exposure of those crops to better understand these relationships. And since if we can get enough information out there of different, different exposures, for example, corn exposed to different conditions all around the world, we can tease apart those pollution relationships with crop production using statistics. All right, so I'm going to take you through just very quickly 3 of the sort of group of studies that my team has done over the years to show you how we've kind of gotten at some of this picture. All right, so the first one that I want to talk about is from a few years ago, and we used the fact that there has been this natural experiment in the United States whereby, just due to economics and technology, there has been this big shift in electricity generation in the United States from coal towards natural gas. So there have been a lot of units that have shut down, and coal-fired units that have shut down, and natural gas units that have opened up. And here's just a little map of between 2004 and 2016, what that landscape looked like. So old coal units getting taken offline, and our whole energy infrastructure just spatially reconfiguring. This was happening for other reasons, but we saw this as a way to look at nearby impacts. What does this mean for people living nearby, either old or new units? And what could we learn, for example, from this? Because it wasn't motivated by agriculture, but what can we learn from this about the impacts on agriculture? If I just take you through one little example here. So this is in Cobb County, Georgia, a unit that shut down in 2012. The blue line in each of these panels shows production, so generation. And so that's identical in each of these 4 little panels. And you can see that, plants don't tend to run at full bore and then just get shut off. They sort of get ramped down as other capacity comes online, et cetera. So you see this ramp down. And for all of these pollutants that really matter, right? Particulate matter, ozone, oxides of nitrogen and sulfur, you actually see these changes before and after the shutdown in the surrounding area. I think this is out to about 25 kilometers here, although that effect does persist over much further distances. So you do see these effects, and this is just one location, but what you can do is average over all of those units being shut down at different locations and times to try to understand what those impacts look like. And so when we look at pollution, we are using both surface and satellite measured information. I'll come back and praise the data more detailed at the end. But what we see on average is, about a half microgram per meter cubed drop in local particulate matter pollution, for example, nearby. And then we can also pair this information with county level statistics on crop production gathered by the USDA, and to see what happens in counties when a plant nearby shuts down. And what we saw is that, especially for corn, we see a strong statistically significant impact. When a unit shuts down nearby, corn yields go up. Incidentally, I'm not going to talk about it too much here, but there are also health impacts. Mortality drops nearby when a coal plant goes offline. That's probably not surprising to folks. Our sort of human exposure story has been a lot more richly elaborated over time, but this agricultural story was a bit new. And so there's very clear evidence of gains, right? Really, that air pollution from coal-fired power plants was having negative impacts on agriculture. If you take the most strict definition, just within 25 kilometers, this top panel shows you where those benefits accrued. And if you take what we see as the limit of where we saw clear impact out to around 200 kilometers, you see a much richer set of beneficiary counties when it comes to corn production. So these are the benefits over that time period in corn yields, right, due to the shutdown of coal-fired plants over that time. The other thing, though, to say, though, is that there's a lot of benefits waiting to be had, right? So there are many coal-fired units still online in different counties, some in the same counties that have already benefited to some extent. So some counties have reached part of their potential benefits. Again, sort of at that tightest bin out to the real limit where we think the spatial pattern holds. So a lot of potential production still being lost to these negative impacts. And, it adds up to billions of dollars every year. I'll say a little bit more about that in a second. All right. So second study was to say, when we look at coal-fired power plants, for example, here, we nevertheless feel a little bit limited by data, right? We're sort of looking at the county scale, trying to merge together satellite observations of pollution, but also surface observations of pollution. And you can end up in a sort of fairly sparse data world. So if I show you over here on the right, this is sort of the main corn and soy belt of the United States. And this is showing you where different pollution monitors are over that area. And of course, this network was not designed for this purpose, right? This is a really public health oriented measurement network. And so, you know, it's not set up the way we would want to do it if we were going to go put monitors out to measure crop impacts. So instead of saying, all right, you know, throw up our hands, we don't have enough data, we can't do it, we said, you know what, like the way to do this is to actually use higher resolution crop data. So this is a collaboration with a friend and colleague, David Lobel, who has developed a very high resolution crop yield mapping tool over the United States. And this is based on, you know, heavily based on US remote sensing infrastructure and international collaborations. But this is a seasonal map over the last 2.5 decades of corn and soybean yields at about 30-meter resolution. And so we can leverage this really nice high-resolution data to now zoom in where we know that there are, for example, measurement networks, and we know where there are emission sources like power plants, and we can get a much finer understanding of what that looks like. So this is the second study. And one thing we thought was really interesting was, you know, when we looked at coal-fired plants in the previous study that I showed you, we're seeing the total effect of the plant shutting down, but that's a lot of emissions of different varieties, right? So there's carbonaceous aerosols, there's sulfur compounds, there's nitrogen compounds, there's carbon dioxide, et cetera, et cetera. So it's the sum total, but we wanted to try to now tease that apart. And this is also a way that we could now do that. All right, so briefly, I'll show you two kind of summary figures here. On the left, this is now taking all the power plants, all the active power plants in that area, and now looking at this high resolution yield around them, where around each plant we sort of subtracted the average. So this is now 0 is the average. Now we're just looking at the difference sort of close to a power plant where it's 0. So 0 to 1 kilometer away, you see that yields are lower on average. And when you move out from a power plant, yields go up. So even just sitting there around active power plants, you see this penalty where yields are a few percent lower as you get closer to a power plant. And things that contributed to larger scale differences in crop yields, like soil quality, things like that, don't tend to vary, in those kinds of timescales. One thing we were able to do is then, again, map these different pollutants. So particulate matter, ozone, sulfur, oxides of sulfur and oxides of nitrogen. And you can see that they also have very different gradients around power plants. So this is just, again, one example here, but we could do this around all of them at high resolution. And we could leverage the fact that these pollutants travel different distances to explain these gradients of crop yields around power plants. And a few things popped out. One is that there's sort of a surprising role for these oxides of nitrogen. We don't tend to think of these in pollution land as as it wouldn't be your first guess about what matters most for crop production. You would think ozone and oxides of nitrogen contribute to ozone production, so maybe that's why it might matter, but standing out on their own was a little bit surprising. So a big chunk of the effect is in fact due to these oxides of nitrogen. The other thing that was interesting was that when we look, ozone levels have declined over the US over this time period. And in fact, the reality that the air got cleaner actually explains 20% of yield gains over the corn and soy belt of the United States over that time period. So technology is some of it, farmer know-how is some of it, and 1/5 of it is cleaner air. So there's really we see this as mounting evidence that there's some low-hanging fruit and a real point of convergence between communities who are sometimes like cast in the media as at odds with each other, kind of, right? Environment, climate, pollution, and agriculture. And this is a place where we've found that farmers are very, very interested to hear about this. They sense it's an issue. They're very surprised by the magnitudes, and it creates convergence. This feels like again, as I said, sort of surprising and actionable. All right, third study that I want to bring into my story here is just that we then said, okay, let's take that nitrogen story and let's go global with it. So this leverages more recent satellite capacity to look at nitrogen dioxide at a global level. And we were able to use sort of the first 2 years of the satellite being up and online to look at the world's major bread baskets. And we brought together these these nice high resolution data on nitrogen and vegetation observations. So this NIRV is just a measure of greenness that we're going to use as a proxy for yield measurements. And we can do all sorts of things, control for known differences across regions, and then compare within these regions, again, at spatial scales where some of the bigger factors don't vary, can compare these differences and tease apart this relationship more locally. And what we found was that for 9 out of 10 growing seasons, again, just in the first 2 years of having this observational capacity, significant negative impacts of these nitrogen compounds on crop production. And back of the envelope calculation is that, taking local levels down to kind of their local floor, so like the 5th percentile in a given area, would raise yields about 10% in most regions and even higher in China, just because of the high baseline levels of pollution. So again, we see this as a lot of, to make a bad food pun, low-hanging fruit to be had in kind of our desire for a sustainable food system in a more stable and clean climate and environment. I thought I'd say just a couple of words about how this came about. The 3 studies I mentioned required matching, field to very small administrative unit data with ambient environment conditions. And again, most of these were not designed, again, to be matched to each other at the time that they were launched. So I think it's a really nice story of what comes from just stable, rich, curated public data is the opportunity for discovery. This was directly funded by the National Science Foundation and the USDA, NIFA, the National Institute for Food and Agriculture. But our data actually is sort of, I like to call it was indirectly funded through provision of data by a bunch of other agencies. So EPA data on emissions and on measurement of criteria pollutants at stations around the country. NASA observational capacity, we drew heavily on the A-Train, and then some more modern global collaboration satellites. We used CDC information, national vital statistics, for mortality and other health impacts information that I didn't get into here. And we used the National Agricultural Statistics Service, of course, to really understand what's going on with farmers, around the country. So these are really, really vital long-run public data sources that have been under threat in recent years and are certainly on the chopping block to some degree now. And hopefully I can at least give a few stories here about why just the existence of data, even if it's not designed for the purpose at hand, can really lead to important discovery. Thanks.
Thank you, Jen. That was really interesting and very. The link to why is this important was quite clear there, with this huge impact on crops. And you really got a lot of questions going in the chat, so we'll try to get to a few of them. I'll start with, is ozone damage to a plant like a sunburn? So why does ozone damage plants?
Yeah, it's got high oxidative potential. So just like it irritates your lungs, it is directly damaging to ozone tissues. So yeah, looks like a burn when it happens.
Are there any common signs of pollution damage in our food sources that we can keep an eye out for?
I wonder what the question asker meant. So
I think they were talking about, looking at, as a growing things and consuming things. Yeah. What are there any things to be concerned about?
yeah, so there's some work, I didn't talk about this here, but there is some work to look for things like heavy metal contaminants that can be mobilized by things like wildfires and whatnot and deposit to test food for that and soils for that. So that's kind of one thing. And then, ozone damage to a plant doesn't make it dangerous to eat. It just, it's less productive. It's a less healthy plant in and of itself. Yeah.
Next question. What's the recommended distance from the road, and does it vary based on traffic volume?
That's a really great question. Actually, I've been trying to understand this better because you do have some interesting competing effects. So for one thing, we do know that like plants do get a little bit of a carbon dioxide bump, right, from having sort of more direct exposure to emissions. I've been told that like people who are looking for blackberries in the Pacific Northwest all know this. It's like better near the road or something. I don't know if that's true, but that's what I've been told. So you have a little bit of a fertilization effect from that, but also the pollution effect. We don't quite know how it nets out. So we've been trying to get kind of higher resolution at this. I don't have the answer. It's a great question.
Okay. And let's see, just, I guess, a speculative question to close things out. How much coal would have to be burned to cause complete crop failure?
It's a really stupendous question. We don't know the answer to that. In part because we're not quite sure what effect would win out. So let me give it like an extreme example. We've studied some of this before too. So like what happens during what happened historically during big volcanic eruptions, like Pinatubo, El Chichon, like what happened to, that's often used as like an analog for like nuclear winter or geoengineering or whatever. So we saw there that there were pretty negative impacts. And for example, that the sunlight impact dominated any benefit that might have come from the cooling impact. So, two things happening at once, you're not totally sure which would win out. And I think that's the same thing for coal. Like if you really heavily polluted, you would have, again, these kind of competing effects. And we're not totally sure how nonlinear it might be as you get into sort of super polluted regimes. There's pretty interesting research coming out of China suggesting that you get like, that there may be some nonlinearity.
Okay. Hang on. Okay, let me do one more question here. Let's see. I guess, why isn't New York higher in pollution? I'm surprised there isn't more pollution elsewhere, like in the South or in California.
In terms of the benefits maybe from shutting down coal plants, that might have been what that was.
I think that was
so some of that is a combination of where the plants are, and for example, that had not already been shut down at the start of that study. So we a lot of the New York area plants had probably shut down prior to that window when we were looking at it. And then same thing in California. We just actually in California don't have any coal-fired plants. So that just falls out of the study in that regard. Yeah.
Great. All right. Well, I think we're out of time here. So thank you so much, Jen. It was a really interesting talk, and glad you could join us.
Thanks, everyone.
All right. And before we move on, I do want to address the question that was actually not Leo who went past me. That was Misty. So you saw a Cat 2 sighting. So if you are joining us just now, we are in hour 86 which means we have about 14 more hours to go. And this next talk I'm really looking forward to. It's going to be talking some about climate workforce development. So before we get started on that, you're here because you know that how important weather and climate forecasts are to protecting our lives and livelihoods. Luckily, the United States has long been a world leader in climate and weather protection. We developed the first computerized weather forecasts, and we made the first computer models of the climate impacts of carbon pollution. To make these forecasts work, we've created an unparalleled network of observations using everything from weather stations to satellites, planes, balloons, boats, and floats. The resulting forecasting and observation system is a true scientific wonder, and we're excited to share the science with you. This wonder was made possible by decades of investment by you, the American public. But in recent weeks, funding cuts have put this miracle at risk. Weather stations are so short-staffed that we are losing our observational coverage, which is already impacting the skill of our forecasts, as we've seen in some of the earlier talks. Laboratories dedicated to understanding our climate's future are being closed or shrunk, and funding for basic understanding of the weather and climate is disappearing. And we're losing a generation of scientists as students, postdocs, and early career scientists are missing out on all of the wonderful opportunities that people like I had in terms of getting training and education needed to develop as scientists. It doesn't have to be this way. If you like what you see here, then we ask you to please use the link on your screen to contact your representatives and tell them to save our forecast, to keep the lights on for weather and climate science, so we can keep this wonder alive. And please spread the word to join this live stream. We have 14 more hours to go. We hope you learned something about weather and climate, and please feel free to ask us any questions about science in the chat. So the final talk that I will be hosting today is Dr. Aradhna Tripati, who's a climate scientist and professor at UCLA. And before she gets started, just a reminder that all statements are speakers' views and not the views of their employer or funders. So thank you very much, and go ahead and get started when you're ready.
Hi, thank you, everyone. I appreciate your time in learning about some of the work that we're doing. Our work emphasizes developing the climate workforce that communities need across the country. And we do this by supporting students and community members to gain education and training and to apply what they're doing to address real-world problems. You may not know this, but the last couple of years, we've been having climate disasters that happen in this country that cost more than $1 billion every 12 days or so. Now, it wasn't always this way. In the 1980s, this would happen every 4 months or so. Many of you saw the photos of this assemblage of fires burning around Los Angeles earlier this year. This, of course, hit very close to home. Others have seen the images from North Carolina, and of course, these events are occurring across the country. And so it is so important for communities to have the tools they need to be able to be resilient, be able to respond and be able to recover, plan for these events. So the work that we do with the center that I direct that has recently been defunded, it involves, we've supported about 500 people from across the country with fellowships so that they can devote time to developing science and technology skills and learn about applied problems in climate and environment and health. We've supported high school students, community college students, undergraduates, graduate students, as well as community members, all generations. Now, our motivation for doing this is really because this question of for our collective futures and our individual futures, who's going to get to decide the direction of climate, health, science, research, practice, and policy? Well, all of us need to be able to do that, right? And so we're focused on enhancing science education, research, and workforce development so that we can be prepared for the risks that we're facing now and in the future. And we do this with a really innovative model that involves grounding with community partners in ways that will build short and long-term science capacity in them. We work with over 60 partners. I show here a map. We work with folks from Georgia, Texas, Florida, Oregon, Arizona, New Mexico, Rhode Island, California, and more. We work with people from rural communities and urban communities so that they can get hands-on experience and they can get access to those key jobs in climate. We do this by building out partnerships with companies, community-based organizations, museums, nonprofits, as well as colleges and universities. Now, just as a quick introduction as to how I got to this work, I'm a professor. I direct this center that's focused on climate futures. My parents emigrated here. I was born in Texas. Values of things like service and leadership were really important to my family. And so because of that, and because of some of the values that the educators I met during my training, it was really important for me when I started my job to emphasize service and giving back to the communities that we're part of. And so, with this, the work that we do with the center, with our Climate and Community Futures Lab, the center where we believe in science for all and our national consortium for developing leadership, it includes giving people a range of different types of skills training, supporting collaboration in teams where we're working on research and solving problems, supporting people to give back through outreach and engagement. We're really grounded in partnerships, but also access, equal opportunity, and financial support. And we engage to make sure that there's care, belonging, role models, so we can all see ourselves in the work. And mentorship is also really key. Now, we do this work at a leading public research university that has a top-ranked climate program, but we also have a strong commitment to community engagement and a leading medical school. A third of our undergraduate students are first in their families to go to college, and we have some of the highest in social mobility amongst leading universities. Now, this work began a while ago, back in 2008, and some of the outcomes from our initial phase of work in about 10 years was that we supported 130 people. We worked on real problems that affect people's lives. We emphasized teamwork. We found that people wanted to persist in science, technology, engineering, mathematics, and medicine. Their skills grew, technical skills, data science skills, communication skills, science ethics. And they had this connection to science and did work in climate science. And they felt like they belonged in the climate community. So then our next stage, after getting encouragement nationally from folks at the National Science Foundation, NOAA, the Department of Energy, and other agencies, and from private philanthropy, was to really emphasize building out locally a center and then a national consortium. And that work, has gone on for nearly a decade. We have worked with veterans. We have worked with folks who are interested in community college development and so much more. Now, our emphasis really is STEM for all. And I just show this to show that, we envision a world where people from all backgrounds and cultures for respect for science and storytelling can work together to address complex climate challenges, and where all voices can shape knowledge creation and implementation. This is not the kind of elitist tower or an academy. This is, in fact, STEM for all that our universities are grounded in. And we do this to ensure that people have the tools from climate and data science needed, and certainly the tools we can use to assess the impacts show that from higher skills to technical skills to science identity and scientific understanding, it's been deeply impactful. Just to give you a taste for what this looks like, anybody can apply. It's open to everyone in the country. You know, for folks who are early career, if they're high school or college or a grad student, or if they're thinking about going into this type of training, as long as they make a commitment to growing their skills, applying their skills in communities of learning, getting real world hands-on experience, giving back through community engagement, participating through mentoring, and sharing stories of what they've done, then in fact, they're eligible to become a fellow. And, you know, our fellows come from schools from across the country. Some of them just spend a few hours a week. Some spend more like 20 to 25 hours a week. And so this is what is really being impacted and being lost because of the recent funding cuts. We also have faculty from universities that are steering some of the projects, including things like fire resilience, the cleanup of lead after storms, using artificial intelligence to better predict disaster risk, and working on issues of climate change and health. Now, we also support community members who steer some of the projects, and this ensures that there's civic science being done, science in service. So from science camps for youth to developing GIS as a tool, geospatial tools for community health to look at impacts of air pollution on health to better prepare communities. So, you know, we've been building resilience in people who might not have otherwise had access to these resources so that they could advance community goals relating to climate. And at the same time, we support people and equip them so that they can participate and give back to the communities that they're part of. This work has been incredibly inspiring, and I just show here some of the network of fellows that we have from across the country. Now, this is very much science for impact. You know, from Esperanza Community Housing, a low-income housing community, we have been supporting for several years cohorts of youth and adults, working with college students on a series of community education projects. We've also been supporting community members in an urban community in Watts, from developing frameworks for partnership, learning about how to make measurements of lead in the community, understanding how toxics might be released and transported, engaging with youth, and also even things like working on support of a community garden and art and science exhibition. Our fellows also have the training that are needed so that they can work and advocate for communities and go into science policy, climate and weather policy jobs. And there's a whole series of really important outcomes from this around things like water access, air pollution, and other things. So with that, I will thank you and take some questions. I really want to highlight that the work that we're discussing in these 100 hours, it relates to whether, you know, being able to address planning for extreme weather, for climate change, health outcomes that are downstream of this, energy needs, and food security. So it really does touch on all of our lives. Thank you.
Thank you so much. That was both inspiring and also depressing. Yeah, my first question, I guess, is, so is this program defunded now, or is partially funded still? Or
Yeah, we lost 2 grants from the National Science Foundation, one in April and one in May, April 18th and May 9th. And those grants totaled almost $8 million. They were our next 5 years of work. They support more than 30 staff and contractors and more than 247 fellows, community members, students. So this is really devastating. This is one of the top 15 grants that got defunded from the National Science Foundation listed in GrantWatch in terms of the monetary amount, and the largest one at the university and one of the largest in the state. But keep in mind, please, this is impacting people from across the country. It's impacting students in Florida and Georgia and Texas. You know, their support impacts their families. It impacts these communities having trained people to be able to do this type of work.
I guess follow-up question, how can we get involved, or how can we help?
Yeah, thank you. Well, this was about 80% of our support. So we have a 90-day emergency campaign. One of the first things we really need everybody to do is to please consider writing to your elected officials. Whatever city, county, state you're in, doesn't matter. Write to them. Let them know that these are the impacts on our communities. You know, what's happening right now with a budget that's under consideration, that's going to result in many, many more people being defunded. So first and foremost, you know, this is for communities across the country. We absolutely need to contact our electeds in the next week. Secondly, please share what I've shared on social media and with your friends and family members that this has happened, and please consider asking them to reach out as well. Finally, I also put my email here, the email for our program, my number, and you know, our website to learn more about the work. You know, through this, there's opportunities to learn about how you can, if you want to donate, we have a crowdfunding campaign. People can donate $1, $5. We welcome that. But even just expressions of support, we appreciate. The most important thing is knowing that we're going to get through this together, and that every little action counts. You know, I can say that just because, you know, since this happened in mid-April, we've been reaching out to our network and reaching out to people across the country. And we've raised about half the money we need for this year, which means at least we have something, right? And that's through small and large donations. But the thing we need more than anything is to call on our electeds to please make sure they support NSF, NOAA, DOE, and the other federal programs that all of us depend on. Thank you.
So maybe another question related to it. How about for people outside of the U.S.? Is there anything people outside the U.S. can do?
Yeah, thank you so much for asking that. I actually think it's really important to do some of those same things. I lived in England for several years as part of my training, and you know, then came back to the U.S., of course. And in that time, I also saw that it's helpful, really helpful for people in the U.S. and electeds in the U.S. to know that what happens here, the rest of the world also cares about. You know, the U.S. has been such a strong part of international weather and climate prediction, international weather and climate research, and our programs, this type of work, it's been on the forefront. Our center and the work I've talked about, we've had people visit from all over the world to ask if they could replicate what we're doing and learn from us. So please consider reaching out to electeds. Please share about our work, and also please join our crowdfunding campaign so we can get through this immediate time. Thank you.
Thanks. So talking a little bit about the program itself, question, are there considerations that go into outreach towards not currently in school adults or ones who never received any sort of degree?
Yeah, so actually the majority of the community members that we work with, the hundreds of community members we've worked with, are people who've never had a degree, right? And so this has been something that gives them the skills to be able to enter the workforce. So people have then been able to apply for jobs, then been able to get, the practical experience needed so that they have skill set and also the references to be able to point to this. And for others, it's made them decide, hey, they want to go to community college or four-year university and get that training. We've also been looking at micro-credentials, and supporting that. We've had people who had to drop out from high school because of just what was happening. They had to support their family at the time, and they have found our program to be an enormous source of support. So they're some of the strongest advocates for our program. We actually have video reels that people are posting to Save Our Center. If you search for that hashtag, Save Our Center, you'll see information about it online.
Great. So I guess also in terms of the working with these different groups, you've worked with a wide range of people, different backgrounds. What has been like the most surprising to you in terms of something maybe you didn't expect, but maybe changed your way of interacting with the groups or something like that?
Yeah, I have such deep respect for everyone, irregardless of their education level, irregardless of their career, their economic status. This is what my mom taught me, right? And so those are the values that I hold. Everybody is deserving of care and respect, and everybody has potential. They just may not have access to opportunity. What I've seen has been extraordinary. There's a person, Monique Uriart, who I've worked with, who's a community member from Esperanza Community Housing, and seeing the extraordinary wisdom she holds, and the research questions that she said the community needed answered, the things that came from that, the ways that helped her community with respect to air pollution and human health, it was remarkable. And it actually ended up impacting everybody in the city, county, and state, were the eventual impacts that she was able to have. And so to me, it was truly a David and Goliath story, because here's a person who doesn't have, the same formal training, let's say, that a person with a PhD has. And yet through this collaboration, through this NSF supported, federal government supported partnership, supporting community education in climate, weather, and the other science tools we have, she did something extraordinary for everybody in the city, county, and state. And that shows me the potential for climate science and our tools when everyone has access to it.
Well, that's a nice uplifting stories about the impact you can make. There's something going on with okay, so I think we need to wrap up for now, but thank you so much for coming and sharing this amazing work with us, and fingers crossed that things will turn around and you'll be able to keep doing it. And I'm definitely going to keep your program in mind for the climate science students at my university. So really appreciate it.
Thank you so much. Take care, everybody.
All right, thanks. Okay. And I believe that is the end of my hosting duty. Is that right? Lily, are you here to replace me?
Yes, I'm ready to take over.
Okay, great. Well, thanks everyone. It was fun, and hand you over to Lily and enjoy the rest of the live stream.
Thank you, Karen. Okay, hello everyone, I'm back. For those who don't know me, I'm Lily. I'm a PhD student in atmospheric and climate science funded through the NSF Graduate Research Fellowship Program that we've been hearing so much about. So as a reminder, I, as well as our upcoming speakers, are speaking in our personal capacity, and our views do not represent those of our employers, funding agencies, or any other speakers. Since this is my last time signing on as a host and the night is getting late, I thought I might go off script since you guys have heard my spiel a number of times already. And a lot of our scientists have been sharing their own stories with their scientific journeys on this live stream. And I wanted to say a little bit about what this scientific community means to me. So, a little bit about me. I was kind of like born into this community. My parents came to the US when my dad did his PhD in atmospheric science at NC State. And I was born when my dad was doing his postdoc at the National Center for Atmospheric Research. So, like, I literally would not be here today as an American citizen without these like federally funded weather and climate science initiatives. It, goes without saying that growing up, I thought that being a scientist was like the coolest job in the world. And that was even before I knew anything about physics or climate science. Like, what could be cooler than, like I saw my dad traveling across the world, exploring the unknown, literally flying through hurricanes and becoming a friend, mentor, and like family member to all these really amazing people. So, unfortunately, my dad passed away a few years ago, but with the current situation, what's been going on, I can't help but I've been thinking a lot about him and like how he would have felt about what's happening now. So since we're nearing the end of the live stream and the start of hurricane season, I felt compelled to share some words, like maybe on his behalf. So one of my dad's greatest scientific achievements was pioneering this system of assimilating, so incorporating high resolution observational data from radar and satellite measurements to update hurricane models. And they found that this method outperformed the existing hurricane predictions, and that actually like helped spur the adaptation of these assimilation techniques in operational models that are now used by NOAA. And so NOAA and the collaborations between the research arm of NOAA and all these like scientists at different universities was so essential to like all these advances that have literally saved lives. And many of these friendly aunts and uncles I knew growing up, they were NOAA scientists. So it's just really unthinkable that the administration would try to eliminate the Office of like Oceanic Atmospheric Research as they proposed in their most recent budget. So I hope that you all have been able to see from our efforts the like truly like deep love and commitment weather and climate scientists have for understanding, modeling, and predicting the Earth system, and continue to spread the word about what we do. Call your representatives even after the event is over. And thank you so much to everyone who already has. So with that, back to the script. Following up, we have another professor from UCLA, actually, Dr. David Neelin, who is an expert on many things, and I'm so excited to hear his talk.
Hi, Lily. Thanks. Can you hear me okay?
Yes, we can hear you.
Great. And I really enjoyed catching at least part of Aradhna's talk before me. It's a very inspiring center and work that she was able to share. So I'm going to go through a couple of things in terms of the volatility of weather and climate, giving me also an excuse to mention a couple of items of work from groups around me and some of the younger people who work with me. The slide that I have up at the start has a couple of samples from California, where I'm based. From the drought that culminated in 2014, reservoir at the upper left that is, essentially you can see the boats gathered in a very small fraction of the normal reservoir. And then a couple of years later, a very heavy winter and the near collapse of the Oroville Dam, or at least the great concern about that, as they had to switch from the regular spillway to an emergency spillway, and then that began to erode. Fortunately, there was a large evacuation of people from downstream, but in the end, it was disaster was avoided. And then on the right-hand side is from January 1 year before this January. This January was the fires, which is still much too close to be putting pictures of anything from the fires here in Los Angeles. But we got over 11 inches of rain. We measured 14 inches right in my neighborhood. And this is just down the street, a house that was washed by a mudslide off of its foundations, and the piano ended up in the street that you can see the pieces of here. And this is this switch between the drought and the flood and the high intensity rains and the circumstances that lead to higher probability of fire weather. That is something that has always been a feature of weather, at least in California, but it is tending to increase. And the sort of thing I want to return to at the end after some examples is just that with these changes, there are strong reasons, if this is happening and is going to be happening with more probability, you can't just sit with the same forecast systems that you've always had. All right, so I want to pick up a couple of things, sort of moving backwards to a study that came out right after the drought. It was led by Richard Seeger. NOAA funded. This is from a NOAA task force that he was the chair of on the causes of the droughts. And I'm just picking out one tiny piece of that study, which is pointing out in the time series here, year by year in the black lines, you have the precipitation for each water year for all California for records going back over a century. And you can see that there is considerable variability through all this time. And the pink is the 7-year average. But one of the points is that the seasonal average does not show much trend. This is something that even in a warming climate is expected from our climate models. California sits in the node between where you expect decreases in precipitation down in Mexico, Central America, the Caribbean, and increases from Northern California, Oregon, north into Canada. And so this, lack of trend, but we've had volatility for a long time. And if you look at the sort of particular years that went into that drought, they were dry, but not by themselves extreme, although the sequence of them ended up on the extreme side. But here's something from a colleague now at UCLA, also funded, among other things, by the National Oceanic and Atmospheric Administration, among others, Park Williams. On top of that natural variability that would have given drought, but not unprecedented, another factor that has long been known to influence the way your ecosystems and your agriculture and other aspects of your human impacts experience the drought is through the soil moisture and the amount of water that's available in the soil. When you have warmer temperatures, you can evaporate more quickly, or when you do it through plants, it's referred to as evapotranspiration. So a long-term temperature increase will exacerbate all the effects of a decreased precipitation in the years when you have less of it. And on the left here is 3-year averages of the observed California temperature in black, and then running the long-term average of multiple climate models that include the effects of human-emitted greenhouse gases, with this warming over the recent decades here being attributable to the greenhouse gas change. Now, this isn't to take I've been teaching this material in a bipartisan way for years. Climate science tells you that if you increase greenhouse gases in the atmosphere, you're going to have a long-term warming. The first statements of that. For instance, the Charney Report in 1979, where before this really noticeable trend occurs. And depending on your views, you might decide to do something by reducing emissions, or you might simply decide to adapt to those changes. But if you decide towards the adaptation, you definitely want to be able to have these systems available to deal with that adaptation, such as it's possible. And in this case, in Project Williams' study, the evapotranspiration, or the potential evapotranspiration, if your soil moisture were able to keep up, or if you were irrigating, weighed in at about 30% of the contribution to the drought for a measure of drought that takes the soil moisture into account. So we had the natural variability within its range, more or less, that would give drought, but not completely unprecedented. And then on top of that, this long-term warming trend that just keeps pumping up the effects. Now, let me just show an image of a El Nino year. This is the 1998 very large El Nino that was the one that, the first one that was really predicted by major weather centers, including the NOAA Center, thanks to methods that were developed in the universities, including my group helped contribute to the understanding behind that. Down below is the accumulation over the winter, running a total of the precipitation. So all the storms that you see coming across from the coast of Asia over here across to hit California during the El Nino year, or tantalizingly come towards California and then head up to Washington State and Vancouver, missing California. These are examples of the year-to-year variability, both due to climate variations and to natural weather variations. In this case, the 1998, you've got an El Nino down in the tropical Pacific, which is out of the picture down here. But it's warming the tropics and creating a little addition to the jet stream that's helping to steer the storms across. During the drought years, it's not something that's really easily attributable to an El Nino or La Nina, or in fact, other major SST indicators. It seems to be more of an internal variability thing, but a persistent ridge just off the coast essentially slowed down the delivery of the storms by the jet stream towards California and enhance their normal sweep up towards where you get a lot of rain to the poleward side. So these are examples of natural climate variability giving you swings that you can then exacerbate or change slightly if you're warming the climate. So still with the California, and giving an excuse to talk a little bit about where the word whiplash came from, I'm going to show a couple of slides from a paper where Alex Hall's group and my group got together, Daniel Swain, Baird Langenbrunner. Baird had a bunch of analysis ready to go. Daniel had a bunch of background to contribute. And there was a lot known about the potential for flooding in California because in 1861, 1862, Sacramento was essentially under a lake. It was almost an inland sea, hundreds of miles long. And in LA County, there was also lakes on the order of 10 miles. And a number of previous groups had done estimates of what if there was such a storm currently, and they would total for California losses in the hundreds of billions to getting towards $1 trillion. So sometimes called the other big one. In getting ready to study this, we realized, thanks to this previous work, that you can't just prepare for the wet extremes. In particular, if you are a water manager thinking about what to do with your dams, if you're coming out of a drought, your tendency would be to keep as much water as possible in your reservoirs for the next summer. But you have to allow for the possibility that you could have very large inputs of water, in which case you get into the Oroville Dam type scenario where you can have too much of what would normally be a good thing. So we were working on a way to, and I'll show a couple of slides just of these changes, but how to communicate this volatility. And I suggested the word whiplash and advocated that we put it in the title, which we did. A reviewer made us take it out, but it has since caught on in a couple of variations because it expresses the fact that you can get both sides of the extremes. You have to prepare for both. So this is a couple of the examples of what you do if you take a large number of runs from, in this case, a particular climate model. It's funded by the National Science Foundation as the lead agency, from the National Center for Atmospheric Research, Community Earth System model, the large ensemble. And if you, for instance, take a measure of wet day extremes, like the 1 in 200 year event, and ask in pre-industrial times, and ask how often would that recur cumulatively year by year, and just starting it, at what was then the present. The dashed line here is the cumulative probability of having such an event again, if you just had the pre-industrial probability. But both in Southern California and Northern California, your probability increases substantially more quickly than that when you have this warming factor, so that when you get wet times, you have more water vapor in the atmosphere, so you can rain out more water vapor per event. So getting the types of things that would have been 1 in 200 year return time before the warming is now increasing. And the number of these 1 in 200 year events you would get between 2018 and the middle of the century, the median lines here roughly say it becomes about as likely as not with ongoing warming to have such an event. But you also, if you create a similar measure for dry seasons, and there's a map of the occurrence of these dry times, it's skewed towards Southern California. You would have mean change towards drought down in Mexico, Central America, as with ongoing warming. But the probability of dry times over both, especially Southern California, but also Northern California, also increases. So you can make up different indices. Here's a particular one where you're looking for, say, a dry to wet precipitation change. And this is without even including the soil moisture effect on the dry side. And your probability of having a sudden switch between a dry to a wet year that would both be regarded as unusual increments with time, as well as the change in the wet years. Okay, so let's switch to things in current climate that we can do to try to improve our ability to say, how do these different events depend on the the factors, the meteorological factors, including the temperature and the amount of moisture that implies that the air can hold. So one of the things that we have in a current research project, this is a paper led by Wei-Ming Tsai, and a longer author list down here. It's funded by DOE, and part of the things I'm going to show you are funded by NOAA to look at the environments of some of these events. So you take features or weather systems like fronts, atmospheric rivers, mesoscale systems, and low pressure systems, which include tropical cyclones. And people create criteria for tracking each of these. And what's being done here is to combine those criteria so you get multiple features tracked at the same time, and you can look at the co-occurrences. The squares are regions surrounding the centers of the low pressure systems. The blue are tagging the atmospheric rivers. The fronts are shown as the lines up the middle, and you can see, of course, since every atmospheric river has a low-level jet that is associated with a strong temperature gradient, that's basic dynamics, they all have a front embedded inside them, so those co-occur frequently. But the interesting thing is mesoscale convective systems, they're identified by having high cloud with a cold area of cloud at the top, but heavy precipitation associated with convection inside. And those very frequently co-occur with fronts and ARs as well, and are often associated with the most intense precipitation. So, so you can tease these things out. This is just an example of, what if you say region by region, what is the the type of weather system or the most common combination of weather systems for extreme 95th percentile rainfall. And you can see big patches of the ocean here where you're getting the leading one being a combination of AR front and MCS. You move over to the center of the US here, and the leading one is the combination of front and MCS. There's tends to be a little less water vapor, so it doesn't quite make the criterion for atmospheric river typically. And down here, you can do these sort of breakouts of the fractions just so you get a sense of how important the co-occurring systems are and how much they show up in the heavy precipitation. And then you can do things like, for instance, just to not always be about California, but here's a system that's identified as front AR MCS in this region off the East Coast here. You can see there's a classic cold front up here. And if you take an average sort of a cross section across this event and look at it in the vertical here, with pressure is down towards the surface here, so this is essentially like height, and then going across that event, you can see the very deep vertical motion that you would expect for a mesoscale convective system, looking rather much like it would look even if it was occurring by itself without a front, but being fed by the air that's coming up in the frontal system. But you have, if you do a measure of convective instability, it's quite unstable in this region, so you're able to get the air going very deep. All right, now I'm going to switch for one slide just before wrapping up we care a lot about the probabilities of these extreme events. And I want to show you a way that we tend to characterize these probabilities. You can think of it as a histogram or a normalized frequency. How often does a particular type of event occur that has a precipitation that's, 1 millimeter per hour, 2 millimeter per hour, 3 millimeter per hour, and so on, up to 20, and then 40, and then 60, and then 80, and 100 millimeters per hour from observed rainfall from basically a NASA data set that combines multiple satellite retrievals, multiple satellites from multiple agencies. And this is subdaily precipitation. So we're looking at the type of intense precipitation that caused that landslide. So usually this black line is showing the total precipitation. These are different regions, like one in the Western Pacific, one in the East Coast of the US, one in the Southeast US, Western continental US. Let's go with the Western Pacific one here for a moment. The there's a range where you are going from the sort of, average-ish precipitation that you could get used to on a rainy day on up, from say 20 millimeters per hour up to many times more than that. And the probability, which is shown in this axis by powers of 10, is dropping as the precipitation increases. And you can essentially give a scale to how this decrease happens. So for a given drop in probability, how much does your precipitation have to increase? And you see that as this slope here. And if you look at the Alder rain, or you look at the combination of low pressure systems in MCS, or just low pressure systems over in the Western Pacific, they all drop in very, very much the same way here. This is essentially typical of convective, heavy convective rainfall. So your probabilities of the individual systems are behaving similarly. That's pretty good news. Now, in the East Coast US, it's not quite as perfect as that, but the main contributor to the severe precipitation, which in this case is front AR MCS, is dropping in much the same way as the total precipitation. And if you switch to the front AR atmospheric river combination, it's dropping not that much faster, and they have very similar behaviors. So another thing you can ask, and this is work by Suchin Zhuan that's not published, and I'm just going to give one indication. You can ask, how does this depend, how does each of these systems depend on the moisture environment? And the answer is you can combine, AR fronts and fronts ARs and versus MCS only versus combinations, and look at the way the water vapor in the environment and its contribution, not shown here, to those probability slides. How does it change similarly, differently? And the answer is basically very similarly for all the precipitation phenomenon. So if you increase the moisture, the temperature will lead to an increase in the moisture your air can hold. It tends to change the probability of extreme intensities for all of these types of weather in a rather similar way. And that brings me around to sort of a repeat of my original slide, but just with a slight variation. There are lots of impacts, and have long been huge impacts, of extreme weather events, from the drought side to the intense rain and flood side. When we experience warming, as we have been for decades and are likely to be in the future, since we're not rapidly changing the input of greenhouse gases to the atmosphere, we need to be able to keep track of this. And if you're not doing the type of research that allows you to jump in and say, I need to represent my convection that's going into mesoscale systems in a different way to improve the most intense rainfall part, or I need to be very careful that I'm representing in my weather model or climate model the effects of soil moisture decreases properly. If you don't have those in your systems, our ability to keep society apprised of these events before they happen or as they're approaching is going to be more and more limited going forward in time. Now, I do want to just switch and mention that, this research, the examples here from fabulous young people that I've had the pleasure of collaborating with in different studies over the years, there is going to be dramatic challenges to keeping this system going. The people who work in this system are highly committed to it and very enthusiastic. It's just delightful to work on these things with everyone. But for instance, the NOAA funding, we have a grant in my group that was awarded a year ago, and with fiscal year 2024 funding, and is sort of in limbo. We have no idea why it is, but it's, you know, if it doesn't show up, that will be extremely challenging for us to do some of the types of things that we're doing, in particular for delivering to the NOAA weather and climate forecasts some of these measures for improving the forecast models. That's precisely what the, you know, that grant is about, is like making these things available in a way that's easy to digest for people working on the forecast system itself. So it's a time where, if you care about knowing in advance that you're going to have an intense rain that might cause a mudslide in your backyard, or on the dam upstream, you really would want to be supporting the weather and climate sciences at the national level. And so I think I'll wrap up my set of you know, formal statements here, and I think the next thing is questions.
Great, thank you, David. Thank you for ending on that note as well. We have a question from Kelsey. So a bit of a broad question, but are there any infrastructure improvements that can be implemented to mitigate the effects of these whiplash events on our communities?
Yes, that is a great point. And one of the things is that this, you know, things like having, you know, just drainage regions to put flood water. This is something that many communities know about and work on, but you need to, if you're trying to decide what you're preparing for, you need to have a sense of what's the probable event. Do I have a soccer field that I need to convert into an emergency overflow region? Well, how much water are we likely to be talking about in a plausible case? So being able to refine these statements for that community planning level to turn over to the designers and hydro managers is really important.
Great, thanks for those insights. I have a bit of a science question. So I was really interested in the tracking algorithm for the ARs and the MCS storms that you were showing. And you talked a little bit about how with like a warming climate, we expect there to be more water vapor and like maybe more intense rainfall events. I was wondering, with your tracking algorithm, like, are there expected to be any shifts in the location of the ARs as well, the atmospheric rivers?
Yes, and so the tracking algorithm used here is known as TICA-BARD, and that's Travis O'Brien and his group have been running that. In this particular effort, which is very much coordinated across universities, including Indiana University, where Travis works, and some of the DOE labs. So it's just combining several existing tracking algorithms. So like the mesoscale convective systems, that's PyFlex tracker from Zhifeng and Ruby Lung, and the LPS are being tracked with tempest extremes, and so on. So it's the combination here. Now for the changes in region, that indeed can happen. We haven't, in this study with the multiple things tracked, we haven't looked at that, but as far back as, was it 2013 or so, maybe 2015, we showed that the type of thing that happens during El Nino, where you get an extension of the jet stream, that type of shift to the jet stream can happen under global warming. but it's one of the things that is less certain with current systems, partly because the changes in El Nino themselves, or El Nino-like ongoing changes, are less certain in the climate models. It's an area that, yeah, this is the sort of thing when you get down to the regional specifics and details, you're working your climate models harder and harder to get more and more specific about these regional effects. And that's something we can do, but we can't do it without support.
Right. And one last question from Sydney. So Sydney asks, are there any links between like thinking about weather, whiplash, and extreme weather, and then other natural disasters like earthquakes in California in particular?
Yeah, so people often ask about connections between weather and earthquakes, and the answer is mostly no connection. It's very common for people to have a sense of what might be earthquake weather, but it's usually turns out to be what the weather was during the last big earthquake. The solid Earth isn't very much affected by the weather. On the other hand, there are some little things about, like, if you're affecting the groundwater a lot, or the subsurface structure, for instance, like fracking is not weather, but it can affect the subsurface hydraulics. You can have some impacts that along that lines, but mostly the answer is not connected.
Super interesting. Thank you. So that's all we have time for with Professor Neelin. So everyone thank him again in chat.
Yeah, thanks. And I want to thank you for all, everyone who's been involved in the hosting. Such a great job. I've had the pleasure of listening to a number of
Oh, we're
stretches.
so glad you've been enjoying it.
Mm-hmm. Yeah.
All right. So we have a surprise for you guys. Let me grab. I promised Kelsey something. I'm so sorry you've been sleeping. Oh, this is not the cat from earlier. Actually, this is a different cat. I'm so sorry, Kumo. His name is Kumo. It means cloud. We have a surprise lined up. I too am being surprised right now. I don't know what's happening.
Hey, Andrew.
Hey, Nadir. How do I turn this
How's it
down?
going?
I don't know how to turn this down.
It's late.
It is late night.
It is late. I mean, for folks on the West Coast, I don't know, 12:30, but over here on the East Coast, it's late.
I don't think I've ever been awake this early, actually. 3:38. I did not know that the clock showed these numbers. I'm scared. I'm confused. Please send help.
I mean, 100-hour live stream around the clock, no gaps. It means some sacrifices have to be made. And boy, wow, look at that.
And boy, were they willing to sacrifice us.
Yeah. And I don't know who's making more of a sacrifice, if it's us or our viewers. But maybe it's just all the way around.
Yeah. Let's. Is there any reaction? I'm wheezing by Kelsey.
So now,
Kelsey, you look after if that's asthma. Look after it. I don't know what else it would be.
Also, I hope you signed the waiver, because we're not responsible for that.
Yeah, sorry about that.
Yeah.
Cheering, clapping. Yo, 80s vibes. Yeah.
All right. I think they like it, Andrew. I think they're
They
into
like it. You should know that Nadir is actually in a yacht rock band.
All right, now I have to put the website in the chat here. I mean, I wasn't going to self-promote, but that is why I have this outfit. Okay, there we go.
Yeah. Oh my New York City.
Who did that? There's too many people backstage who are too good at Googling.
Whoa.
This is not good for my reputation. All right, we're going to need everyone to
Can we
log
like
on.
zoom in? Can we actually get a little bit closer in on that?
I don't think so. I think we need to move on.
No, Nadir, there's some education that needs to happen. Someone doesn't know what yacht rock is.
Oh, is it that they don't know what it is, or they're just very surprised? I think people in the chat can explain.
Yeah. But
I think people's minds are blown.
I think this is the appropriate response to what's happening right now. I think.
This is what happens at 3:30 in the morning East Coast time.
Yeah.
So we've got quite a program here for you. We've got special guests. We've got musical entertainment. We've got our favorite climate data sets, which doesn't sound that fun, but it's actually going to be pretty fun. And so we're going to get to all of this because we got to fill a bunch of hours, people. And so we're gonna do this. Andrew, so it's so late. What was your approach to staying up this late? Did you go to sleep or you just stay up?
I went to sleep. I'm not sure if it's helping me or not. You know, yeah. But the thing was, I finished my host. oh, buddy,
you set yourself up for that one.
Yeah. Oh, wait. No. Give me a second. I have like literally 50 photos of Nadir sleeping. Like we are going to show those at some point. But I finished my host segment and I was like, oh, I'll go to bed. But we had such great keynotes. I had to stay up for Dan Swain. I had to stay up for Zeke, talking about why 2023 was so warm, 2024 was so warm. So
good.
Yeah. Oh, there we are. I don't know who's putting these up now.
Yeah, we've lost control. I think there's a chaos gremlin backstage.
Yeah.
And we were warned that this would happen. So there you go. So you thought you'd go to bed, but then the stream was just so entrancing, right? There's just
exactly. Also the TV is gone upside down, as is everything else right now.
Oh wow, that's the chaos gremlin again.
Can we make Andrew go upside down? Is that possible?
Oh, I think I don't want the stream to crash. I feel like this
technology's not there yet.
Yeah, exactly.
Yeah,
like
you just dared, Lily. You just dared the chaos gremlin, and I'm afraid.
They were so obsessed with what they could do. They never stopped to ask what they should do. But yeah, and then I was like, I got 2 hours, and here we are.
There you go.
Yeah. What about you, Nadir? Did you? I hear terrible rumors that you have not slept yet.
I have not slept because I don't even have a time zone right now because 24 hours ago I was in Seattle hanging out with Lily at the University of Washington and Stella, who's backstage, and then I took a red eye, and then straight to the live stream. So I'm not even sure what's happening right now. That's where I'm at. Well, should we show these people some data? They're staying up late with us.
Yeah, but I think we know what to do when we want to see data right now, right? Or maybe Nadir, I think you may have missed this, but Jared had this thing that the chat has to do now if they want to see some data.
Oh.
So if I go like this at the chat, what are you going to say? Show me the data.
That's right.
Show me the data. We don't have Jared's level of.
All right, I'm getting a couple all caps data.
Oh yeah.
A few more.
Shannon, right. You know where it's at. Sydney, yeah.
Except the thing is, Andrew, is that, as the climate's a coupled system. We got the atmosphere, the ocean, the land. You and I were atmospheric folks. And we probably should show some ocean data. But to understand that, we're going to need an oceanographer.
We're going to need someone to help us out with that. Do you know anyone? Do you know an oceanographer who would be up at this terrible hour?
I know this guy in Scotland. And
I don't know about that.
It's not that early, and maybe he's. Do you think he might be around? Let me check backstage. Is Graeme backstage? Can he come out? we have Graeme?
Graeme, come out to play.
Graeme, you're muted.
We got to unmute Graeme. There he goes.
Classic rookie mistake.
Graeme, welcome to the GeekFest.
Thanks, folks. Nice to be here. What a wild ride this is.
We don't even know what's happening. So Graeme, tell the folks who you are, your qualifications, how you know us, and then what's going on your T-shirt.
For sure, yeah. I'm Graeme MacGilchrist. I am in Scotland, as Nadir says. Unfortunately, I do not have my bagpipes and kilt with me right now, as I'm sure everyone in the chat will be disappointed to hear. So I'm based at the University of St Andrews, which is in Scotland. It's just a little bit north of Edinburgh. I am an oceanographer and climate scientist. I know Nadir in particular through time that I spent in Princeton and GFDL. I was there for 5 years, from 2018 to 2022. No, 2023. That's 5 years, isn't it? And then I moved back here a year ago, and now I'm here. And so the T-shirt that I'm wearing, I don't have a bucket hat, but I do have. This is the GFDL Fun Run T-shirt. I think this was from 2021, maybe, or something like that. It's got the same graphic that's been on it, I think, for about 30 years or something. I don't know.
Amazing.
So I don't know who these are meant to be. I don't know if this is Nadir, or you the tortoise, or the hare, Andrew, are you either of these? I don't know. That's me. And I don't have a bucket hat, but I did actually just look to my left, and I have a hat. And now I know this is a non-partisan activity, but this is my only hat that I have here. So
that'll do.
This did just actually happen to be lying right next to my computer. So this is my Philly Eagles hat. So I apologize if that triggers anyone or upsets anyone, but
Awesome. I love it.
Amazing. The shirt again, that's a picture of GFTL as well, right?
That's right. Yeah. So
you lift your shirt a little bit so the camera can see it?
Oh god.
That's right. Yeah. The building is in the background. That's the main building of GFDL, and then the fun run, the 5K fun run, happens around the sort of campus area in that part, and it ends right in front of the fun run. So
Whoever's working the screen is getting high off power. Wonder who that could be.
That is definitely true.
He is definitely getting high off something right now. That is.
All right, so we promised them some data. So should we show them some data?
Should we do clouds or should we do ocean?
Maybe let's do clouds first, because oh, come on.
I like clouds as well. I'm fine with clouds.
All right, let's do.
Because Graeme, we taught clouds when you taught that course at Princeton. So I know you know a little bit about clouds, and so
that's right. I'm basically a cloud expert. Everything I know about clouds, I learned from you, Nadir, in that one second-year undergraduate course. So, here we go.
Wait, can I just say we got someone saying, "Wait, is it Nadir?" The disguise
he
is
hasn't learned that power yet.
Do you need to share a tab, Andrew, or do we have it as one of the videos?
Or I think I might share a tab. I think that'll work better.
No, share a tab. Share a tab.
Yeah. Give me 1 second. So we have.
So for those of us who saw Isaac Held's talk on Friday night, which I hosted without the glasses and the hat, we talked about these infrared. The infrared radiation to space. Oh, there we go. Look at this. Look at this.
This is beautiful.
So this is real, people. This is not a simulation. This is not made up. This is geostationary satellites, which sit above the Earth at an altitude of several tens of thousands of kilometers, and they rotate with the Earth, so they stay above the exact same spot. So they can just take pictures of the Earth at different wavelengths every 15 minutes or so. So you get excellent temporal resolution. And this is actually, somewhere between a half a dozen and a dozen different geostationary satellites stitched together to give a global view. And what we're seeing here is infrared radiation, so which is thermal. So things that are cold emit just a little bit of infrared radiation. Things that are warm emit more. This is kind of like your toaster oven glowing red hot, but something that's really hot like the sun glowing white hot. This is the analog of that, but just for the temperatures on the Earth. So the white stuff that you see here are high clouds that are cold. The darker colors are things that are warmer, like the land surfaces. You can see the diurnal cycle going right to left as the land surfaces warm up. If you look at, say, if you look at the Sahara, you can see it warming up with the diurnal cycle. And, Isaac also showed this in his talk, and you can just stare at this forever. So, we're not going to take forever, but I thought we could just look at this and, maybe take turns. Oh, we got to loop this. You know how to do that, Andrew? Go in YouTube and I think you right click.
No, it is looping. Sorry, Cleo was asking to leave the room. So
I see. Okay, we have to pause. Good. All right. So yeah, Andrew, what should we talk about here? Let's riff. What do you got?
I mean, I think it's kind of amazing to see that so like Nadir was saying, you have this kind of, you see this wave of black colors that's moving across the screen. So like in this color bar, black means hot and white means cold. So this is showing just the sun moving across the earth and warming up the land as it's going. So you can see that places like Australia and the Sahara, every 24 hours are just getting really, really warm. And a little bit after that, if you look, so maybe where should we look now? If we look at Australia down here, you can sometimes, maybe right now is not the good time of year to look at this, or maybe what's a good time? Maybe over the Amazon. So if you look over the Amazon, over South America here, you can see that after the sun goes over and it heats up the land, you get a huge explosion of white. And that's because a couple of hours after the sun comes over, you get tons of thunderstorms to get rid of all that extra energy that the sun has just dumped into the earth right there. So as it goes over, bam, and then bam, explosion of cloud. I think that's, you can really just see this stuff in the data as well. It's kind of amazing.
Yeah, and so I guess those afternoon thunderstorms kind of typically occur, it's like late afternoon, right? Like 3, 4, 5 o'clock, just after the peak. Peak temperatures are maybe 2 o'clock, something like that, 2, 3 o'clock. And then the thunderstorms will peak right after that. Nice hat, Lily.
Love the hat, Lily.
Keep that there. Graeme, anything in here you wanna talk about?
Clouds to me are just an annoying thing that blocks my view of the ocean.
Wow,
so
sorry, non-partisan event, Graeme. Not partisan.
Yeah, sorry, I'm not trying to cause controversy. I was just thinking about the fact that one of the things. So I study a lot to do with the biogeochemistry in the Southern Ocean. So we try to see the surface of the Southern Ocean, and one of the main ways that we get at the biology is by looking at the color of the ocean. But of course, when there's clouds there, as you can see, the Southern Ocean is just covered in cloud cover most of the time. It means that you can't see the ocean's surface, and so you have to do a lot of data filling to try to see through it. But it does. I mean, you see just how beautiful these swirling structures are over the Southern Ocean in particular.
Yep.
Yeah, it's the cloudiest place on Earth, right?
Unfortunately for the ocean biogeochemists.
Andrew, do you have? Can your mouse go over the video?
Yeah, it's going over the video now. It's not so easy to see, but you see I'm over the East Pacific now.
Oh, that's a little guy. I thought that was like. Oh, there you go. Yeah. All right, so keep your mouse there. So Andrew's the mouse is kind of right in that central equatorial rain band. So if you look right across the equator,
I'm on the left of the screen.
Yeah, you should see this band of convection that goes across the Pacific, across the Atlantic, coincides with this pulse of cloudiness, this daily pulse of cloudiness over the rainforest. So that's all part of this intertropical convergence zone. And it's so narrow relative to the rest of the tropics. Isaac was talking about this too. You have these broad areas of the subtropics, just north and south of that equatorial band, where you don't really see much cloudiness at all. You can see that in the Atlantic. You can see that in the East Pacific, just these regions where you don't get much high cloudiness. You actually get a lot of low clouds, the sort of low stratus decks, the marine layer. Folks who are familiar with the West Coast, you get that marine layer. You get the June gloom in LA, that kind of thing. But you actually can't see those clouds in this data set because those clouds are near the surface and they're warm. They're about the same temperature as the surface. So you can't really distinguish them. So the clouds that we're seeing here are all the high clouds that are way up high, near the top of the layer of the atmosphere that has weather. kind of minus 50, 60, 70 Celsius.
Mhm.
That's what we're seeing here. And
Yeah.
so yeah, you're just seeing that band of convection. Got anything to add there, Andrew?
Well, I mean, so right now, so we have this clock ticking up top here. So this is August, and August is when we have, like, say, the monsoon, and we have other things which are shifting this band of rain, which we call the ITCZ, was shifting it north. And so in summer, this thing shifts north, and in winter, or at least in our winter, it shifts south a little bit as well. So I think if maybe I skip forward a little bit.
Yeah, do that.
What's a good timestamp here?
We can go to the beginning. The beginning's January.
Yeah. All right. So let's hop back and forth between here. So you can see now, like, if you look over Africa, this band of rain is a lot more south. It's over more of the Congo than the Sahel. You can also see there's a lot more convection over Australia than there was previously, and you don't really see this band of rain over the East Pacific anymore. But if I shift, so I'm going to shift back to that July thing. Suddenly in July or August, everything is shifted upwards. So over Africa, these white splotches are way further north now. You can see, and then you see this band of rain. And yeah, we have Fish who says, I think I can kind of see the Andes. And yeah, I think, and if you look over the edge of South America here, you see this persistent, someone correct me if my geography is wrong, but I'm pretty sure this is the Andes right here.
I think so.
You see this persistent thing where you have lots of white, lots of high cloud. I think that's probably like orographically driven. Like, so you have a lot of wind which is pushing air upwards over the Andes, and it's forming cloud. And that cloud is just very cold. So you're getting a lot of white here in the color bar.
Exactly.
I have a question.
We'll allow it.
For the climate dynamicists amongst us. So when people talk about the cloud feedbacks, the potential that changes in clouds could lead to changes in the warming. Well, you could have kept the video up. It's related to the video. So people often talk about the fact that, right, so these high clouds that are very cold changes in those high clouds will change the radiation balance with the Earth. People often, or my impression is that people are mostly talking about low latitude high clouds, so like in the tropical convection regions, the things that you've been pointing out in terms of across that equatorial band and across the Amazon and in those sorts of areas. But when I look at this, I also see a lot of, let's say, high clouds or cold clouds in the high latitude regions as well. So in the subtropics and over the North Atlantic and over the Southern Ocean and these sorts of areas. And I recognize that these are just colder regions anyway, but I see a large difference between the clouds. You can really see the prominent high clouds moving over clearly a warmer ocean underneath it, particularly in the Southern Ocean, or a warmer land underneath it. So is there any expectation that high latitude, high altitude clouds, if that's not getting too kind of obscure, are also going to change in an average sense and lead to some changing climate dynamics? Or is it really just people thinking about the things that are happening in the tropics and in the equatorial regions?
Graeme, I think you've had too much sleep and you're asking sensible questions. This is a late night session, man.
We may have to kick you for that. I think banning is on the table.
Is that a party foul to be bringing too much?
Yeah, we may have to move on from that one.
I do forget that it is 3 a.m. I'm ready to go. I'm absolutely.
I know. That's like you got that Scottish sun beaming down. So Graeme, we do have an ocean animation that we're going to want to look at. But actually, right now, we have a special guest lined up for this time of night. A special musical guest. So maybe we can we bring Dargan on? Hey, Dargan.
You're muted.
Hey, how y'all doing?
Woo!
Right.
All right.
Let me introduce Dargan a little bit. Dargan Frierson is a much beloved climate scientist from the University of Washington, a student of Isaac Held, who we heard from last night. And Dargan's known for a number of things, just being one of the coolest dudes in our field. he was originally going to have the 3:30 a.m. slot, and then we said, "Can you come at 4?" And he said, "It's fine. I'll just move my 4 a.m. and I'll I'll just move my 1 a.m." And Dargan is famous for his songwriting skills in the field. So Dargan, you teach a class at UW, right? That is aimed at a general audience, and each lecture has a song. Is that correct?
Yes. Yeah, we do a lot of songs. Yeah, this is a real UW tradition, actually. Every winter before the break, we have a winter party, and all the musicians torture all the non-musicians with their horrible singing and stuff like that. So yeah, it's great. It's good to be on like the microphone side of things rather than the audience side of things.
Yeah. So are you going to torture us in a similar fashion?
Oh yeah. So y'all asked me to be on this, I guess, Friday, right?
Maybe 24 hours ago, maybe not.
Yeah. So I took the IPCC 6th assessment report.
No way.
And I set it to music.
Oh my God.
Yes.
You did this since we asked you.
3,949 pages.
Nice. And that's going to take us through to 6:30 on Wednesday.
This is like the climate equivalent of like
y'all said
the B-movie
15 to
script.
20 hours, right? I heard that I was supposed to cover about 15 to 20 hours. No?
Yeah, it's great that
yeah. Anyway, I have 15 to 20 hours of music ready to go if y'all want to hear it. But yeah.
What key are you in? I've got my harmonicas here.
Nice. Yeah. Key of G.
Here we go.
Yeah, so I got my mandolin. It says Dargan on it.
Oh, no way.
Yeah.
Custom.
Is that a custom job?
Homemade mandolin. That was my PhD graduation project present for graduating from GFDL, Princeton, right? NOAA, where I was very happy to have support from National Science Foundation and to be at that just spectacular NOAA lab. This one of the centers of the field. So allow me to get my little 3,900 pages of notes here ready, my lyrics, and well, maybe I won't do the whole thing for y'all now, but I'll do the beginning. So here we go. This is the IPCC Summary for Policymakers headline statement. Here we go. It is unequivocal that human influence has warmed the atmosphere, ocean, and land. Widespread and rapid changes on the atmosphere, ocean, cryosphere, and biosphere have occurred. The scale of recent changes across the climate system as a whole, and the present state of many aspects of the climate system are unprecedented. Over many centuries, too many thousands of years, la 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 la, la 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 la, la 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 la. Human-induced climate change is already affecting many weather and climate extremes in every region across the globe. We've seen increased heat, floods and droughts, tropical cyclones, and their attribution to industry, mostly fossil fuels. I'm paraphrasing now. Learned a lot about the present and the past, and the climate sensitivity's about 3 degrees. We also know how to stop it. Stop burning fossil fuels. And if you ask me, we need the Green New Deal. La 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 la. La 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 la. La 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 la. right. Thanks. All right. I'm going to switch to the actual chat here. Yeah, cool. All right.
That was amazing.
Amazing.
Amazing. Wow.
You might have included a little editorial in there. I like that.
Yeah. Sorry about that. Yeah. I couldn't think of, that was in, I actually sang that to the winter party a couple of years ago when it was new. And yeah, couldn't think of anything else to say. So
I love it. Very apropos.
That's my own opinions as a citizen, of course, representing any kind of other stuff.
I mean, Dargan, I haven't even taken your class, but I actually know a couple of other songs that you do.
Oh, you do, eh?
I do. I don't know if this was, from the Gordon conference one year or when you came in for Isaac's retirement, but I remember a song called Albedo to the tune of Albedo.
I do have a song, Albedo. Yeah. So how many in the chat know what albedo is?
Talking about albedo a little bit. So people have heard the phrase albedo.
Yeah.
Who on the chat remembers? Spell it out for you.
Whose cat has the highest albedo? Lily's has partially high albedo.
He's a cloud, so he has pretty high
the
albedo.
cloud. That's a good sign, right? So albedo is the amount of sunlight that's reflected from something. Yeah. And things that are white are high albedo, right? So like cloud surfaces, sunlight, ice surfaces, right? And, y'all might think that we sing in the class for, fun or, climate anxiety relief or something like that, right? But it's actually just for educational purposes. And I think we can all agree that songs are only good if they're scientifically accurate, right? So, this actually helped the students to learn the concept of albedo. We have documented evidence of this. Where
and
more
is that just like when we learn the alphabet, when we learn the 50 states, like we learn them in song form, right?
Exactly. It helps remember stuff, right? So albedo, there is we have questions on the test that are like, is it high albedo, is it low albedo, right? And so next I'll sing that one for y'all. And we can get the double effect of both. Hopefully you'll remember that albedo is high for clouds and ice and things like that. And it'll also hopefully ruin the Jackson 5 song, I'll Be There, for you.
With any luck.
Here we go. Sheets of ice and snow packed, they reflect radiation back. Where there is ice, albedo. Tiny droplets in the sky, cirrus stratus way up high. Where there is cloud, albedo. Albedo, albedo. Where there is white, albedo.
Hello.
Albedo to reflect you in a world so warm and bright. I'm so glad you bounced that light. Where there is white, albedo. if your city skies are never blue, with air pollution all surrounding you, scattering light, think albedo, 'cause at least that haze is keeping you a little cooler. Albedo, albedo, where there is white albedo.
Phenomenal.
It's just brilliant, man.
I think get this man a Grammy. Oh yeah.
Yeah.
I mean, Dargan, I don't know if you can see the chat, but they're.
I can. Yeah. I'm watching the chat. Yeah. Thank y'all so much.
Yeah, they want it on Spotify.
Yeah.
They
Yeah.
want you a Grammy.
There's some out there. There's some YouTube clips of me playing in class, for instance, and some of it you can see the folks with like whatever website up on their computer, you know, not even really paying attention to the song, you know. But hopefully the lyrics are scientifically accurate, and me missing an occasional change doesn't, you know, chord change doesn't actually matter.
I love it. When did you get brave enough to take like what is obviously like, you know, a bit of fun playing mandolin, writing songs, and translate it into, you know, teaching things? What was the impetus there?
I would love to share this whole story with you. For instance, I was in a band in grad school that was made up of grad students. We were called the Jersey Sprawl, you know, because we were in New Jersey, of course, right? And the band was kind of sprawling as well, right? Like 15 of us or so, maybe like 7 on a given night would make it, right? Yeah, so got a little bit of experience playing songs, including goofy songs, of course. You know, I wrote one song called "I Ain't Gonna Pull an All-Nighter Again." And
did that happen? Did you manage to avoid pulling an all-nighter again?
I think I was pretty close to the last one. Yeah.
Well,
yeah.
And
another verse of that was "I ain't gonna sleep in my office no more," and I have not stuck to that. But I think sometimes it's good for one's, you know, health to take a nap sometimes in your office. Anyway, yeah. So there was that. The Jersey Sprawl sadly went the way that so many bands go, right? Like so many great bands have broken up because of, you know, the fact that their members got their PhDs and the other universities or, you know, government labs to go study more. Yeah.
I think that was the Beatles, right? As well.
I think so, right? Yeah. I can't remember which schools, you know, were involved there, but Liverpool Institute or something. Yeah. So there's that. But then with the class, I was very terrified to sing anything, and I had several songs written before trying to perform them in class the first time. But the last day of class, I decided, okay, let's do this. And I sang them all. And like the students were probably like, who is this guy? You know? But then like people clap and stuff, you know? And like you kind of realize that singing is better than not singing, you know? For me, at least, singing is way better than not singing. Because it wakes people up, you know, get some good science content in there. And I think too, like global warming, you know, can get kind of heavy sometimes, right? Like being a scientist and not feeling appreciated can get heavy, right? And what do we do when we're sad but sing about things, right? It's something that keeps us going, right? So that's. Yeah.
Yeah.
That's the story. And then after that, then I started singing them, and got more and more, like, students have written some of these, and other, like Mike Wallace, who spoke earlier in the stream, I think on Friday morning, right? He is very well known in our department for making up great songs that are atmospheric science themed. Like he did a man, a bunch of like Christmas, let it snow type songs, that describe the exact meteorological conditions of snowfall in Seattle stuff, and then another one is Dennis Hartman, also very esteemed scientist in our field. So I think having these role models who are also not afraid to have some fun, share some musical entertainment, yeah.
Do you play any other instruments? We have this question.
Yeah, I saw that. Yeah, I do. I have a lot of instruments here. They're not all in tune, but I got the electric guitar here.
Whoa!
It's not as late for me as it is for y'all, but it is 1:15, so I don't think I'm actually allowed to play this song. But you can watch. I'm like shredding underneath the camera here. You can't see, but
you can't see or hear it. But
the cat approves, right? The cat approves of the shredding. Yeah.
I feel a concept album coming on here, Dargan. A little collaboration, a little super group. And,
let's write it together. Chat if you got any ideas for songs and stuff. Let's write them, man. Yeah.
I appreciate, Dargan, what you say about the music as a way of lightening the load a little bit. I've always really enjoyed it. There's a regular meeting every couple of years called the Ocean Sciences Meeting, organized by AGU, and they always have a jam session, like organized at a local bar wherever the meeting's taking place. And there's a big, everyone goes along, anyone that can sing or play or whatever. And so you end up, you see, really esteemed oceanographers and climate scientists and whatever just standing up and playing like the Beatles or whatever, and it's just really, there's something incredibly joyful about it, which is just really fun.
Nice. Yeah. What's my favorite science area topic? Thanks for the question, Sydney. I right now I'm really into like climate futures, basically. So thinking about what directions we can go with emissions and things like that. I came first, my first projects for my PhD had to do with water vapor and more sort of traditional climate dynamics topics, but it's been super fun lately to think more about things involving climate justice and emissions pathways and stuff like that. Which are like both intellectually pretty fascinating, but also so important for society too, right?
Awesome. We also have so the chat, for context, I don't know how much of the rest of the stream you've seen, but the chat loves Argo. So I think at some point in the future, it doesn't have to be right now, but if you ever get a chance for an Argo song,
okay.
Argo
Yeah. Any ideas for how Argo could be in a song?
I'm coming up.
Yes.
I want the world's Argo.
Nice.
Yes.
Nice. Oh, I love this. Wow. Nice.
Yeah, Jonah, that's a gift, the heart opening as well. We need to find the full gift.
Argo, it's truly amazing, right? Like to be able to dive down to 1,000 meters, right? Come back up,
I've learned so much about we know about what's funding our specific branch of science sometimes. Like I know what's funding like the atmospheric, like in geoscience part of NSF and stuff, but I didn't know how much the US actually funded Argo as well. Like literally like 50% of these floats or something at 5 cents per taxpayer or so. Or do it for Argo. This is a high quality meme. It's a high quality.
Fantastic. Wow.
Yeah, Graeme, do you actually use Argo? Like,
Oh,
do you
yeah.
use that data?
Yeah, for sure. Yeah. And there's a big program launched. Well, it started sort of 10 years ago, actually based out of Princeton.
This is spoilers for tomorrow.
Oh, this high quality meme content. I love that. Yeah, so we use Argo all the time. I mean, both, directly just looking at the data. There's a PhD student that's working with me currently based down in Southampton who's looking at biological processes in the upper ocean. That's what I was going to say. So there's a program. So Argo since 2004 was just measuring mostly temperature and salinity of the ocean, which are the two key variables that determine the density and a lot of the dynamics of the ocean. But then about 10 years ago, they started putting more and more sensors on there. So they now measure oxygen and nitrate and PCO2, so carbon dioxide levels. They actually measure pH, from which they can derive carbon dioxide levels, and other things like that, like fluorescence and things that can tell you all about the biology and the biogeochemistry. And so we use that a ton now to get, just the total revolution in what we can say, particularly in far-flung parts of the ocean, which we had no data for. You look at the data that we had just in the ocean in general up until 2004 when we started chucking Argo floats in, and then just a total step change in the data availability. So yeah, there's no end to how valuable Argo has been. And then so that's you can use the data itself directly, but then it's also obviously being assimilated into a bunch of other data assimilation and forecasting products and these sorts of things as well, into state estimates to look at the how things have changed in the past, but also trying to get your forecast system up to the most accurate picture of the present day and then forecasting from there. So Argo is all kind of feeding into a bunch of that as well. So yeah, it's just absolutely revolutionary for ocean sciences.
I think we had Nicky Gruber at one point basically saying that like a third of his papers wouldn't have been written.
Yeah.
Without.
Yeah, absolutely. Yeah. And particularly for Nicky's stuff on the Southern Ocean carbon cycle and all that sort of stuff, so much that we just wouldn't even have a clue about. And the thing about these things is that somebody said to me once, or it's a kind of a famous aphorism or whatever within the field of the worst thing you can do as a scientist is start a time series, because then you got to keep it going because there's nothing more valuable than a sustained time series, right? So the minute you start collecting data, you're tying yourself into having to continue to collect that data because it's so valuable to just keep that going. And so all this data that's been collected, all the Argo float data, all the data of the Southern Ocean, the carbon cycle stuff, its value it keeps increasing. Step changes increases each further measurement that you get, each further day that you keep measuring it. So sustaining these things in the long term is just essential for continuing, not just to continue to say, to do fun science or whatever, but to continue to actually understand the system on timescales longer, as long as we can, and timescales that are relevant for, thinking about climate and climate change.
Like knowing how much heat the ocean is taking up and things like that.
Just a first order question that we don't yet have a real sort of solid grasp on, because we need to keep observing.
Mm-hmm.
So Dargan, we don't want to keep you up too late tonight, but I know you mentioned you have some slides. I know you designed some climate video games. I don't know if you've got other stuff.
Yeah.
Over here.
I was just kind of thinking about the Argo floats measuring like the scales within the ocean and how the ocean is kind of filled with vortices, right? Like really, really small length scales within the ocean as compared to the atmosphere, right? And it was kind of making me think about some of the concepts that we teach in GFD, geophysical fluid dynamics, or the courses where we learn about why there's so much spiraling motion on Earth, and concepts like potential vorticity come up, right? I like these words because they're very poetic, right? And absolute vorticity is another one, right? So it made me think about whether there are conservation laws for these things, meaning like it can't change. Some quantities just stay the same, or very other parts compensate in order to make things spin around in certain ways, right? So I've got a song about this, which is called Absolute Vorticity, but it's absolute spelled like the vodka. Right? And this has a conservation law. I can only play this on late night, GeekFest. But this is about a different kind of conservation law, where if you drink it, then the room spins around. So here we go. My friend brought me a gift last night. It was a bottle of vodka he said was all right. Said it was distilled at a high latitude. He said, take a drink, I didn't want to be rude. So I felt the world begin to spin. I lay back and felt the relative motion. Getting dizzy like I took one on the jaw, 'cause I forgot the conservation law. Oh, absolute vorticity, absolute vorticity. Head into inebriation, accompanied by rapid rotation. Oh, absolute vorticity, strong in its intensity. 'Cause with every shot I downed, it makes the room go round, 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 and round. Scrawled on the bottle in strange notation indicates that it can cause rotation, but I forgot the effect of beta to omega sine of theta. I'm gonna tear away from this potion. I can't handle all the relative motion. I know all this spinning's just in my frame of mind, but tell yourself that when you try to walk a straight line. Oh, absolute vorticity, absolute vorticity. Head into inebriation, accompanied by rapid rotation. Oh, absolute vorticity, strong in. 'Cause with every shot I downed, it makes the room go round, 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 and round, and round.
That is phenomenal, Dargan. That was.
Thank you. Yeah.
Getting 2 omega sine theta into a song is without just priceless.
Thank you. Yeah. I hear you. The chat recognized it. Greek letter variables kill in song. Yeah.
Dargan, I'm guessing that one's not on the syllabus, or it's extra credit.
That I can only sing to grad students 21 and up, right? Not allowed in the 100 level classes at all. Yeah. Strictly prohibited. Even to sing it in a grad class, we have to have a chaperone nearby. Have to make sure that there are no undergrad classes in the halls nearby. There we go. There's the
Mid latex.
Yeah.
Equation.
Yep. Please derive nice. Yeah.
Very good.
Do y'all want to hear another one? I got one called Science Rules.
Chad, what do you think?
Yeah.
Yeah, I don't know if the chat's got energy for this. Good energy, chat. Come on.
Yeah, they're getting tired. Might be getting tired.
So science rules is like science rules, right? You know, we all know this at GeekFest, right?
Oh.
He's scienced out there, you know. But then the other part of science rules is that science has rules, right? Can't just make stuff up if you're doing science. You got to share your sources, right? You got to, describe your methods. You got to not exaggerate, right? You got to recognize that correlation is not necessarily causation, right? So there are these rules of science that if you're gonna play the game, you gotta actually do that stuff. So this is a song both about how much science rules, but also what if everybody played by the rules of science? Like, wouldn't the world be so much of a better place? So here we go. We cite our sources so you can look them up. Follow safety procedures so our lab doesn't blow up. Carefully we take our data, even sick upon the sea. We stick to the experiment for reproducibility. Sometimes science tells you things that you just don't want to hear, but that's no excuse to hide your head in the sand in fear. We gotta listen to the evidence, let our scientists compete, get more to participate and take it to the streets, 'cause science rules. Science rules. Let's get the whole world to play by science rules. It's like herding cats, get researchers to agree. So those consensus statements are not hyperbole. And to those of you distorters who say it isn't true, when you make up your own facts, we'll make some noise to remind you that science rules. Science rules. Let's get the whole world to play. Let's get the whole world to play by science rules.
Woo!
There you go.
Marvelous. Is that one in the curriculum?
Oh yeah, definitely. Yeah. I actually wrote that for the March for Science. Which was super, super inspiring for me to see so many people standing up for science, you know. Mm-hmm. It's really the vast majority, you know, who really supports scientists. And they, you know, another thing is that people want us to speak out too, you know. They don't want us to sit on the sidelines and you know, just let you know, unscientific policies happen, right? Or you know, just tolerate these massive cuts that we're facing right now, right? So that's why I am so appreciative to everybody who's helped to organize this stream. You know, so many early career folks, students, you know, and I actually get to know some of these folks from research too, right? Like Lily, despite wearing the flippy hat there, is like a super genius. You would not have believed her research presentation, her qualifying presentation a few months ago was just absolutely outstanding. And then the folks behind the scenes too. Stella is just incredible. She was a TA for the Climate Justice and Energy Solutions. So like it's super tragic to see early career scientists not being able to fully achieve, and that's what's happening with these cuts already. So I would say we all got to speak up about this. Another plea that I have is to really take care of each other during this next natural disaster season, because we've lost a lot of great folks at the Weather Service, at NOAA, NASA already, and they're shorthanded, basically. These are folks who keep us safe, but we can all be science communicators. And all those folks at National Weather Service, these are real protector type folks who want everybody to be safe during these events, So everybody can be a good science communicator, make sure that what you share on social media is actually true, right? Find those trustable sources, right? So I think, they're getting worse, right? As y'all have seen in so many talks, right? So many types of disasters are getting worse, right? But we can do better on that as well. And then I want to say too, if anybody in the chat or scientists is interested, every year we run a game jam. Game jams are like hackathon type things where we get together and folks get into teams and make video games about some aspect of climate science. So we're partnering with Indiecade on that. And the Indiecade Game Jam starts on June 12th, I believe. So really, really be terrific to get folks to participate in that. We had over 500 participants last year, and they made 50 games. So it's really, virtual event, and is going just spectacular. We need mentors, science mentors. The theme is natural and unnatural disasters. So anybody who's interested in being a science mentor for that, or if you got art skills, or oh wow, thanks so much for finding the link. That's it right there. You can sign up, and we'll start to have like team building events and stuff pretty soon. Need all sorts of talents to work on games. So what's an unnatural disaster, right? Many disasters are turning into unnatural disasters, right? Because they wouldn't have been possible without the increase in global temperature, or but we're kind of letting you, we're going to have a lot of scientists there to provide guidance to the more creative types, right? Because you really need both working together to make good science communication, I think. But we need testers too, work is hard sometimes. And so we need folks to play games for us, there you go. 12 hours. So one unusual thing about this jam is it's quite long term, but it's sort of a slow jam, I'm not so good at playing slow jams, I'm a little too jittery on the mandolin, I think. But so if y'all are already coding up games on climate change, please join this event. We would love to work with y'all, and there are just so many talented people who come and work on it each year. So that's about all.
Dargan, do you have a favorite game that's been produced over the last few years? Is there any that stick in your mind about ones that have been...
There's so many, so many. This is the thing. We started Earth Games to make our own games. So we do have some of those available at earthgames.org, but there's so many great climate games now. In our that's right. The EGU is ahead of us on the Games for Geoscience night. But some of the geoscience games that I really love, there's one Half Earth something that's like a game where you can do climate features. There's another one called Thunderbird Strike that's really cool. It's about like pipeline resistance. There are the winning one 2 years ago was called Row. And it was this amazing game where you do this sort of meditative rowing, through a kind of post-apocalyptic landscape. But it's really, really cool to experience these ways of storytelling, right? I think one thing about games is you really feel like you're that character, right? Once you're moving around on the screen, even if it's just a few pixels, right? You feel like you're that character, right? So it's such a unique way of storytelling, so immersive, right? So I'm hoping, someday Earth Games will be able to make like a real simulator where you feel like you're in charge of the planet or something, and trying to protect people into the future of global warming. Yeah. Thanks, chat. These are great. The one that won last year was a card game called At Least I'm Rich. And it was one where you kind of are playing to maximize your own profits, but it turns out that you can't get by without the ecosystems and climate stability and things. So it's super, super cool. There's a great coral reef game. This year also we're planning to do a bundle of the winning games that'll be like professionally released on Steam during Indiecade's like big takeover of the Steam platform. So there's also the potential of getting real exposure for your game if you participate and win. So
That's amazing.
These are great ideas in the chat here.
Yeah, you can just be crowdsourcing it, Dargan. The video games.
Totally.
Yeah.
So y'all should help make them. Yeah.
Yeah. You got some HI here in the chat. Just query it. And it's,
yeah. Cool.
Well, Dargan, man, it was amazing having you. You're just a treasure.
No. All respect to y'all. Appreciate being able to play some music. Yeah.
Thank you so much for sharing that.
Do anything for Noah. Yeah.
Do it for Noah.
Do it for Noah.
Yeah. It's definitely, watching this live stream, all the people who use the data, who've been through their programs, especially the AOS program at Princeton,
Yep.
Touched a lot of lives, and made a lot of science. It's pretty wild.
Yeah, no doubt, right? Nobel Prize winning science, right? Just so many fundamental advances, great climate modeling, so much history. So much present, going on too. Yeah.
Exactly.
There's a lot of people saying this is a pick me up, and it's nice because like what you said earlier, where being a climate scientist, sometimes you introduce it to people and they're like, oh no, how bad is it going to be? How screwed are we? How do you do that? Or how are you not depressed all the time? But really, there's a lot of I think we as a community managed to bring a lot of like joy and hope to this as well. There is this, you have to hold these things in tension, right? Things could be really bad, but we also have hope and So I feel like these, like having these songs, having games, things that bring people together, productive stuff like that, I think is really important. Thank you.
Yeah. I think really it's all about community. You got to be in community with others, and So just appreciate y'all in the chat so much. Along. I actually want to mention this too. Somebody mentioned the Cranky Uncle game. This is one about climate misinformation, disinformation that's done by John Cook's group and others. Like it has his little cartoon illustrations. That's another one that's just spectacular. So highly recommend that.
Cranky Uncle meets retired engineer.
Yeah.
Skeptics.
Exactly. Yeah. Yep. Speaking of which, I better go respond to the retired engineer / cranky uncle emails that this performance was probably generated. Now they're probably all asleep. So, yeah.
All right. Well, thank you, Dargan. Thank you so much.
Yeah, thank y'all.
Great having you. Great having you. Everyone, give it up for Dargan.
Love in the chat for Dargan.
Hear it in the chat.
What a legend.
What a legend.
I've never met Dargan before. That's an absolute treat. Sometimes it's fun to know these people exist. It's just terrific.
Dargan is the bard of the party.
Yeah,
I met Dargan for the first time a couple of months ago, and like Dargan, for like you guys in the chat might not know, but he is like, his papers are just like huge. He's like super influential in the field, and in his PhD, and his particularly like his PhD, and he talked about earlier on before he was doing like more of the climate justice stuff. He was doing really like hardcore climate dynamics, and so I saw these papers, and I was like, oh, I bet you when I meet with him, he's going to be super stern, you know, like just talking about math. You know, things like that. And we had a conversation that was much like this, and it's amazing to see the people behind the science. It's completely changes the whole dynamic. It's amazing.
I feel this, what I was saying about the jam that happens at Ocean Sciences is a very similar vibe where you see like, I don't know, David Marshall or Sonia Legg or something like, you know, these like really like proper scientists that you think just speak in math all day, and then they get up and they're singing, you know, Thin Lizzy or something, and like, okay, it's a different person than I thought you were going to be.
Yeah, exactly. But I think that's kind of been the vibe of the whole live stream is, you know, we're scientists, but there's a lot of human there too, right? There's some human there, and you know, I think and part of the outreach that myself and Nadir do is related to this fact that a lot of people haven't really seen a climate scientist before or interacted with a climate scientist. You know, I think that as a field, we're not as, or you know, weather and climate science, we're not as visible and as interactive as I think we could be. And so I think it's been amazing to see in the chat people just, you know, interacting with us and really maybe meeting climate scientists for the first time, seeing that we're all real people. You know, we're not. We have technical hiccups. We have, you know,
we have funny hats. We have funny hats.
We have cats. We have children in the background doing our thing. We have all this. Whoa, Lily! Did you just drop the ears?
I've been doing that this whole time.
The ears have been the main feature.
I didn't see that.
You haven't seen the ears already?
Behind these glasses, I have been sleeping for like these glasses serve multiple purposes.
Ears are the main event.
Oh my God, that's amazing. We have about 45 minutes before we're going to hand over to our next speaker. I feel like we would.
Do you think the people want some data? What do they want?
People might want some
Guys,
data.
what do you say? What do you say?
Show me the data.
We can keep rapping. We can just keep chatting, but maybe people want some. They want the ears.
Now it's on me.
Yeah. All right, we have a couple of show me the datas. I feel like Graeme, are you chill to talk us through some ocean model stuff? We have an amazing ocean model.
I was introduced as an oceanographer. I haven't seen any ocean yet. It was blocked by those clouds.
Yeah. We're gonna get rid of all those pesky clouds. Don't you worry, friend. Don't you worry. How do let me bring this up now?
You gonna share screen again?
Yeah.
Okay. Oh, look at it. It's glorious.
Andrew, you wanna tell the people what this data set is, and then Graeme can point some stuff out?
Yeah, if in order to do that, I'm going to have to look at what it is.
We could play the guessing game. We could have said, you know, what do you think this is?
Yeah, chat. Yeah. All right. Actually, or no, we'll just do it. All right. Chat, close your eyes. I'm going to pretend that I know this off the top of my head. No. This is a numerical model simulation of ocean physics by the MIT General Circulation at a resolution of 4 kilometers. Okay, now I know that. I can pretend that I knew it already. How do I play it? Come on. Yeah, this is chat. This is MIT makes their own climate model. They make their own ocean model. This is the MIT GCM, Global Climate Model, GCM. And this is run at a resolution, which means like the boxes that we split the Earth up into, they're only 4 kilometers big. So normally the boxes we split the Earth up into are like 100 kilometers big. So you imagine pixelating this like majorly. So you wouldn't see any of this detail really. So that's why this is so amazing. And Graeme, whatever you want to say over the top of that.
Take it away. Oh, I mean, so much to say about this. I just, seeing images and movies like this is one of the reasons that I'm an oceanographer and one of my reasons that I'm a climate scientist. Like, just aesthetically, I just think it's so stunning. So yeah, this, I presume, I don't know that, I presume that this is the 1/48th degree or 4 kilometer resolution simulation that was run by folks at MIT, but I think in large part supported by folks at JPL and with funding from NASA as well. So the Jet Propulsion Lab, there's a big collaboration there that goes on to run this ocean simulation. And this is basically the highest resolution global simulation that's ever been run. It was an amazing technical effort. Absolutely phenomenal data set that they then created off the back of this. And the particular reason to do that was to really get down to these very fine scales in the ocean that no one's really been able to fully understand the imprint of. People know that they're important, but we just haven't been able to really grasp because it's just so hard to run the simulations to resolve these things.
Like you look at these swirls off the edge here, that's kind of what you're talking about, right?
Exactly. Exactly. So these swirling motions that actually, even though they're small in the large scale of the global ocean, they actually play a really important role both in sort of changing the characteristics of the flow, so the momentum of the flow in different regions, but also in moving heat and temperature, heat around the ocean, and also in moving salt around the ocean. These things that sort of impact the ocean's dynamics. And so let's see, once we're really going down into the fine scales here, let's see, once we zoom out a little bit or move around, I can point out some features that people might sort of be able to recognize. I think we're going to come across the Indian Ocean now, and we're going to see one of the best features in the ocean circulation, which is the Agulhas Current, which is about to pop up down here. Okay, so right on the screen now, you can see these really bright yellow patches next to the continent of Africa. And this current is actually moving southward. So this is what's called the Agulhas Current. I don't actually know where that name comes from, but that's the Agulhas Current anyway. And if you run it on a little bit, I hope it's going to show us the tip of Africa around the Cape of Good Hope. If it's going to go down there. Nope. Okay, they're going to skip right past it. But what's really fun that this is that current comes all the way down to the south of Africa, and then it sort of leaks around, it sort of squeezes itself around into the Atlantic basin. That's something called the Agulhas leakage. And it let's see if this is not too technical, it does what we call shed eddies. So these swirling motions are called eddies, often referred to as eddies, sort of eddy, like you see eddies in a stream, you can have these sort of swirling motions. And it does what's called the Agulhas current kind of, it sneaks around the continent and then sheds off these swirling motions. And you can track these swirling motions in a sort of coherent way as they move across the ocean all the way from the African continent all the way across to the other side of the basin. And people think this is important for a bunch of different reasons, not just a shed. He's very, very good. Do you know, they actually call the eddies that are formed from the Mediterranean, they call them meddies, just for fun. Nice. So sheddies is fantastic. So these shedding eddies, and they actually play a really important role in connecting the Indian Ocean and the Atlantic Ocean. Actually, it's quite hard for water to get from one to the other directly, except at this Agulhas leakage. And it plays a really important role in setting the properties of the Atlantic. People may have heard of the Atlantic meridional overturning circulation, or the AMOC, or sometimes called the thermohaline circulation. I'm sure some talks have been delivered on that. There's this big, large-scale current system that leads to a lot of heat being moved northward. It's the reason that I am currently in, well, actually, no, if it was wintertime, I would be in relatively mild conditions, whereas on the same latitude as me on the American continent, it would be really much colder. So that system plays a really important role in climate. And actually, it's partly sensitive to these tiny little features associated with this agulous leakage, because it's bringing salinity or saltiness into the basin. That changes the density and is part of what drives that circulation. So even these tiny little features, even these small scale things, can have this really large imprint on the planet and on the climate. It's just amazing. But like trying to understand that, trying to really resolve that is tricky.
Is this the Galapagos? Yeah,
I think that's probably right. Yeah, my geography is not as good as my oceanography, but I think you're right. Yeah,
this is the Galapagos as well.
You can also actually, I just noticed. So I think Brian Arbic, who I saw showed up in backstage, is coming to speak at some point. He does a lot of work on internal waves, and you can actually see them resolved here. You can see sort of, in addition to these kind of swirling motions, you can also see these sort of wave-like features that are also present. These also play a really important role in momentum transfer and mixing in the ocean, that sort of thing. And I'm sure that Brian will talk about that whenever he's scheduled to speak.
Graeme, what's going on if I just play this now? What's the pulsing? Bam, 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 bam here.
Great question. Can we go back to it?
Yeah.
And maybe it's also worth noting the Kuroshio there, which is the analog of the Gulf Stream, and folks may not know about that.
Yeah, so the equivalent of the Gulf Stream in the Atlantic Basin, that exists, actually these what we call western boundary currents exist in all ocean basins. So the one that you can see here across the Pacific, or on the western side of the Pacific, is called the Kuroshio current. And it's exactly the same feature. It's set up by the same dynamics, and it just rolls up the coast of Japan and then detaches and moves off. And you can actually see, again, those sort of eddy features also, and they play an important role there. The pulsing, I think, is probably the diurnal cycle, but I am reluctant to say, but you probably see it showing up in that region particularly strongly because that's a shallow shelf sea region. And so the heat capacity or the sort of volume of the ocean in that region is much smaller, generally speaking. So you're seeing a kind of, do you know what? It's probably the tides.
Oh, yeah, okay.
It's probably the tides in a sort of amphidrone type formulation there that's kind of rotating, because you can see it's got some sort of rotational component as well, that it's sort of moving around in a sort of funny way.
Yeah. Oh, and I hear all the coasts, actually.
Get somebody on who works on the South China Seas and ask them.
Do you know why the ocean is a different color here? Is kind of brown.
Yeah, it's really interesting. Yeah, sometimes when the ocean gets really dry, we call it land, and then I stop talking about it.
The animation is for some reason going over. Oh, we're getting some medis.
Here we go. We might see some medis. So actually, medis, one of the really cool thing about medis is that they actually are in the subsurface. So you won't see it here because this is surface velocities. So what happens? This is some fun facts about the Mediterranean. Here we go.
All right.
The densest water in the world is formed in the Mediterranean. Okay, it's actually because the Mediterranean is a net evaporative basin. So it's in the net. It's losing water through evaporation. So the amount of water that rains on it versus the amount of water that leaves through evaporation, it's mostly leaving. And so what you have is a net gain of, it becomes this really salty water. And then that water that's become really salty and dense leaves through the Gibraltar Strait, which you can see there, the link between Spain and the northern tip of Africa. And you can, this water, which is super dense, it's now really salty and really dense, and it's actually denser than the water that's in the main Atlantic basin, so over to the west there. So that water that's coming out flows, rather than sort of flowing straight out and forming the medis at the surface of the ocean, it actually starts to cascade off the shelf down into the deep ocean. And then it mixes with the surrounding water and then flows off. Once it reaches its sort of a density that matches the density around it, it actually sort of starts to move off into the ocean basin, and that's where the meddies form. So actually the meddies appear as these really cool features in the subsurface of the ocean at around about 1,000 meters, 500 to 1,000 meters in the Atlantic Ocean.
Nice.
Amazing.
We should probably move on pretty soon, but can we get some Gulf Stream? Is this going to show us the?
It is that Gulf Stream.
We're a little far north, but I think we're seeing it.
I think we had some Gulf Stream right at the beginning. If we go back to the beginning.
Oh, it's so glorious. Look at it. So that's the Kuroshio. That you can see it very prominently here, moving out across the basin there.
Mm-hmm. I think we go over the North Atlantic again.
Go. Drum roll.
Wait for it. Wait for it.
So actually the Agulhas current that I mentioned before, that's also a western boundary current. It's in the southern hemisphere. It's on the western side of the southern Indian Ocean. So it's also established by largely similar dynamics that happens there.
Oh, here we are.
Oh, Gulf Stream.
Yeah, there we
so
go.
Here's the Gulf Stream. Beautiful feature of that northward moving Gulf Stream. One of the really cool features of the Gulf Stream that's, again, really hard, dynamically to understand, but it's similar to the Agulhas stuff in the Gulf of Mexico, in that northward moving. So you can see it sort of moving up from Central America, and you get this what's called the retroflexion in the Gulf of Mexico. So you have this kind of swirling formation there, where the water is moving quickly up in that region, and actually you get these similar to the Agulhas shedding of eddies. You actually shed these eddies off of the retroflexion here, and they actually form a really important part of the oceanography of the Gulf Stream. So you have this warm water and these warm water cores that then sort of move westward. I don't know if you play it forward, you might see this one actually detach. So you can see it detach there and start to move across. Maybe it's catching up, but you can basically see this is also a really important part of so it's not just the Gulf Stream further north, but it's actually that Gulf Stream playing a really important role within the Gulf of Mexico there.
Awesome.
So you're looking at this big swirl here.
Exactly. So that's all that warm water that's coming up. And so sometimes that current is confined to being much closer to the west, so much closer to the Caribbean, and just moving directly up. And sometimes it kind of migrates out into the Gulf of Mexico and then moves northward. So it has a really important role in the local dynamics there, local effects on hurricane season, for example, that warm water that's sitting in the Gulf of Mexico and its imprint on the atmosphere in that region is really essential. But again, that's a really small feature in the ocean, so trying to capture all of the dynamics associated with that is really hard in climate models and in climate dynamics and in weather prediction models.
Yeah. Awesome. Well, we've got some other data to show folks, so maybe we should move on from the MIT GCM. But Graeme, thank you so much for hanging out.
That was a delight. That was honestly the most enjoyable 15 minutes of my last week or so. It's great. I should just sit and watch ocean velocities more often.
Yeah, it's mesmerizing.
Yeah. All right. Well, I better head off because my mum is about to arrive for a nice Sunday here in Scotland. So I better go and get ready for it. Probably have to tidy my room or something. I don't know. That's what you do. Thank you very much, folks, for having me. Thanks so much for putting this all on. It's amazing. And yeah, all the best for the next, what are we on, 11 hours?
I think, is it, if I have to flip myself upside down, 11 hours?
11
we can
hours.
do it.
Bon chance.
All right. Thank you, Graeme.
Good luck, folks. Cheers.
Take care, Graeme.
Bye-bye.
Oh, I think I meant to take you off. Sorry. Our current director is somewhere else. I think our background chaos gremlin is elsewhere.
That's all right.
So Nadir, what do we want to look at next? Do we want to look at X Shield?
Well, we could, we probably got half an hour, and I wonder if we want to kind of, zoom out. We've done some nice high res, global modeling. Is the chat ready for some CO2, some carbon dioxide, different places around the globe over time in space? Maybe?
You know what to say if you want to see some data, right?
Do they want to see data? I don't know. They're saying goodbye to Graeme.
Oh, they're saying goodbye to Graeme. Understandable, honestly.
That's important. All right, we're getting some, we're getting some sure. Oh, all caps. There we go. All caps and many exclamation. Okay.
I think people want to see some CO2. All right, let's get that up and running.
All right, you got it?
Give me 1 second. All right, here we are. Or wait, is it actually going to work? There we are. Okay. So let's play this video. I'll play it on loop.
Wait, hold on. Should we pause it and tell them what they're going to see? Because it's kind of a lot going on here.
Yeah, there's a lot going on. Okay, so you guys remember one of the early talks we had was Ralph Keeling talking about the Keeling curve, which is this place in Mauna Loa, which is an island in the Pacific, this red dot here, and they measure CO2 at that place. So it used to be you take a flask of air, you shine lasers through it, and you can tell how much CO2 is in the air. And the way we measure CO2, or the unit we have, is ppm. So that's parts per million. So what this thing on, we currently have about 400 or something parts per million of CO2 in the air. And what this graph is doing is it's showing you've got all these different data points from across the world that are each measuring CO2 over time. So we're starting. Sorry, go for another.
Yeah, exactly. Each dot there is an independent measurement of CO2 from a different location around the world.
So we got the South Pole, we got Hawaii, we got the North Pole, we got somewhere in like Kentucky or something here. And you can see, and so there's three things that are plotted. So over time, we're going to have more data coming up on this map, some more dots coming up on this map. And whenever a new dot comes up on here, it's gonna come on to this plot here on the left, which is showing the latitude of that data. So this is 90 degrees south. This is the South Pole, so it's that blue dot in Antarctica, the equator, and then the North Pole. So like this red dot Mauna Loa is kind of like around 20 degrees here, and it's going to show you in the vertical how much CO2 there is. So currently 1979, we've got about 10 dots, and they're all about 336 ppm. And then it's going to show the global mean value in this time series on the right here as well. So let's just play it through for a little bit, get ourselves calibrated.
All right, so we've got a lot going on here. So look at the red dot moving up and down. So that's the up and down motion is the seasonal cycle that Ralph Keeling was talking about, the breathing in and out of the biosphere. And the red dot is Mauna Loa at a latitude of 20-something degrees north. What's superimposed on that seasonal cycle is just the slow trend of the CO2 gradually going up. And so the red dot, even though it's going up and down, there's also on top of that just the slow drift upwards. Mm-hmm. Then you look all the way to the left, you see a blue dot. And that blue dot, that's at 90 degrees south. That's the South Pole. They started measuring that a little while later. And that one's also drifting up. But the seasonal cycle is much more muted because there's not that much forest down there. And so there's not that much breathing in and out of the biosphere. And so that seasonal cycle is much more pronounced in the north, where you have the land masses, you have the boreal forests, and you have them breathing in and out. That's a lot of what you're seeing on the left. And on the right there, it's just showing the South Pole and the Mauna Loa time series. So now on the right-hand side, the x-axis is time. The vertical axis is still the CO2. And so you see the seasonal cycle in red in Mauna Loa, but also just a steady climb upwards. We'll just watch this for a minute.
I was just going to point out as well, so you can see that in the northern hemisphere, in this red dot here, we have this seasonal cycle where you're peaking. So you're peaking in the summer in the northern hemisphere, but you can also see there's a small seasonal cycle even in Antarctica. It is much smaller, but it's what we scientists call out of phase. So if I just jump back a little bit so you can see it a little bit more clearly. You can see that the seasonal cycle in Antarctica peaks 6 months later than the seasonal cycle in the northern hemisphere, and that's because when northern hemisphere, when we're having our summer, southern hemispheres have in their winter, and vice versa as well. It's kind of like a nice thing I think is cool. Yeah. Let's watch this.
We'll keep playing it, and then we'll see what happens when we get to the present day. So right now we're at 2000. Let's see what happens.
You can see we have more dots coming in as well.
Yeah, look at that map. You just see more stations coming online. A lot of that is NOAA. Now we're at 380. Still creeping up. Boy,
nice
some of the
thing.
stations. Go ahead, Andrew.
I was just saying, a nice thing, chat, is to think what ppm was I born at? What CO2 was I born at? So I was born at about 355 ppm, which is a nice, which is my data point. And now we're all the way up to
Well, look at that.
Let's calibrate people on what's happening now. So this is all the historical measurements we have from data across from actual stations across the world. So all these dots we have so far, this is from people going out, getting a flask of air and shining lasers through it. And that's the data we have. And we're about to get some different data now that's going to help us go further back in time. So let's play that.
Now we're going backwards. Chat, any idea where this data is coming from? Whoa. What just happened?
What's happening?
That was really fast, but you can see up here it's telling us some of the answer here. So we have ice core measurements. These orange dots are ice cores, right? So I think a few people have told us about how you can actually go to places like Antarctica and Greenland and you can take out like 10 feet of ice and you can go and you can slowly melt it. And when you melt it, there are bubbles in the ice that were trapped 500 years ago. And you can tell how much CO2 there is in that little bubble of ice. And the reason that works, the reason why that's a useful thing to do is because CO2 is basically the same number everywhere on Earth. So you can see, so if you look over here on the left again, you can see even back when we just had like the South Pole Station and the red dot in Hawaii, these are completely different places. Like one is in the Antarctic, one is on like a tropical volcano, and they're basically giving you the same value. So even like a bubble of air trapped in an ice core in Greenland is going to tell you something about global CO2. And that helps us go back like really far. That's what you're seeing here.
And so this pre-industrial value of CO2, 280 ppm, we were never able to directly measure that from flasks, right? It had been too long. So the only way we know what that number was from the ice cores. And before we measured that in the 80s, we didn't know what the pre-industrial concentration was. Now we're looking at a different set of ice cores from Antarctica that go deeper in time. So now we're looking at tens of thousands of years. The CO2 levels have dropped because we're in an ice age.
So on the bottom, this axis is now hundreds of thousands of years before the current event, before like current times.
Now we're seeing multiple ice age cycles being uncovered by these ice cores.
So you have these glacial, interglacial periods where CO2 has gone up and has gone down over time. These are all coming from ice cores. It's pretty amazing, actually. And so when people will say sometimes that climate has always changed, and that is true, right? You can see in the data here that CO2 has gone up and it has gone down. But there are two things that are different about the way that climate change is currently happening. So one is that you can see here that although CO2 has gone up and down in the past, it's capping out at about 275, maybe 300 parts per million in this ice core data. But currently we have pushed we've pushed CO2 up above 400. Above, what are we now? Like 440 or something?
A little over 420, maybe.
I don't know. Yeah, so we're well above 400 at this point. And also the time scale over which this is happening. So if you look at like natural glacial interglacial cycles on the Earth, these are changes of maybe like 100 at best parts per million of CO2 over 100,000 years. That's like really, really slow. Whereas now we've put 100 ppm of CO2 into the atmosphere in about 100 years or something. The scale of climate change is completely different to what we're thinking about with glacial interglacial cycles.
Yes, this is just an amazing example of how piecing together different data sets, different techniques from different places all over the globe, just gives you this incredible perspective and paints an incredible picture. Andrew, if you want to forward that to the end there, it shows all the different funding sources. This is what it takes to put together this data and decades, right? The Mauna Loa measurements started in the 50s. Some of those ice core data sets go back to at least the 80s, if not further. We heard talks from ice core folks in Greenland and elsewhere. We heard about the incredible effort it takes to go out there, to drill out these ice cores, to bring them back and to sample them, and to do all the chemistry to extract the data. But that graph that you saw and the perspective that you get from it, that's the payoff, is being able to put the present moment in the context of the last almost million years of data.
And there's a lot of U.S. funding here. We have NOAA Global Monitoring Division. We have the National Center for Atmospheric Research. We have the Atmospheric Research Measurements arm. That's a Department of Energy research arm. NOAA Chemical Sciences Division. NOAA Halocarbons Environmental Research Lab. This is This is a global. We saw that those dots are coming from across the world, but there's a lot of that that's coming from the U.S. And you see these early measurements from Mauna Loa. This is like the most famous time series of CO2 that we have. That's a U.S. thing.
Well, and if you go to the very end of the video, it gives a credit to who made the video.
Oh yeah.
Let's go see that. Oh.
Andy Jacobson. A NOAA.gov guy.
There it is. 4 little letters.
Yeah. But yeah, chat. Do you have any questions about this curve, about what we just showed? We can try and answer some questions if that went a little bit too fast, or you have anything else you want to ask? Loving the hats. Thank you, Astra. Okay, loving the ears. Astra.
I think they got it, Andrew.
Talking about the Southern Hemisphere more. There's a lot of Southern Hemisphere friends in chat right now.
Yeah.
Awesome.
Where are some? I mean, let's just have a look. Where are some of these things? We've got some stuff in South Africa. We've got some sites. It looks like there's a dot actually here in the Southern Ocean. It's pretty cool. Maybe some stuff on New Zealand. I think this is an early dot on New Zealand here. It's gray over here, and yeah, that's pretty awesome. Thank you to our Southern Hemisphere friends.
Indeed.
Are you able to project the future of CO2 uptake? Bitte. That is an amazing question. I think that's what Graeme was talking about a little bit earlier, is that exactly how much CO2 the ocean takes up is a real uncertainty in understanding how much the Earth is going to warm, over the next few decades and things. So currently the ocean has taken up a huge amount of the CO2 that we've emitted into the atmosphere. So when you burn a certain amount of carbon, you get a certain amount of carbon dioxide molecules in the atmosphere, and a lot of that goes into the ocean. And so the ocean has buffered the pace of climate change. so far. I don't know if Nadir, you want to add anything extra to that.
Just that, so Andrew's described how, the ocean and the land are taking up CO2, and projecting how that's going to evolve in the future is a major task for climate science, especially for the land, because how the plants are going to respond, how the vegetation is going to respond, big uncertainties, and a huge topic of work for the years to come. So that's one of the big questions of climate science that you've hit upon there.
Yeah, great question. Great question.
Should we, we've got 10 minutes, and we've got that nice greenhouse effect analogy. So should we hit them with that, and then we'll say goodbye?
Yeah, should we hit them with it? So that's 4 minutes long.
Well, we'll.
No, I was going to say I wonder if I can do my piece of paper.
Sure.
All right, chat.
Yeah.
We're going to try something. I don't know if this is going to work. Give me 1 second to set this up. So I think so. I think so. What I think we'll do is we have an animation of that. It kind of talks a little bit about the greenhouse effect. What would be fun, maybe before we do that, is just to go over a little bit of the science of the greenhouse effect as just in a really quick. Let me present a different screen now. So I think, all right, I think this is going to work.
Whoa.
All right. When I should have been sleeping, this is what I was doing. So some of you will have you've heard a lot about the greenhouse effect already on this chat, but I think it's just important to keep in mind some basic things. So over here we got the sun. So the sun is the main source, is the power source for everything that happens on Earth. You heard Kirsten Findell a couple of days ago, the land queen, talking about how the sun really drives everything on the planet. And over here we have the Earth. That's to scale. We're gonna have to blow it up a little bit though to really see. Oh dear, that was a terrible circle. I'm so sorry.
You're committed.
Blow it up a little bit here. And so what we have is the sun is putting out a lot of energy here, and that sunlight is hitting the Earth. And when we think about the temperature of the planet and how the greenhouse effect affects this, we have to think in terms of energy balance. So, let me move this down a little bit. Energy balance. So there's a certain amount of, we're going to call it solar energy in. So there's a certain amount of energy from the sun that gets absorbed by the Earth. And so this depends on how strong the sun is. And it also depends on how reflective the Earth is. So you guys remember albedo from Dargan. It depends on the albedo of the Earth. So how many clouds there are, how much ice there is. It also depends on the strength of the sun here. And the fundamental control on Earth's temperature is that the solar energy in has to match the heat energy out. So what happens is you get solar energy that hits the Earth, and that causes the Earth to warm up and to have a temperature, which we're just going to call T here. And it turns out that everything that has a temperature emits heat energy, emits thermal energy. And so the Earth is also losing energy like this. It's losing energy out to space. And the biggest constraint on the energy on global mean temperature is that the solar energy in has to equal the heat energy out. Now, what does this heat energy out depend on? So it turns out that heat energy out increases if temperature goes up. So if T goes up, we're going to call, let me just call this, I'll just say this heat out goes up. So if the temperature of the Earth increases, then we lose more energy to space. And if CO2 goes up, then we emit less to space. So these are the main things we need to know. So there's this balance between the amount of sun that goes into the planet, solar energy, and the amount of heat energy that goes out. And if the temperature goes up, then we lose more energy out to space. And if we increase CO2, then we lose some of that energy that's going out to space. And that's the basic balance that determines Earth's temperature until this is the basic physics of global warming. And it turns out that you can think about this in terms of a leaky bathtub as well. Now, what does that mean? We're going to show you that in a second. So I'm going to unshare my screen and share something else. Earth's energy balance. Sorry, one second. Okay, so this is a video by our good friend Jake, who made this great video we're going to play. So just to say, in the context of what I was showing before, we have sunlight going into the Earth, and then this heat energy going out. This is the water that's spraying out the side of the of this bucket here, and eventually they become into equilibrium. And so the sunlight energy going into this planet, this box here, is equal to the infrared or heat radiation that's going out. So Jake has marked that here, the little green dot. This is the equilibrium temperature of the Earth. Now, if you reduce the amount of energy that's going into the system, you turn the sun down, then you need less infrared to balance it. And because heat energy depends on temperature, that means that the temperature drops as well. That means you get a new equilibrium temperature. So the Earth, if the sun was colder, the sun gave less energy, then the Earth would be colder. You turn the sunlight back up to normal, you see the temperature rapidly rising. We get extra heat energy back out to space. Now what we're going to do, what Jake's going to do, I'm going to tell you about it before he does it, is we're going to think about what happens if we put greenhouse gases into this system. So if you put greenhouse gases in, it makes it harder for that heat energy to get back into space. So what Jake is doing is he's plugging one of these holes. He's making it harder for the water to leave, the energy to leave the system. So what's going to happen? So if you do that, we've lost some energy back out to space, and the temperature has to go up. And when the temperature goes up enough, you get back into a new equilibrium where you've got more infrared energy back out to space, but the temperature is warmer.
I think the key thing is here is that when you plug one of the holes, the water level starts to rise, but doesn't rise indefinitely. It just rises enough to get water to flow through a new hole, to get more water to flow, and to reach a new equilibrium.
Mm-hmm. And you can just keep, what we're doing at the moment is by adding more CO2 in the atmosphere is we just keep plugging these holes. We're stopping the Earth being able to lose energy back out to space. And Jake is now turning off the sun. This would be bad. Okay. Yeah, Nadir, I don't know if there's anything you want to. We can play it. We can play it again. I don't know if you want to add anything over the top of that, or.
No, I think we're all good, and I think we're at time.
Yeah, we are at time.
All right, Andrew. My GeekFest brother. We the sun is coming up here in New Jersey. I can start to see a little bit out the window, so I think we can remove our.
We can remove the hats. I've got terrible hat hair. I'm keeping the hat on, but I'll take the glasses off.
Yeah, wow, it's bright. So,
it is.
We have made it through the long night over here on the East Coast. Thanks everyone for jamming with us. We had a good time. I hope you did too. And I think we're gonna resume our regularly scheduled programming. And Lily, I think you're gonna host. Or sorry.
Oh
No, Virginia's
a
gonna
time
host.
for Lily.
Surprise, I'm here. No.
Hi, Virginia.
Good morning.
Good morning.
Good morning.
I logged on to see the TV with the counter upside down, and there was music and drawings. And Lily and I were talking backstage about the vibes overnight versus the vibes during the day. And I feel like vibes during the day are like,
get it.
Yeah, it's like we've taken the suit jacket off, and it's like, no, we're just chilling around the table now. So welcome to like climate change after dark or whatever it is.
I mean, we're people too, and late night, it gets a little more relaxed around here.
Thank you all so much. I am happy to let you go. I don't know, it's Sunday, sleep, rest, do something. Thank you so much for the GeekFest. It was lovely to spend this time with you.
Awesome. Taking over.
I'm going to have my own personal GeekFest for a minute. I'm a marine biologist by training, and there was a question forever ago when I first logged on, and they were showing the animation of the Earth where the oceans looked like they were on fire, and they were talking about ocean currents, and I saved it because they didn't answer this question. Kelsey Ward asked, is the East Australian current from Finding Nemo real? And since I studied fish, since I'm a biologist, I need you to know, yes, the East Australian current is real. Fish actually do ride it, but it's not like surfing like in the movie where it's just like a little thing that's like and then there you go. It's not like those tubes at the bank that sends your stuff up to the banker. It's more like a giant current that like provides them with a little less energy to get where it is that they're going. But yes, biology is cool. Finding Nemo is factually like pretty good. So, like the number of eggs that clownfish have is larger than what they had in the movie, but they showed them having a large number of eggs. So anyway, now that I've done the fish thing, I can officially welcome y'all to the next part of the stream. I feel like this is, I feel like this is like my 5 to 7 time slot, and I'm seeing people in the chat that have been here for days with each other and with me, and it's so delightful to be with y'all in the final hours of this live stream. We are halfway through hour 89. You can see the TV's flipped up normal again. We're halfway through hour 89. We've got 10 and a half hours left. It is so exciting that we are going to finish this strong. I do want to issue a little bit of a different call this morning. So we've got just a couple minutes before the next speaker comes on, and I am supposed to read you the mission. So why we're all here united. And a lot of you in the chat, I think, have been here for a little bit. And so you've probably heard someone talk about the call to get in touch with your representatives. My own GeekFest yesterday, after I got offline from hosting this time block yesterday, I was gardening and I was just letting myself think about what gets people to take action and what gets people to love science, and how y'all are like vibing on the stream. I've seen several people say, can we do this again? Or with like a different subject, can we have some kind of like public live stream? And I was thinking like, yeah, we could do this all the time. And then I was like, oh, well, only if we have jobs. And so normally I read you this kind of more generic statement that's like, here's why we are here. Here's why weather and climate science is important in the US. And I just want to make this one very real. I gave my own talk yesterday at 7 a.m. and I said, and this is true, that I am funded by multiple federal grants. And so what that means for people like me is I wake up each day, I go to work, and I don't know if I'm going to get an email or a call from my colleagues saying our grant is done. We have contingency plans now for like, okay, if they stop us here, this is how much work we'll be able to do. If they stop us here, if we can just get to this part, we could do this work and then maybe we could squeeze in. And so I know this sounds very depressing, but I'm saying this because I want to take it out of generic and make it very real for you. I, Virginia, on your screen, don't know if I will be paid to do my job next year. Don't know if I would be paid to show up. I mean, I'm not being paid to show up to this live stream, but because I have a job, I can volunteer to do service stuff like this because I'm not like scrambling to find another job. So I just want to make it very real. And I want to ask you, if you're in the chat, have you actually contacted your representatives if you're in the US? Like, I know we're all vibing together and that is great. But the point of this is to get you to contact your representatives. If you have not done it, then we have failed to reach you to convey the urgency of this, because it sounds dire, like we may not have jobs, but the power is completely in our hands still. Budgets have not been passed. There is no savings in the budgets proposed because they just shift stuff away from science and into defense. If you want sources for all this, I can give it to you. But I just want to make sure you know that, like, this is not meant to be depressing. This is meant to be I am handing you the power, because this is what movements are like. If we are hanging out in the live stream together, hanging out on the stream together, we're having a good time. Y'all all watched a really fun and weird, like very long YouTube video, right? But if you take action, we are a movement. And this is what it feels like to be in movements. I've seen people say in like action spaces lately, like, I'm just here to learn. And I think what I've been learning is that we are the people that are going to make the difference. We are the people. I am learning that it is us. It is us who is going to change things to be the way that we want them to be. And so if I can have y'all learn that, if I can have y'all, honestly, if you haven't contacted your representatives, take that next step I'm going to introduce the speaker soon. I'm eating in their time a little bit. I'm so sorry. I will wrap this up, but I will be back at the top of the hour. I'm going to ask you at the top of the hour, literally, to mute me for like 3 minutes. That's all it takes to contact your representative. So get prepared for action. I'm going to stop taking up the speaker's time. I'm going to bring Brian on stage. This is Brian Arbic, who's going to be joining from the University of Michigan. Good morning.
Hi, how are you?
Good. I've eaten like a minute into your time, so I'm just going to stop talking and hand it straight over to you. Welcome and thanks.
Great. Thanks a lot. And thanks for having me this nice event. So I'm going to talk about tides and ocean forecast models. Sorry, I'm having trouble advancing. Why is the slide not advancing? Oh, there we go.
I see it.
Yeah. Okay. Yeah. So I'll talk about ocean forecast models and then a concept called the ocean general circulation. That's the big current systems in the ocean, and tides and internal tides. So I'm going to assume that a lot of people haven't heard of internal tides, but that's something I'm an expert in. And I'll talk about insertion of tides into ocean general circulation models, why it matters for many agencies, why a lot of agencies fund this work, and what do we do with the funding. So just like you can have weather forecast models, you can also have an ocean forecast model. So a weather forecast model is a computer simulation of the atmosphere where you take the equations of motion, there's momentum, the wind pushes on the ocean moves, things like that. And you discretize that. That just means that, the real world is continuous, but our computer isn't big enough to go down to the very finest scales. So you just say my block is this big, and I'll have the equations working on this point and then this point over here. You put the equations of motion onto a grid, and if you have larger computers, you can get finer resolution detail. A weather forecast model combines observations of the present and the recent past with a computer model that can then push out into the future. Like, okay, if that's what the atmosphere has been doing for a few days, this is what it's going to do tomorrow. So the exact same principles can apply to ocean forecast models. You have data of the ocean, a computer simulation of the ocean. You combine these things and you can say, what is the ocean doing a few days from now? So a lot of observations go into ocean forecast models. Here I'm going to highlight just two. So I've been hearing that a lot of people are excited about Argo. So Argo is also used in ocean forecast models. So what Argo is it's a bunch of robots that are floating around the ocean, and they basically drop down the upper ocean. I can't remember the exact, I think it's a couple thousand meters. And as they're going down, they measure temperature and salinity, and then they park for about 10 days, and then they come back up. And so this map here shows, as of a couple days ago, where the 4,173 Argo floats were. And so these things are measuring temperature and salinity in the water column all the time, and that goes into ocean forecast models. Now, another big thing is satellites. And so satellites can measure the sea surface temperature, the winds, lots of things. They're really amazing. And this particular satellite is my personal favorite. It's called a satellite altimeter. So satellite altimeters send microwaves down to the ocean surface that come back. And so and they measure that distance. It's really amazing. They measure the distance to accuracy of about a centimeter. And so from space. And so if you have, for instance, a low sea level, then it's going to take longer for that signal to come back. And if you have a high sea level, it takes less time. So anything that makes the sea level go up and down, tides, currents, El Nino, they can all be measured with satellite altimeters. And that's actually probably the most important measurement that goes into ocean forecast models is satellite altimetry. All right, so who uses ocean forecast models? So a lot of my work is funded by the United States Navy, and the reason they're interested is their fleet is sitting out in the ocean, working in the ocean environment, and they want to know what's the temperature, what's the currents, the tides, things like that. Fishing boats use ocean forecast models because the ocean spawns little eddies that are kind of the ocean equivalent of atmospheric weather systems. And if they're spinning one way, you'll get an upwelling that will promote biological activity in fish. And if it's spinning the other way, you won't. So fishermen look at these things all the time. Search and rescue operations. So if someone falls overboard and you want to know, a few hours later, where might they have gone? Well, you need a forecast model of the currents. The currents might have taken that person over there. Oil companies use them because they have platforms sitting in the ocean, and when you have waves and currents, it stresses those platforms. So these are just some examples of who uses ocean forecast models. Okay, so next I want to talk about the concept of the ocean general circulation. So this is things like currents, like the East Australia current that Virginia was talking about. So they're primarily driven by the atmosphere. So the wind blows on the ocean and it moves water around in a lot of different ways, waves and currents. That's probably pretty intuitive. You also have air-sea heat fluxes. So if the ocean is warm, it releases heat to the atmosphere. If the ocean is cold, it goes in the other way. And that changes the temperature of the ocean as well as the atmosphere, by the way. This constant heat exchange is changing the temperature. So we call that air-sea heat fluxes. And then if you have a lot of evaporation, then the water becomes saltier and denser. Whereas if you have precipitation, the water becomes fresher and less dense. And so the reason these things matter is that temperature, so cold water is more dense and it tends to sink. Warm water tends to stay up high. And similarly, salty water tends to sink and fresh water tends to stay up high. So the ocean is a stratified fluid. It has different layers. You have light water over heavier water. And that stratification is driven by the temperature and salinity, which is controlled by these interactions with the atmosphere. Minor note is that atmospheric pressure loading also matters. So if you have a high pressure that pushes the ocean down, a low pressure goes up. That's also important, but I won't say more about that. So anyway, all these interactions with the atmosphere drive a system of currents. And I'm going to show an animation that illustrates that in just a second. And then separately, you also have tides, and that's my specialty, and I'll talk about that more in a second too. So I'm going to try to see if I can do this shifting around here. Sorry, I don't present quite this way usually. Oh
Looks
boy.
great to us, and the chat is very engaged. I'm not sure if you can see it right now, and I'm monitoring it for you, but the chat is very into this. No worries.
Yeah, sorry, that's good. I heard that there were other oceanographers, so I'm glad to hear that. Okay, there we go. Present. I'm really an amateur at this kind of thing. I usually just show my entire screen, but then you get to see the things I read. And
You know what? So many people on this live stream, like, it's not your literal job, right? And that's
Yeah.
why the whole system is needed to make this all work. No worries. And yeah, you're not the only people. The latest comment in the chat is, "We love Argo floats."
Yeah, I do too. So I've got a new movie now. I don't know if you, yeah, there we go. Okay, so I'm an older guy, so I tend to sometimes show older things. This is a movie that was made 20 years ago. So some Department of Energy scientists, actually at that time, the biggest computer was in Japan. So they did this simulation in Japan. We have newer models now, but they to illustrate the point, this old one works fine. So what this is showing is the colors represent temperature. So when you're in warmer climates, the water's warmer, and that's not too complicated. And then when you're in colder climates, like down here, then the water is colder. So the red is temperature. The time is clicking along like this. And so again, these temperatures are from the interactions of the ocean with the atmosphere. Then what you're also seeing is these bumps and valleys are highs and lows in sea surface height, which again is detected best by altimetry on a global scale. But in a model, you see it too. And so just like the atmosphere has a jet stream and then it spawns off eddies, which are weather systems, the ocean has strong currents in certain places, like this is called the Agulhas current, and then it goes into what's called the Antarctic circumpolar current. And these things have eddies. So the colors are temperature and the highs and lows are eddies spinning around. And you see these eddies are fairly small. And so the bigger computer you have, the better you can resolve them. Okay, so, okay, I think I'm getting the hang of this now. So back to my PowerPoint. And if I was really sophisticated, I would have these movies embedded in a PowerPoint, but I don't know how to do that.
Listen, sophisticated is relative, and people have never encountered this before. So it's coming across great.
Okay, so now a little bit about tides and internal tides. So now I'm going to show you movies of tides. But the thing to keep in mind is I'm going to show you first tides like people think of tides. The sea surface height goes up and down. Then I'm going to talk about something called internal tides, and I'm pretty sure most people have not heard of. So remember again that the ocean has these layers. So here's a little sketch that I made by Harper Simmons in a paper that I was on, and he's showing that you have these layers. So rho is a symbol we use for density, and as you're going down, the density increases, and each of these layers has a certain thickness. And so we often represent the stratification of the ocean in this way in ocean models. More dense water as you go down. Okay, having said all that, now I can show two more movies to illustrate what all this means for tides. So two more movies. So, I'm a professor and my students sometimes complain that my slides are a little text heavy, but then I show these movies to make up for that. All right, so now there's another thing, a movie should be showing. There we go. All right, so M2, you see in the title there, stands for moon twice daily. That's the principal lunar semidiurnal tide. That's the cause of most tides in the ocean is the moon. And it's twice per day. And the tides are much more complicated than that. I'm oversimplifying it. But anyway, so these are the tidal heights in simulations of a model called the Hallberg isopycnal model, HIM, written by a guy named Robert Hallberg, who works for NOAA. And you see that the color bar is interface height meters on the left. I'll talk about the right in a minute. And so Blue means you have a negative, so that's a low tide. Red is a positive, that's a high tide. And so this is what the tides actually look like in the ocean. They're propagating around, and the tides go up and down. It's fun to look at New Zealand. Look at how the tides are opposite sides of different parts of New Zealand, which I actually spent a month in New Zealand just a little while ago. Okay, so the tides go up and down, but people who've sailed also know there are currents. So when currents go like this, that feeds a high tide. And when currents go like that, that gives a low tide. So along with the sea surface going up and down, which you're seeing here, there are tidal currents. Now, what happens when the tidal current encounters a massive topographic obstacle, such as the Hawaiian archipelago? What happens is those currents will then start to go up. But if they go up like this and the ocean is stratified, that means those interfaces between different layers move up and down. That's what an internal tide is. And the internal tide, so you can have layers moving up and down by 100 meters. And by the way, if you're in a Navy submarine, that means you will be lifted up and down, just like when you're in an airplane and you encounter turbulence. The submarine will go up and down like that. That's one of the reasons the Navy cares about this stuff. Now, you have 100-meter signals down below the surface, but these things also project onto the sea surface. So there is a measurable effect on sea surface height, which you can see by NASA satellites. So that's how this all connects. Now, the blues and reds are the interfaces moving up and down by tens or 100 meters. And we made this movie, and then my collaborator, Harper Simmons, who made that little sketch, made a better movie. Okay, so let me show you his movie. That's the last movie I'll show. Here we go. Stop screen there. Enter the last movie. Share screen. Window. Oh, yeah. Okay, this means I got to go to here. All right. I got to click on this thing. Okay, so I want this. There you go. Okay, so this is the movie that he made of these internal tides. So what he did is he started from rest, and then you're seeing how from rest these things start moving. And he chose a much nicer color bar. So, you know, and we worked on these things together, but his movie got more attention than my movie. But I showed my movie first so you could see the regular tides make the internal tides. And then his movie, the internal tides, is much nicer. So you see these internal tides fill the whole ocean basin. And when we did this, by the way, we were both working at NOAA GFTL, which has been mentioned many times. These were the first global simulations of internal waves in the ocean. There was other teams that had done a lot of great prior work, but we did the first global simulations as postdocs at NOAA 20 years ago. Okay. Move here, stop showing that movie. Back to the slides, which I will then use for the rest of the talk. All right, so I managed to show all those things. So I'm back to the slides now. Are the slides up? Oh, there we go. All right, so, oh, geez, I gotta do this, right? Okay, now why do internal tides matter? So internal tides are tidal motions that are really big motions below the surface, measurable at the sea surface. So internal tides interact with wind-driven internal waves, which are called near inertial waves, and they produce a spectrum of high-frequency internal tides, which is named the Garrett-Monk spectrum after the two very famous scientists who discovered it. Now, just like waves at the surface of the ocean can break, internal waves can also break. And that mixes warm and cold waters. It exerts an influence on ocean stratification, circulation, and uptake of heat and carbon. They lift cold water up, push warm water down. That changes the sound speed, so it's really important for naval acoustics. So this stuff really matters. And it just so happens the largest internal tides are in the South China Sea near Taiwan. And they have a detectable signal in satellites, as I mentioned. So the thing that I've done that has probably been my the highlight of my career was putting tides into high resolution ocean general circulation models. So people had done tide models and they'd done models of the ocean general circulation forced by the atmosphere. We were the first to put it all together. Now about a dozen modeling centers around the world do this, and the numbers are growing all the time. I think maybe I'll skip that slide because I think I might be running a little short on time. So why would you put tides into ocean circulation models? So the interaction of internal tides with currents and eddies actually makes them less predictable. So we think of tides as being very predictable, but these internal tides actually get knocked around by those eddies I showed in the one movie, and that makes them hard to predict. But if you have a forecast model, you know where the currents are, and you can actually predict the things that are hard to predict. Also, we are able to reproduce part of that high frequency internal wave spectrum that I talked about, which means that we're getting to the point where we can actually start to simulate the energy cascades that drive the mixing that then changes the whole structure of the ocean, the stratification and the circulation. We're actually getting to the point where we can simulate that directly, or, well, it's complicated, but at least indirectly. Another thing is that tides interact with all forms of ice in the ocean: sea ice, glacial ice streams entering from continents, and the floating ice shelf extensions of these ice streams. So tides matter for those things as well. And all the ice in Antarctica is, of course, critical to the global climate. So applications for different agencies. So for instance, we have a NASA project where we're examining whether the Navy ocean forecast models can offer improved predictions of internal tides to use with altimetry products. So just real quick, these things here are altimeter tracks near Hawaii. The red HRET, that's what you get measuring what's called the amplitude and phase, how big is the wave and when is it hitting its highs and lows, and you multiply the amplitude times the sine of the phase. That's the way we combine the information. And the red is from analysis of the data itself, and the blue is from the forecast model that the US Navy uses, which is called HICOM, Hybrid Coordinate Ocean Model. So you can see that the reds and the blues are almost on top of each other, and that means that the forecast model can predict where these waves are almost as good as if you just analyze it from the data itself. And so work that we started as postdocs at NOAA then became useful for the Navy, and then the Navy model is used by NASA, and then the NASA data goes into the Navy model to make the Navy model better. So it's all interconnected. So the work that I showed here, and from our community more generally, and some of this was my work, some of it was community work, it was funded by NOAA, NASA, Department of Energy, the Office of Naval Research, and the National Science Foundation. So I just want to make the point that all these agencies are contributing to this. And I think this is my last slide. Where does the funding go? So if you take the big view of the funding to the community, it's going to things like satellites, high performance computing that we use to run our models, Argo floats and other instruments, salaries of scientists and engineers who develop the instruments, satellites, and models, and more. This is just a partial list. To my particular research group, I can say that most of the funds and the grants to my group go to support the early career scientists, PhD students, and postdocs who generate most of the results in our papers. Okay, so the point is that, we're funded by many agencies, and obviously, if funding goes down, we won't be able to do the work, and the young people in my lab won't have work to do. I think that is my last slide. Yep.
Thank you so much. I want to start by just highlighting some things from the chat that aren't actually questions. You have so many questions. We cannot possibly answer them, but I want to read this to you from Astra H. We appreciate how many of y'all who are not professional science communicators taking that dive into public presentation for this stream. So people were, like I said, the movies were very well received. We are on a movie sharing platform and they were great. You also, when you were showing the diagram of, there were two on the left and the right, and the one on the left had green and blue and purple. There were some rotating around New Zealand happening, and there's a New Zealand contingent in the chat that is just lighting up about the disco balling rave happening around New Zealand. I do want to give you an actual question. So again, you have so many. This is from PB, do internal tides vary by depth? Are there any depth dependent patterns?
Yeah, very much so. So like I said, the internal, if you look at the displacement signal and the sea surface, they're kind of 5 to 20 centimeters in places where they're really big. Way below, like around maybe 700 meters, they can be moving up and down by 100 meters. And then above and below that maximum, they move by lesser amounts. And then there's internal tidal currents. So the currents at the surface are much, much stronger than they are at depth. So there's vertical structure in the internal tide currents as well as in the vertical displacements. Great question.
There's so many great questions in the chat. We have time for one more, and let's see, where is it? Okay, Climate Break asked, to change the colors of the simulation, do you have to rerun the entire model over again? And I'd love to broaden this. We only have a minute or two, but I'd love to broaden it. You said you've been doing models for years and years. What's it like to actually run the models? Do you have to sit there and wait, or is it like you used to, but now it's like you just click a button and there it is?
Yeah, I mean, the biggest ocean models that are run, which I'm involved in some of them, it can take months for them to run. And, you know, it was mentioned in I think it was called the GeekFest. One person talked about the MIT GCM simulation. I mean, I'm heavily involved in analyzing that, and it is the biggest simulation that's ever been done, as the person correctly said. I don't remember the exact numbers, but I think it basically kind of runs in real time. Like if you want to have 3 months of simulation, you have to wait 3 months. I might have the numbers a little bit off, but it's something like that. It takes many months to run 1 year of that simulation. And the person that runs it is one of my best friends in the whole field. His name is Dimitri Menimemlis. So we work together on analyzing that simulation, comparing it to satellite data and other things like that.
Wow. With a runtime of months, I'm imagining the times that I've started something and then been like, oh, there's a mistake. And like month 2, you're like, oh no.
Yeah, and then, you know, like the colors is like you're using the color bars to show what the simulation shows. That's actually relatively easy. I'm not very good at it, but we work with people who are good at making those things. You know, I might also mention Dimitri's simulation is petabytes of storage. So it takes thousands of terabytes of storage. So actually analyzing it is a tremendous effort. It involves a lot of computer science to analyze it quickly.
Well, thank you so much, everyone in the chat. We all have learned so much from you. This was a great, continuation of the oceanography stuff we saw just a little bit before this. Thank you so much for spending your very early morning with us.
All right, thanks a lot for having me.
All right, so again, it is the time. We are at the top of the hour. We are on hour 89. We have 11 hours left. And this is when I normally remind you why we're all together. I said half an hour ago that I would issue you a challenge, and I'm just going to say it right now. If you have not contacted your representatives, mute me, because I am going to be talking for the next 3 to 4 minutes. That's all the time that it takes. And even if you don't want to call right now and leave a message, set yourself a calendar reminder to do it during business hours. Go to the link in the description of this video if you've never contacted your representatives before, and just see what resources are there, because people want to help you make this as easy as possible. Because not just for science, but for anything you care about, the government serves the people, or it should. And that means that you have the right to let the government know what you think they should be doing. I do want to bring up something that Climate Break said a while back when I was first getting a little bit action-y during the last half hour. Climate Break said, calling representatives is hard. I don't want the disappointment of being dropped to voicemail, fed to AI, only for my email to be spammed asking for donations. That doesn't feel good. I agree. It sucks to call your representatives and say, I really care about this. And then they respond 24 hours later with some text or email that's like, can you give me money for this thing that feels urgent? And I know not everybody does this. I probably shouldn't make fun of these emails on the live stream, but as a communicator, I am trained in how to activate people, and I feel distinctly angry and not activated by the response that I get when I contact my representatives. So here's the thing that works for me. As a scientist, when I was getting my PhD, near the end, I was like, okay, but how do I know when I am ready to graduate? How do I know when I'm ready to write my dissertation? When do I stop gathering data and then I write it all up and I get it out? And I remember a friend of mine saying, oh, you'll know when you get so angry that you can't be here anymore. And I was like, that sounds bad. But then what happens is near the end of your PhD, you get so sick of looking at the stuff that you're supposed to be revising, and you're like, oh, I just need to leave for a job. And then you write it up. People call it channeling spite to get a degree. I channel my spite when I contact my representatives, because I have told myself, if I am willing to feed my email address into 4 different swimsuit buying sites, just in case I get that 10% discount for a first-time purchase, I can also feed my burner email address that I use for spam stuff to my representatives, so that when they contact me back with a fundraising email, I can just be like, well, this one I don't need to read. And I set up that filter. So I feel like for me, I have entered a phase of life where I am not going to let your attempts at spam stop me. I am not going to let your attempts to push your agenda stop me from claiming my right to push mine, because I feel like my agenda is to have a better life for myself and for other people. So again, this is not meant to be like a depressing talk, like we're all going to lose our jobs. This is meant to be a real talk about, as a communicator, how do we talk to each other? How do we collectively achieve things that we think should be happening? I find it encouraging that I haven't been like yanked off stage by that like giant cartoon hook and stuff like that. So hopefully this is resonating with some of y'all. If you need help contacting your representative, the people who have set up this live stream have made it as easy as we possibly can. I'm still on here for another hour, so I will have 1 half-hour mark where I can talk to you again, real talk, about how we get things done collectively as a group. And so if you want to have a real chat with me during the next half hour, please put your questions in the chat, your comments in the chat, or whatever it is. If I can help you solve problems, that's the point of this. This live stream, the point is not just to have a good time. The point is to achieve something together that 1 or 2 of us cannot. Oh, I already know what I want to say to you at the next half hour. But right now, it is time to bring on, I'm checking the schedule, Michael Evans from the University of Maryland, College Park. Good morning. Oh, you're Mike. Good morning, Mike.
That works. Hi, can you hear me all right?
Yes, we can hear you great. I've taken up my intro time, and so I'm just going to hand the floor to you. Good morning.
Sure. Okay. Yeah. Thank you. And thank you all for being here. If you're in the East Coast, it's 6 a.m. And I want to also say thank you for all those folks who've been asking such amazing questions in the chat through this streamathon. It's amazing. It's wonderful. Thank you for those great questions. I'll give you a little bit of an introduction to me and a bit of why I do what I do. And then I'll tell you about some current science we're working on, which is around the question of, is El Niño changing as the climate changes, as the radiative forcing of climate by greenhouse gases continues to build. But my message to you is really about why your support for weather and climate research is essential, and in particular, why your support for science education matters even more. And the bottom line is, without that education, science just stops. So with that, let me begin. So a little bit about me. So in my spare time, when I'm not parenting 2 college-age daughters or engaging in various hobbies like bread baking or managing the pet menagerie, I am a paleoclimatologist. I study past climates. What does that actually mean? Well, I use a combination of tools. So we use realistically forced, and by that I mean these radiative forcings. They could be the effects of volcanoes or greenhouse gases or solar variations. That is given to climate models that produce climate simulations. And then the climate simulations I can use to actually simulate the observations that we actually make. What do I mean by that? Well, we make paleoclimate observations indirectly from archives like tree rings, like marine corals, like deep sea and lake sediments from all over the world. And those observations aren't directly usually things like temperature or precipitation. So what we do instead is we transform the climate variables into into the paleoclimate observables. And then we can do a process called detection and attribution, where we try to understand why what we observed happened through the use of both the climate or the data simulations and also the paleoclimate observations. What I want to do today is actually just focus on the paleoclimate observations, if you'll allow me, but maybe we'll get back to the modeling at the end. All right, so a little bit about my motivation. It kind of starts with Mr. Del Moro in middle school at Amity Regional Junior High School in Orange, Connecticut, a town so small we didn't have our own junior high or high school, so we had a combination with two other neighboring towns. So here's a report that I recently found in my attic. I recently moved. Shout out to my neighbors at Eastern Village Co-Housing, where I now live since January. But yeah, so I moved and downsized, and I found this report I wrote on meteorology in 1982. Okay, I was in middle school, and you know, this is before the age of computers for me. So this was all typewritten, and you can see there's like mistakes that I had to correct. And there's hand-drawn pictures of things like the hair hygrometer, you know, which you actually don't use in reality. But I was 12, I read about it. It was kind of cool. I drew this picture. I also took collected weather observations. Thank you, NOAA and the National Weather Service. So I listened to the TV at night, and I wrote down and I graphed the data. And here's some data for the week of end of November, beginning of December. And it turns out actually that if you look at the temperature, you know, it's kind of warm in Orange, Connecticut in the late part of the year. And it turns out it was actually warm in the entire eastern US. So this red shows warm anomalies in the month of December of 1982. So I think I cut off the scale, sorry. But yeah, these are warmer than average. These are our temperature anomalies for the entire month relative to the climatological value. So thank you to not only NOAA, but also to NASA, who produced the reanalysis, a combination of modeling, weather modeling and observations to get a best estimate of what actually was happening at the time. And then also thanks to NOAA and its weather library data imaging project, we have these synoptic weather maps. And here was a storm from February of 1983 that whacked us in, here's Connecticut, for those of you who aren't familiar with the United States, where I was. And I bet I had a snow day or two, and I was probably pretty excited about that. But this warming and the storms, they turned out to be related to, and I had no idea that this was happening at the time. This happened to be related to the 1982 to 1983 El Nino event. So El Nino is a coupled ocean atmosphere phenomena, and it's primarily focused in the tropical Pacific. There's South America, there's Australia and New Guinea, and it's characterized in the ocean by warmer than average sea surface temperatures. These are a few degrees Celsius above average. This is an area that's about a quarter of the circumference around the planet. So this is kind of a big deal in terms of the heating of the atmosphere. And so this drives atmospheric circulation anomalies. And instead of having rainfall be primarily organized around the Western equatorial Pacific, instead it kind of reorganizes around the Central equatorial Pacific. And the Western equatorial Pacific is characterized by drought, and then that drought leads to fire. Okay, and also it turns out that these weather and climate anomalies, which can persist for 12 to 18 months in the tropics, they force characteristic patterns of climate variation in the atmosphere all over the world, in particular over North America for our purposes, and these have real impacts. So the estimate originally for this event, which was rather big, was $8 billion. And according to Wikipedia's references, it might be as big as $4 trillion. So this is a big deal. This drove actually a lot of development of some of the first forecast models for El Nino, and now we can predict a season, 2 seasons, maybe even 3 seasons ahead, whether we're going to have these effects, and we can avoid or mitigate this economic impact. Okay, so this event in 1982, 1983 was called the El Nino of the century for about 15 years, because in 1997, 1998, we had one that was probably even bigger. And so this led to the question, is El Nino changing as we keep forcing the climate with increasing concentrations of the greenhouse gases? So let me turn again to my motivation, okay? And so I got interested in El Nino, and I went to, then I got in graduate school. I was lucky enough to be a student of Mark Kane. He was one of the people who developed one of the first intermediate complexity forecast models of El Nino. But I'm really motivated by students and research scientists that I work with more generally. So we have a stable isotope lab, and students have come through it over the years. There's Caitlin, there's Evier, there's Leah, there's Becca, there's Anne-Marie and Grace, there's Alex, there's Kevin. And all this work was supported by grants from the National Science Foundation. So taxpayers. So thank you, taxpayers, for supporting this work and supporting me in my efforts to give training to all of these students and colleagues. What sort of training do they get? Well, we do paleoclimate science, as I mentioned, but there's also logical troubleshooting, there's communications, there's all kinds of experimental design, project management, data analysis, all kinds of skills, and yeah, thank you, NSF, thank you, taxpayers. What I want to focus on today with a little bit of science is some work by a particular group of students. Here is Sandy, Austin, Jenna, and Mary, and these students worked through the pandemic on their research that I'm about to talk to you about. All right, so I mentioned as a motivation that we had this El Nino in 1982, 1983, and then we had another one in 1997, 1998. Every El Nino is kind of a little bit different from the other ones. This is because of natural variability and in the climate as a system, this complexity of coupling between the ocean and the atmosphere. But the big question in climate research is El Nino changing? And the answer from climate simulations, which are essential to our projections of climate into the 21st century, is maybe. So here is the change in the amplitude of sea surface temperature anomalies. So basically, in the Eastern Equatorial Pacific, a region we call Niño 3-4. Okay, so this is essentially an index of how big El Nino events are. And the gray shows you simulations from historical runs, here from 1950 to 2012. And then the colors show you the simulations from a variety of forcing scenarios called shared socioeconomic pathways, which result in from 1.9 watts per meter square of radiative forcing to about 8.5 watts per meter square of radiative forcing by the end of the century. And the colors give you the error envelope. And so you can see there's a tendency toward an increase in the amplitude from all of these, but it's not really significantly different from 0, meaning no change, 1. So a ratio of the amplitude in the future to the amplitude today of 1, given the uncertainty posed by just the spread of the simulations. The same thing is more or less true for precipitation, okay? But there is a bit of a tendency toward the end of the century for that envelope of variation in some of the most strongly forced simulations to be larger than it is today. And that's something that Kim Cobb in her talk yesterday afternoon alluded to. Okay, so our approach is actually to go back in time. Richard Alley wrote a book, which I highly recommend, called The 2 Mile Time Machine. It's about what we learned from the study of about 120,000 years of climate history from ice cores, and this kind of stylized pattern where you can see these horizontal bars going through this book title is a representation of the layers in ice cores. And so if the most recent layer is at the top, this is the geologic principle of superposition, you go down a layer and you're back in time. And so you kind of count back in time. And so Ali called this the 2 Mile Time Machine, because this ice core was 2 miles long. And as you go back through depth into this ice core, you go back in time. So with apologies to Richard Alley, we have a 20-inch time machine made of wood. And the wood is from a place in Indonesia called Muna. It's in South Sulawesi. The samples were collected by my colleague Roseanne Dorigo and her colleagues. And we have this set of cores, wood cores, and some of them are just of the most recent period, and some of them stretch back into the 1600s. And for comparison here, here's the, in kind of these red bars, this is the radiative forcing from volcanic activity as estimated by dust in ice core records. And this red is the increase in the radiative forcing in units of watts per meter square of greenhouse gases since the 1750s from the IPCC's assessment. So if we can go back in time to a period when that radiative forcing was small, then we can assess whether El Nino is changing as we go forward into the future. Okay, so that's kind of the rationale for this study. So how do you actually collect this data? And the particular data we're collecting is the oxygen isotopic composition from Indonesian wood. So here's how we do it. So first we have to get these cores from trees, and then we cross-date these samples using characteristic patterns in the ring widths. Then we sample that wood for the isotopic composition, and then we load samples into our elemental analyzer. The samples are really small. They're 0.2 milligrams in mass, and they're encapsulated in these tiny little capsules you can barely see here. Then we vaporize those samples and we separate out the gas we want to analyze from the other gases. In this case, the gas we want to analyze is carbon monoxide. It contains the oxygen signature of the wood. And then we do the mass spectrometry. And so what that means is we ionize that carbon monoxide, we accelerate it into a magnetic sector, and we separate the molecules that are labeled with the heavy isotope of oxygen relative to the light isotope of oxygen by mass to charge ratio, and then we report those ratios. And it turns out that, this is 5,689 analyses over 3+ years through the pandemic. So it turns out that oxygen isotopic measure in the wood, through some work that we've done that I'm not going to get into the detail unless you ask me questions about it, is kind of like a rain gauge. Okay, so it's a rain gauge from the Western Equatorial Pacific, and it seems to mirror the passage of rainy and dry events in Indonesia, and those rainy and dry events are in turn driven by these large-scale atmospheric circulation changes associated with El Nino. All right, so here's what we found. So here's all the data. This oxygen isotopic composition measurement in each of the different colors are from the different data series. We separate out just the year-to-year variations because that's primarily the time scale in which we have El Nino events, and we get that black line. And then we can compare that to independent estimates of El Nino variability from historical observations of this Niño 3-4 sea surface temperature index. That's in red here. All right, so we can do that from about 1856 to 2005. And the correlation here is 0.4. So it's a small correlation. There's a lot of uncertainty in this. But the chances that this correlation is not zero, rather is zero by chance, is less than 1 in a million. So we think we have a record, and sometimes it's pretty faithful to what we see, and sometimes it misses. Okay, but this is the nature of paleoclimate. And so the question then became, is there a change in the distribution of events over time? So what we did is we separated that record from 1681 through the present, or 2005, into 25-year chunks. And then we looked at the cumulative distribution of the data within those independent 25-year chunks going forward in time. So for instance, this is in standard deviation units. So there is zero chance that you have a number that's less than 4 standard deviations below the mean. And there's all the data, okay, a probability of 1 that the data fall below a value of plus 3.5 standard deviations above the mean. Okay, and so what all these different colors are the different 25-year segments, and the black is the overall mean. And what these statistics are telling us in their p-values is that there's a very good chance that these are all drawn from the same distribution. In other words, there isn't a change in the distribution of events over time. Now, this has been independently shown by Cook and Kane in 2024. They made a reconstruction of sea surface temperatures from tree ring data from all around the Pacific, and we can find the same result by performing the same analysis from their independent data collection. Okay, but maybe that's not the full story. This is a result from climate simulations with the NCAR, NSF NCAR Community Earth System Model, version 1. And what they did is they compared this Niño 3 index, here shown in time. And this is for a 350-year control simulation. So just let the model run and see what it does. It simulates El Nino events. And these stars tell you when there are rather extreme events, large events. Then they run the model in the configuration where it's warmer. It's been radiated forced to a new climate that's about 3 degrees warmer than present. And you see that if you compare those indications of extreme events done in the same way, you have a lot more extreme events in this warm climate. So maybe we just haven't seen this first signal because it hasn't emerged yet. All right, I think I'm out of time. That's the barking dog. But my ask to you is to support training grants for students. And in particular, you can talk to your Congress people about the National Science Foundation's Graduate Research Fellowship Program, GRFP, which has been running since 1952. I have reviewed for it for 10 or 11 years. It's pretty amazing to read these applications from students. Over the previous decade, we had 2,000 of these fellowships awarded each year. And of course, you read these and you want to award many more because there's so many deserving students out there. In 2024, this went up to 2,500 fellowships. This year, only 1,000 fellowships have been awarded to date. So without this sort of support, science just stops. These are really great applicants. Please support science education. All right, so here's a summary in haiku, and I'm out of time, so I'll just put it up. And I would hope that I can have time to answer questions. Thank you very much for listening and for being awake.
Thank you so much, Mike. I love the haiku summary. I love the emphasis on students, not just the people who are here on this stream. You do have time for a question. I want to get into it fairly quickly so we can make sure that you have time for these questions. I want to start the reactions to the beginning of your talk. I just want to highlight a couple of them. Microscopic Marvel was yelling, yay, middle school science teachers. Kelly said there are those teachers that you never forget. Mark said, shout out to teachers that motivated career scientists and parents who encouraged interest. So you really hit a relatable nerve there for so many people.
Shout out to that Tumblr gang also. I've seen they've been like totally fierce and been present all the time. They have such great questions.
I see that you've been monitoring the chat yourself. Yes.
No, I've been going to talks all week and it's been amazing. Yeah.
Yeah. I do want to ask, so the thing that came up most often in chat, and I may have missed this, I'm sorry if I did, but you showed a chart early on that showed El Nino variation through time, and it was at that one mark until about 2000 when it just went merp. And there were a couple people in the chat like, what happened around 2000? And I just want to make sure that was such a... If I missed this question and you said it, I'm so sorry, but it was multiple people were asking it because this graph is just so compelling.
This slide right here?
No, it was back a few. It was around a 1 mark for most of the chart.
I number my slides, so was it?
I think it was before this one, maybe the one right before that. Yes, this chart. What happened?
Sorry, what are you referring to exactly?
Yeah, so what happened around year 2000? It looks normal until around 2000, 2010, and then all of a sudden. So people were asking on this graph, why do we have normal to the left of 2000, 2010, and then just exploding on the right?
Okay. So the way I look at this, actually, that's a good question. So you see there's like a small envelope of variation in this period from about 2000 to maybe 2015 or so. Is that what you're referring to?
Yes.
Yeah. Okay. So I think that's partly a function of how the data are formed. So it has to be a standard deviation relative to 1995 to 2014. Well, that's exactly this period right here. So by definition, this ratio is 1. Okay. And so I think that's what's happening there. Part of it also is possibly that what's actually happening here is that there are natural changes over decades in which the amplitude of El Nino events, they get smaller and then they get bigger. And we saw this actually through after about 1945 till about 1965, 1970, 1975, the event amplitude got smaller and the time between events got longer. And we think this is part of the natural variability. So that's another part of what's going on here. So part of it is just the way the data are presented to you here, and part of it is real changes in the amplitude over decades, something that we see from historical observations and something that we also see from the paleoclimate observations. It makes it so hard to see a forced response in El Nino to greenhouse forcing.
Okay, so when we look at graphs about change over time, we have to remember that the graph itself we weren't predicting backwards. We were monitoring backwards and then we predict forwards. So these graphs will often look like then something known and then something that explodes.
Yep. And those predictions backward in paleoclimate we call reconstructions, and in model world we call them hindcasts because it's something we know happened. Paleoclimate turns out to be a really nice way to test our climate models because you can kind of run them for configurations for the paleoclimate past and see whether they produced results that look like what we observe.
Okay, perfect. Thank you so much for this talk. It was very well received in the chat. I appreciate your drive, your enthusiasm, sharing all of that with us at 6:30 in the morning. I'm going to let you go and get on with the rest of your day.
Thank you all for being here. Thanks. Bye.
Thanks. All right, everyone, it is my last time to pause and remind us why we're all together. I said that I wanted you to actually mute me for the next 3 minutes. If you haven't made plans to contact your representative, we have time. I'm just going to talk to you about why we are all united. If you want to see me, you can come back to the YouTube channel, watch it in the past, or if you want to, watch me now, but then do not forget to actually contact your representatives if you're in the US or if you're abroad and you are eligible to vote in the US. That is the point of this live stream. This is what it feels like to be a movement and not just a comment section of a YouTube video, is to see this and then go act. I said I knew what I wanted to talk about. I haven't seen any questions in the chat about like, here's a challenge I'm feeling when I contact my reps, besides what we talked about last time. So I just want to touch on how we know it works to contact your representatives, because I touched last time on how it feels so bad. And then I draw from my own personal spite to contact people anyway and be like, no, but you need to listen to me. How we know this works is politicians and their staffers share numbers. I have seen them on social media. I have seen them in advice articles about how when there is any issue that our representatives are discussing, voting on, making policy on, they usually don't get many comments about it from the public. And so the numbers I've seen are people saying that something like being contacted a couple hundred times about an issue is enough to make people be like, whoa now, this is a lot of interest, and people feel very strongly, right? If you think about that couple hundred people, it's weird because you are just one person. But there are hundreds of thousands of us that have watched this live stream, that there are hundreds of thousands of you. I suppose I haven't been watching as from your end the same way, but there are hundreds of thousands of people who have come to this live stream. There are thousands of you. I don't want to steal the thunder of the live stream if they're going to announce at the end how many people have acted because of it, but there are thousands of you that are acting. That will make a huge difference. We know it does. I know one of the organizers put in the chat, we have a couple hundred people here. What if we did? If you muted right now, it would take you, if you click that link, the one that's scrolling on the screen is in the description of the video. Everything at that site is designed to help you do this well. You do not have to be an expert. You do not have to know what to say. You don't have to have the information for your representatives. It's all right there. Okay. And like I said, if you don't like how it feels when they respond to you, I, a professional communicator, don't like it either. And to get totally nerdy, this is a huge discussion among professional communication communities, is how we interact with our representatives and how they interact back with us does not follow the science of science communication, because science communication is a research field in its own right. I do some science communication research. Other people have done much more. We know what works for activating people. Our representatives do not do that. And it feels weird and bad, especially as a communicator, to know it, to see it. But it is our job as informed, like, people on this earth who want to make a better life to say, your bad communication is not going to stop me from pushing for the world to be the way I think it should be. So if you have not acted yet, that is the point of this live stream. Please don't let me fail you. Don't let me fail to activate you. Make sure you do that, because that is what will keep all of us working on this very cool stuff and coming back to you year after year to share our joy with you again. It is 6:36 my time. I would like to introduce our next speaker and bring them onto the stage. Thank you so much. David, good morning.
Morning. Can you hear me?
Yes.
Okay, great. So yeah, thanks for allowing me to talk about this work a little bit. I could have given talks about many different topics. I'll talk about that in a moment, but I thought this was important to talk about, to just highlight what each of these agencies do, NSF, NASA, NOAA. I'll talk more about the NOAA contribution, and I'll talk about how we monitor heat, how much heat is in the ocean, so the ocean environment, or the marine environment, the Navy now has to refer to it as the marine battle space. I'll highlight things like that as well, how we have to change our language. Like, I can't say the C word, CLIMATE, but I'll talk about how I got to where I am just briefly. So being an academic for me meant geographic instability. So especially when you have I don't want to call it a problem, but it's referred to historically as the two-body problem. If you have a spouse, partner, etc. things get complicated. And so this geographic instability has led to research focus instability throughout my career. So I did a PhD at University of Washington in physical oceanography. I studied transient tracers there, like CFCs from air conditioners, etc. And then I went on, actually 2 speakers ago was my first postdoc advisor. I had no idea that he was going to be scheduled for that time. And I could have talked about my efforts to improve the representation of ocean circulation and its role in the Seawater. And then my second postdoc was continuing those efforts. Then I studied here and there a bit of ocean oxygen. I haven't seen a talk about that, but I may have missed it. I haven't been awake for 90 hours. But I chose to focus on this, and I've eventually landed at University of Maryland's, which I didn't know the previous speaker also is affiliated with, and I'm a NOAA affiliate, it's called. And so I get funded by writing grants to support NOAA mission efforts. That's basically what it means. It's a way to funnel money from agencies like NOAA to universities so that we do a lot of the work that supports NOAA and other people support NASA. I worked with someone at NASA off of an NSF grant recently, and I'll show you a little bit of that. So I'm going to back up a bit, and this is kind of an abstraction, but I'm just going to talk about how the way that we view the health of the ocean, according to some high schoolers, is to use a camera. So they think we observe the ocean with cameras. That was the response overwhelmingly when I did outreach and I asked them how we monitor the ocean. So what you can see about the ocean's health using a camera are coral reefs. And I wrote a song about this. I don't know if you could hear it, but I purposefully lean on some notes for far too long in this song, and that's supposed to reflect the degree heating days, it's called, in coral reefs. So this one pictured here is a healthy one, but then there's an unhealthy one on the right. So this note here. So you feel like I leaned on it too long. So there are a bunch of things that can happen for far too long that can lead to this bleaching in the ocean. About 84% of the world's coral reefs have experienced bleaching over the past year. That's been increasing. And it's partially because of the amount of heat that they're experiencing for too long. For a certain amount of time. It could also be due to hypoxia, so low oxygen conditions, or acidity eroding their calcium carbonate shell. But here I'm going to focus on heat. And the answer to this question is no. Yeah. So you can do with that what you like. But some of these products that NOAA puts out are, so for example, NOAA Coral Reef Watch. They put out these products warning people for conservation efforts and just knowledge, how long these coral reefs have been exposed to dangerously hot conditions. So heating weeks, but they only measure the surface, and coral reefs are at the bottom. So because they reside at the seafloor, we need more information than just the temperature of the surface, and that's why I'm going to talk about what I am for the rest of the talk. We need to know the amount of heat throughout the water column. So that's the topic here. How do we do that? So there's this HMS Challenger expedition, and so it's been 150 years since this happened. And so we can compare the modern temperatures in the ocean with the temperatures 150 years ago. along this route. And so you can see that the world has warmed along this route. The ocean, so there are somewhat large uncertainties because the way that they took measurements 150 years ago was literally they took a bucket off the side of a ship and it stuck in a thermometer. So, and of course that has some bias, and so people have just constructed methods to be able to correct for that bias, but it still has some uncertainty. But in the end, you get that the ocean is warmed along that way. So ever since we've had all these expeditions to go out and sample the ocean, and the density of the sampling looks a lot like our highway system. So imagine you think that you could see the entire US from off the side of the highway. That's basically how well we've observed the ocean. How we eventually we have developed programs like the Argo program. Shout out to Argo again. I think almost every talk has mentioned Argo, at least one that's had to do with the ocean. And so all those red dots and other colors are floats that cover the top 2,000 meters at the very least. So the vast majority of them covered 2,000 meters. And you can see a time series on the bottom right of the world ocean warming based on these floats. And so, but those floats can't surface to relay the information to satellites underneath sea ice. So what do you do underneath sea ice? We can supplement those data with some ship-based data if you use an icebreaker. We've seen some talks about that. Or you can use instruments that are strapped to elephant seals, other marine mammals. And these marine mammals dive below the ice and take data for us. We can't control where they go, but they relay information to satellites when they surface, and we have a lot of temperature data and salinity data because of that as well. And imagine the deep blue in the North Pacific that you see on the top left, just disappearing. That's the impact of coverage also in places like between Antarctica and South America. That's the impact that it would have if we could no longer support these programs in the US, because that was the US's contribution. So in the end, when we put together all those data that I was just talking about in the top 2,000 meters, we come up with, so the amount of warming in the ocean looks like the warming in the map, and the time series of the global average annual mean is shown in the bar plot. And it's only increased ever since. And so I want you to remember how that map looks. There's some features there that will come up later because there are independent methods that we use to try to monitor how much heat is in the ocean. But I want to emphasize first that this is just the top 2,000 meters. And as we can do these energy balances of other parts of the Earth system, like how much energy goes into land, how much energy goes into melting ice, because we monitor how much ice there is with gravity-based satellites like GRACE follow-on, and then we back out how much energy needed to go into that to melt that ice. And we can infer that it goes into the ocean below 2,000 meters is actually growing in time, and actually comparable, or if not bigger, than the amount of energy that's gone into land. And so we need to monitor what's going into the ocean below 2,000 meters as well. And so I'm going to talk about that now. So we have these ship-based programs, and they actually do monitor below 2,000 meters, but it's pretty sparse and aliased. So they monitor they do these repeat transects every 5 to 10 years. And you can see that on the top. And so there have been studies that sampled models to see how well that actually samples the ocean. And
so temporally and spatially. And there are biases of about 10 to 20%. And so that might not suffice. So Deep Argo is this program that has floats go down to 4,000 or 6,000 meters. And we only have less than 200 floats, though, at this point for that program. But if you use the ship-based measurements, this is what you see, even though it's potentially biased by that 10 to 20%. But you see a strong warming signal, especially in the Arctic, but also in the Southern Ocean, because that's where Antarctic bottom water forms off the shelf. So I tried to develop a remote sensing method, and that's kind of the takeaway from this talk, that we need to maintain both the in situ measurements that I just talked about and satellite systems of monitoring the ocean to complement each other to be able to know what's going on. And I'll talk about for what applications in a bit. So we could harness the electrical properties of the ocean because the interior of the Earth has a bunch of metals and it's moving, and also it's ferromagnetic. It generates a magnetic field. Because the ocean carries these ions and they move through that magnetic field, it generates its own magnetic field. And this magnetic field that the ocean generates, you could back out how conductive the depth integrated ocean is. And that's what's shown, the anomaly over time is shown on the x-axis in the top right versus the amount of heat in on the y-axis. And they're very highly correlated. And that's because the amount of conductivity at the surface is strongly related to the amount of heat that's uptaken by the ocean in the vast majority of locations that are shown mostly in blue on the bottom left. And then also in the interior, the transport of heat is strongly related to the transport of electrical conductivity. So if you take information from 3 types of satellites for sea level, for the magnetic field, and for the amount of mass of the ocean, then you can actually get the amount of heat that's in the ocean throughout the entire water column, not just in the top 2,000 meters, pretty accurately. That's shown in the blue and green on the bottom left. In the Arctic regions, you can sample it differently and train this machine learning algorithm I used differently in order to observe the high latitudes as well. So another method that people have used over the years, this is just an interesting story, is to produce these acoustic pings. Say you go out on a ship, you use sonar, and so the time that it takes that signal to go to the seafloor and back is related to the amount of heat that's in the water column. Because the speed of sound is related to the temperature, salinity, and pressure of the water. And so you can back out the amount of heat from this, but if you were to do that, you would probably make dolphins' ears bleed. Other marine mammals too, it would affect them. And so people had a big concern about this, and there was a lot of controversy. And this has been written about in extensive detail by Naomi Oreskes. And I highly recommend this book if you want to know the history of a lot of geoscience. But instead, you can make dolphins happy, and you can instead wait for seismic signals. So from 2 different events in approximately the same place. So there's this P wave that has very short wavelengths, and that goes through land, and then a T wave, longer, that goes through the ocean. And you can tell the difference between these 2 events. the wave properties, and you could back out the temperature from them, like I was talking about with the speed of sound in water. And so what are some implications of being able to use some of these independent methods for telling how much heat is in the ocean? So a big picture about the C word, we could use this satellite series that you can tell from the amount of radiation that's coming out from Earth by Planck's law. Those have very, very long wavelengths. That's cooler temperatures versus how much radiation is going into Earth. Those have short wavelengths. Those are very high temperatures. And you could tell the balance between the amount of radiation that's going in versus out, and also how much is being reflected by clouds, etc., as shown in this plot. And you get a net top of the atmosphere TOA imbalance. And that's approximately equal to the amount of heat that's going into the ocean. In fact, over 90%. So people have talked about that in previous talks, but this imbalance is changing over time. And so this imbalance has a bunch of consequences, non-oceanic ones including, and I probably don't have time to talk about them, but this is leading to things like melting ice and changing the amount of heat that's on land and our warming temperatures. So also, how do we, so I mentioned being able to observe sea level anomalies. So how do we do that? There's the satellite altimetry. So I'll show you a picture on the next slide, but this is a time series of which satellites have existed over time. So this is a record of over 30 years at this point, and this is an amazing effort worldwide, and it's very collaborative internationally. This is one of the few examples I can think of off the top of my head where this is a successful international collaboration where people have engineered ways to monitor centimeter level variations. That's the uncertainty, which is amazing considering how many things you need to correct for in monitoring sea level anomalies. And so the branch of NOAA that I collaborate with most closely is the Laboratory for Satellite Altimetry. So this is kind of my specialty now. And so you have to assume this geoid, or if the ocean were to stop being forced by winds and tides, this is the kind of what the sea surface would look like. So you have this geoid model, and then relative to that, the satellite altimetry can tell you how high the sea level is. And so over time, over the past 30 years, over various time periods, you can see that the ocean generally has gotten higher. So it's been trending in the direction of sea level rise. So what's causing these changes? So a third of it is due to the warming and changes in salinity to a lesser extent that I referred to earlier. And then 2/3 is this non-steric sea level. So it's called barostatic. It's the ocean mass. That's melting ice. The ice that's gone from land, melted, and gotten into the ocean. I know that other speakers like CC Bits have mentioned that. And so we can actually use that information to be able to monitor how much heat is in the ocean, to bring it back to the theme of the talk. That seemed like an excursion, I'm pretty sure. But if you were to take the sea level and then remove the amount of mass signal, the mass anomaly, so from Grace follow-on, the barostatic contribution that I talked about, then you have the steric contribution from temperature and salinity. So then you could remove the contribution from salinity because it hasn't changed as much as temperature in contribution to sea level. but we only have the top 2,000 meters from places, sources like Argo. And then you're left with the thermospheric contribution from the amount of heat in the ocean. And from that, you can actually back out how much heat there is in the ocean. So you can monitor how much heat anomalies is from space, which is incredible. And on the bottom here, so the top shows a different time period of anomalies for how much heat is in the ocean based on space from 2002 to 2060. And the bottom shows relative to the top of the atmosphere energy imbalance, and you can see that they're pretty strongly related. So 90% of the heat goes into the ocean. So what is the relevance here? I'm running out of time, but so to talk about this really quickly, hurricane forecasts have improved in their intensity very substantially over time, over the past decades. Wind forecasting errors saves a lot of money. You save about $1 billion relative to 2007 in 2020 in emergency funds, damages, etc. And the amount of heat that's in the ocean, if you incorporate that information into forecasts, actually improves the forecast by and large. There are some factors like the vertical wind shear and other atmospheric conditions like the dryness that can influence it. But let's say we were able to initialize these forecast models better. So on the left, a subset of those observations are used because of quality control issues, et cetera, and the depth that they go to initialize these hurricane forecasts. But on the right is a method that I've helped develop using satellite altimetry to get profiles of temperature and salinity so you can better initialize these forecasts. So we actually do a better job than the forecasting models of getting that temperature and salinity, and that's what it's shown here. And we show some examples of that for Hurricane Sally. If you used our method to initialize the model with temperature and salinity, then you actually would have improved the forecast. And so there are other examples of hurricanes as well, where cocaine washes up. So what we need to be doing is maintaining the in situ system coverage. We need to maintain satellite coverage. We need to collaborate with international communities. We need to be using all this information to initialize the forecasts to be able to improve them, because we've heard in other talks how these forecasts, there's chaos. Little changes in initial conditions could lead to large changes. We want the most accurate initial conditions as possible, and we need to continue improving the models themselves. Didn't talk about that, but these layoffs and funding cuts hurt these efforts. And thanks, that's all I wanted to say.
Thank you so much. We are pretty much at time, and I just want to ask a quick question. You've got several, but I want to ask a quick question about Argo floats because people are very interested in these. I'm not sure if you know the answer to this, but people are wondering, do ships ever run across them? Do Argo floats get stuck in currents? Do they ever go places where people are like, oh no, not there? Like, how does that work?
Oh, of course. So we seed them in a particular place. So we take advantage of the fact that some fisher people go out and they'll deploy the floats, or maybe some ships for other purposes will go out and they'll deploy the floats. We want to seed them in particular places, and we try to design where those places are, knowing that they are going to be carried by the currents elsewhere. And so we want to get as good of a sampling as possible. And so people use these particle tracking simulations to try to predict where they'll go. And so you need to plan that ahead of time. And yes, they are carried elsewhere. And because of careful planning, we make sure that they don't often go below sea ice. But their battery lengths are long enough that if they were to temporarily, it would be fine. It would just relay the data the next time it could come to the surface.
Perfect. Thank you so much for that quick answer. I'm going to let you get on with your day because we have to do some administrative stuff because it is now hour 91 of this live stream. We have only 9 hours, 10 hours left. I know that's that weird thing where hour 100 counts. So David, thank you so much. And everyone watching, we need to do a stream reset. We do this every day at this time and other times. But the reason we do this is because YouTube will only let you archive live streams if they are less than 12 hours. And we want to make sure that we can give as many of these videos back to y'all in a publicly available format after this live stream is done. So if you've done this before, you know the drill. If you are new here, once I say goodbye, a link will appear on your screen. Go to that link, join the live stream. It should be very easy, but it just takes us a couple minutes to start the whole thing over. When you get there, everyone's going to yell at me about this. When you get there, like and subscribe because that helps YouTube like the video. This is my last time hosting. It has been an absolute joy and delight to connect with y'all. I hope I run into you in other corners of the internet. Bye for now.